Hello, Saki-san. Very nice. I can't hear you.
Hi, can
Hello,
you hear me?
how are you? Good to see you.
Yeah, nice to meet you again.
Yeah, nice to meet you.
Thank you very much for inviting me.
Yeah, thank you very much for joining. I mean, it's really always a pleasure to listen to you.
Congratulations for your 11th anniversary for your.
Yeah, thank you so much. And you people have been very great support. I really appreciate. Okay, so good morning, Wolfgang.
Hi.
Hello, Sanjay.
Hi, Subhankarda. Hope I'm in time.
Yes, yes.
Yeah.
So in principle, we can start maybe 1 minute because people are just joining in. Actually, in India,
okay.
it is 2 o'clock and it's kind of just after lunch. And
yes. It's just after lunch, and in Europe it's 9:30. So
yeah, so it's a bit early. So, but I see in last 2 minutes about 10 people join. So maybe we just wait 1 or 2 minutes. So
yeah, sure, we can wait.
Okay, so we have now about 30 people. So I think we can just start, and I'm sure while starting, people will join in. So
Okay.
Yeah, good afternoon, good morning, good evening, wherever you are. So I'm very happy and thankful, grateful to all of you for your kind support in always helping and supporting in our events, in our academic life, personal life as well. So this is the third day of the Symposium on Magnetism Spintronics. So the last 2 days have been really great, wonderful talks. And Sanjay, can you please mute for a second? Sanjay, yeah. So thank you.
Yeah.
Sanjay, can you please mute for a second? Yeah, thank you. So last 2 days have been really great talks. We have enjoyed interacting and listening a lot of nice physics, nice talks. So today we continue with the same spirit. So the first session will be chaired by Professor Sanjay Singh, very good friend of mine from Indian Institute of Technology, BHU, Banaras Hindu University, IIT BHU in Varanasi. He works on several things, but mostly bulk materials, topological Hall effect, anomalous Hall effect, and many interesting stuffs. So I'm really happy, Sanjay. Thank you. You are traveling, I know, so you are joining from your mobile. So yeah, I think it's all over to you. I just like to mention that the talks will be for 30 minutes, including discussion. So say about 25 minutes for talks and about 4 to 5 minutes for question answers. And at the end of each talk, we will have these mementos, which I request you to present to the speakers. And then we have allocated this virtual platform frame for each speakers. I think it is best that if possible, all the speakers, if they're around during the break between 4:30 to 5 p.m. and during the poster session, if they can be kindly available on the frame platform on the allocated zones in different rooms, then probably some people can come and interact with you. So with this short note, I just now hand over to you, Sanjay, and kindly coordinate the session. Thank you so much.
Thank you, Subhankar. So, welcome to all participants in day 3rd. And in this session, we have 5 speakers. So, our first speaker is Professor Takeshi Seki. And Professor Seki became an assistant professor at Tohoku University. Tohoku University in 2010. He received his PhD in material science from Tohoku University, Sendai, Japan in 2006. He was a postdoctoral researcher with Tohoku University and Osaka University. Osaka, Japan. His major research interest includes the material development for spintronic device, spin transfer phenomena, magnetization dynamics in nano-sized region, and magnetization reversible mechanism. So I welcome Professor Saki for his talk and hope we will enjoy his talk. Professor Saki, over to you.
Thank you very much. Can you hear? Well, just a moment.
Yes, we can hear you and we can see.
Okay.
Oh no, it just stopped.
Yeah,
but
yeah.
Your screen was
sorry.
visible.
I'm sorry.
No problem.
Can you see my slide?
Yes, yes.
Yeah, we can see.
Kindly go in the full screen mode.
Yes. How about it?
Yes, now it's fine. Thank you.
Yeah, nice.
Okay.
It's fine. Thank you.
Thank you very much for very, very kind introduction. So my name is Seki from IMR, Tohoku University, Japan. First of all, I would like to appreciate giving me an opportunity to talk here about our recent research activities. Especially today, I'm going to talk about the spin charge conversion in ferromagnetic materials. So this is the contents of today's my talk. First, I will briefly explain the background of this study, especially for the spin charge conversion phenomena. And first half of my talk will focus on the spin anomalous Hall effect in L10 ion platinum. And then I would like to share our recent research about the spin self-induced spin orbit talk in permal layer. And finally, I'll summarize my talk. Okay, and as you may know, so spin Hall effect, this is a central role of the recent Spintronics. If you have the non-magnet with a strong spin-orbital interaction, and by flowing the charge current in this direction, and up spins and down spins are scattered in the opposite direction, and transverse direction to the charge current, we may have a spin current, which is a flow of the spin angular momentum. And this spin current is given by this equation. And if we put some ferromagnet near adjacent to the non-magnet, due to the spin torque induced by the spin current from the spin Hall effect, we may switch the magnetization. This is called spin orbit torque switching, and which was firstly demonstrated by Cornell University with using the cobalt ion bond MgO cobalt ion bond tantalum layer structure. Here, tantalum is a spin Hall material, and they observe the clear spin orbit torque switching. And in order to develop the spin Hall spintronic devices using the spin Hall effect, we need to have the large spin Hall angle because this is the parameter for the spin conversion efficiency. And then in order to investigate the spin Hall material, so especially spin orbit torque, so many researchers use the bilayer system consisting of the ferromagnetic material and non-magnetic material, in which by flowing the charge current due to the spin Hall effect, we may generate the spin current in the perpendicular direction to the film plane, which interact with the magnetization of the ferromagnet. And by using this ferromagnet as a detector of the spin current, we can evaluate the magnitude of the spin Hall effect in non-magnet. This is a basic strategy to investigate, to do the spin orbit torque experiment. So our group recently reported several materials which shows the large spin Hall effect. And recently, so we know, so even in the case of the ferromagnetic material, we can generate the spin current, which is very similar to the non-magnet. In order to investigate the spin current generation from the ferromagnet, usually we may use the tri-layer structure having the two ferromagnets separated by the non-magnet. And in one ferromagnet, we may generate the spin current due to the spin anomalous Hall effect. That spin current is interact with the other magnetization in the other ferromagnet. Therefore, this ferromagnet works as a detector of the spin current. And we can evaluate the spin current generation or in the ferromagnet. And very recently, without using any spin current detector, we can evaluate the spin orbit torque, which is called the single layer spin orbit torque. In this case, even in the case of the single ferromagnetic layer, we can generate the spin current, and that spin current interact with the magnetization of the ferromagnet itself, and we can detect the spin current. And today, so I would like to explain this spin anomalous Hall effect as the first topic. And then as a second topic, I would like to share our recent result of the single layer SOT. Okay, so let me start from the first topic. And here in this view graph, I would like to revisit what anomalous Hall effect is. Now you have the ferromagnet with the spontaneous magnetization. By flowing the charge current, charge accumulation occurs at the edges of the sample. At the same time, we can consider the separation of the spins. And along the transverse direction to the charge current, we can get the anomalous Hall current together with the spin current. This is called the spin anomalous Hall effect. So because this phenomena is coming from the anomalous Hall effect. And spin current due to the spin anomalous Hall effect is given by this equation with the spin polarization factors and anomalous Hall angle. And the product of the anomalous Hall angle and the spin polarization factors, which is called the spin anomalous Hall angle. And important point here is the advantage of this spin anomalous Hall effect is quantization axis of the spin current can be controlled by the magnetization because this phenomenon is coming from the anomalous Hall effect. Therefore, if we can develop some ferromagnetic material with a tilted magnetization, we may realize the field-free switching of by the spin orbit torque. This is advantage from the practical point of view. And then first demonstration, observation of this spin anomalous Hall effect was given by AIST in Japan. They investigated the spin anomalous Hall effect in cobalt ion boron by using the cobalt ion boron copper permalloy. Here, permalloy is the detector of the spin current. They injected the DC current into the cobalt ion boron layer, and due to the spin anomalous Hall effect, they generated the spin current along the perpendicular direction to the film plane. That spin current interacts with the magnetization of the permalloy. And they investigated the ephemeral line wheels, and that line wheels is modulated by the spin current. And the line wheels modulation was observed by changing the DC current. And from the fitting, they evaluated the spin anomalous Hall effect for cobalt ion boron that obtained to be about 1 minus 0.14. This is a large. However, so from the viewpoint of the development of high performance Spintronics devices, so we should have the material which shows the larger spin anomalous Hall effect. The second point is we needed to carefully consider the symmetry for the spin anomalous Hall effect. As I said, spin anomalous Hall effect originates from the anomalous Hall effect. Therefore, the spin current generation strongly depends on the magnetization direction. And that means in this orthogonal configuration, we can effectively generate the spin current due to the spin anomalous Hall effect. However, so even in the case of the ferromagnet, we may have the usual spin Hall effect, as in the case of the non-magnet. That is the M-independent phenomenon. Therefore, even in the case of the configuration with charge current, in which charge current and the magnetizations are aligned in parallel, even in this case, so we may have the spin current generation. And we need to carefully separate these phenomena. Also, there are the other spin current generation, which comes from the interface scattering. And interface scattering polarize some electrons and which generate the spin current. Also, such a spin current interact with the magnetization. Therefore, in order to quantitatively discuss the spin anomalous Hall effect, we need to separate the spin current contribution of the spin anomalous Hall effect from the other effects. And then, so we focus on the spin anomalous Solar effect in L1 ion platinum, because this L1 ion platinum shows the large anomalous fall angle. Also, this material has a strong magnetic anisotropy along the c-axis direction of the crystal structure. And we tried to observe the spin anomalous Solar effect in L1 ion platinum, and we evaluated the spin anomalous fall angle for L1 ion platinum by utilizing the spin top FMR technique. And then we would like to discuss today I would like to discuss the symmetry of the spin anomalous Solar effect, and finally I will show the spin anomalous Solar effect induced magnetization switching. And so this is a film structure which used for this study. We deposited the same film on the strontium titanate 110 substrate, and trilayer structure consisting of the L1 ion platinum copper permalloys were deposited. Important point here is we use the strontium titanate 110 substrate, and we successfully glue the L1 ion platinum epitaxially. Therefore, L1 ion platinum shows a 2-2-0 crystal orientation. That means the c-axis of the L1 ion platinum lies in the film plane. Then, so we can see the two-fold symmetry of the crystal structure, and we obtained this epitaxial relationship. And thanks to this epitaxial growth, this film, this L1 ion platinum, has an in-plane uniaxial magnetic anisotropy. These are the image curves, and red one is the image curve with the magnetic field along the in-plane 001 direction, and green one is for the magnetic field along the in-plane 1-1 direction. You can see the clear difference between two in-plane magnetization curves. Therefore, this material, this L1 ion platinum, has easy magnetization axis along the in-plane 001 direction. And then we fabricated the CIP, current in-plane giant magnet resistance devices, by utilizing the standard microfabrication technique. And in this study, we prepared two kinds of devices with two kinds of magnetization configuration. One is the orthogonal configuration, in which the current direction and the ion platinum magnetizations have an orthogonal configuration. And the other one is a parallel configuration, in which ion platinum magnetization and the charge current directions are aligned in the parallel. And by using the standard setup of the STFMR, we measure the modulation of the line wells. Important point here is different configurations allows us to discuss the symmetry of the spin anomalous Solar effect, as which will be explained later. And first, we checked MR effect. You can see by changing the external magnetic field direction, and so you can see the clear MR effect. Appearance of the clear CIP-GMR effect, which is the evidence of the spin-dependent transport. And the important point here is, so even at the magnetic field angle not equal 90 degrees, that means this direction. So orthogonal configuration of the ion platinum and current direction is achieved. And then we did the STFMR measurement for the orthogonal configuration device with DC current of 4 milliampere and -4 milliampere. You can see, so line width is modulated depending on the magnitude of the DC current. And this is a line width as a function of DC current measured at different field angle. And you can see the linear change with changing the DC current, and slope strongly depends on the field angle. And this is a line width change by the DC current as a function of the field angle. And experimental data, blue points, were well fitted by this equation, which includes the spin anomalous Solar angle. Therefore, so we evaluated the spin anomalous Solar angle for L1 ion platinum to be 0.25. This value is quite large. And same procedure and same measurement were done for the parallel configuration device. And as you can see, we cannot see any clear field angular dependence. Therefore, now we consider in the present devices, the spin anomalous force and spin anomalous Hall effect is dominant, and the contribution of the spin Hall effect, M-independent spin Hall effect, is negligibly small. Unfortunately, so in this our measurement setup, we cannot detect the spin current generated by the interface scattering origin. Therefore, at present, we have no idea for the contribution from the interface scattering. Anyway, now, so we have the large spin anomalous Hall angle of L1 iron platinum. And by utilizing the spin anomalous Hall effect in L1 iron platinum to generate the spin current to switch the magnetization of the permanent layer. And this is also orthogonal configuration device by utilizing the pulse-like sequence. And so we observe the resistance change by changing the applied DC current, and the clear hysteretic transition was observed. And this hysteresis gradually shift with changing the external magnetic field. Therefore, we successfully demonstrated the spin anomalous Hall effect in this magnetized switching. And the important point here is a small switching current is achieved due thanks to the large spin anomalous Hall effect. All right, this is a summary of the first half of my today's talk. So we observed the large spin anomalous Hall effect in L1 iron platinum, which shows the large spin anomalous Hall angle of about 0.25. And thanks to the different configurations, so we successfully discuss and we successfully separate the spin anomalous Hall effect contribution from the other effect, and we demonstrated the spin anomalous Hall effect induced magnetization switching. Okay, let's move to the second topic. That is a self-induced spin orbit torque in permalloy. As I said, so recent experiment reveals so ferromagnetic layer can generate a spin current. And in addition, so recent study imply existence of the self-induced spin orbit torque in the ferromagnet. And so there are several researches for iron manganese, permalloy, L1 iron platinum, cobalt platinum, and terbium cobalt by utilizing the several different experimental techniques, and possible mechanisms are proposed like this. Actually, so we have no definite idea to explain the origin of the self-induced spin orbit torque. However, so this self-induced spin orbit torque allow us to switch the magnetization in the single ferromagnetic layer. Also, we can realize we can excite the spin torque oscillation in the single permanent layer. This was reported by the University Yotebori group, and they clearly observed the spin torque oscillation. However, in order to explain this phenomena, they need to assume the very large spin Hall angle in permalloy. That was 13%. And then we would like to consider what is the origin for this spin orbit torque, self-induced spin orbit torque. And so in order to generate the self-induced spin orbit torque, so we need to consider the inversion symmetry breaking, and possible source of the broken inversion symmetry. And
sorry, Professor Seki, you have 2 minutes to complete 25. Then we have 5 minutes for discussion.
Just 2 minutes.
No, I think Sanjay, we started a bit late.
Okay, so
I think he has about 5 to 6 minutes.
Okay, fine.
Yeah.
Okay, thank you. And so in this study, so we consider 3 kinds of the structure. One is a ferromagnetic layer with different non-magnetic materials, which leads to the broken inversion symmetry. Also, even the case of the ferromagnet with the same non-magnetic layer with different interface quality, which also leads to the broken inversion symmetry. And ferromagnetic layer with a structural evolution, such as a composition gradient, which may also induce some the broken inversion symmetry. And therefore, in order to examine this idea, so we did the spin torque STFMR measurement for very thin permalloy layer ion nickel layer with and without structural inversion symmetry by preparing an asymmetric permalloy in which permalloy layer was deposited on the silicon oxide substrate with aluminum oxide capping layer. The other one is the symmetric permalloy, in which the permalloy layer was sandwiched with two aluminum oxide layers. And this view graph summarizes the thickness dependence of the fundamental magnetic properties and the transport property. And so saturation magnetization and saturation field gradually decreases with decreasing the permalloy layer thickness D. These results suggest the presence of the magnetic lead layer and the perpendicular magnetic anisotropy at the interface. And resistivity gradually increases with decreasing the permalloy layer thickness. This suggests the interface scattering and or the change of the film morphology. Anyway, so interface is different from the back. This is quite natural. And then we did the STFMR measurement for the device with different layer thickness. And this is the result for the asymmetric permalloy with the thickness of 5 nanometer, 3 nanometer, 2 nanometer, and 1.5 nanometer. As you can see, all the device shows a clear STFMR signal, even in the case of the sample with only permalloy layer. And by fitting using this equation, consisting of the Lorentzian and anti-Lorentzian functions, so we obtain the damping-like torque and field-like component. As you can see, all the samples show the VAL. This means a field-like component. However, so damping-like component VL appears with decreasing the permalloy layer thickness. And then we investigated the angular dependence of VAL and VL. So in the case of the asymmetric permalloy, we can nicely fit the experimental data. However, symmetric permalloy, only field-like component is fitted by the equation. Therefore, so field-like torque appears for the both asymmetric permalloy and the symmetric permalloy, and the damping-like torque is observed for the asymmetric permalloy. And by utilizing this technique, we can evaluate the damping-like torque, even in the case of the sample with very thin permalloy layer. And so you can nicely fit the experimental data using the Kittel's equation. And by linear fit of the line width as a function of frequency, we obtain the damping parameter. And the asymmetric permalloy shows a larger damping parameter than that for the symmetric permalloy. Then the enhancement of the damping constant that comes from the inhomogeneity of the magnetic property in asymmetric permalloy. And then here I would like to discuss the main feature of the STFMR. And what is the source, major source of the damping field-like torque? That is mainly LZ field. And so as this is again, I show the field angular dependence of the asymmetric permalloy, and that sign of this angular dependence is completely same as the reference sample of the permalloy platinum by layer. Therefore, we now consider the current flowing at the bottom side of the permalloy that generates the LZ field. That means the imperfection of the structure gives rise to the spatial inhomogeneous current distribution in the permalloy layer. And next is damping-like torque. As I said, the asymmetric permalloy shows a larger damping constant. Therefore, the inhomogeneity of the magnetic properties in the asymmetric permalloy is suggested. And as decreasing the film layer thickness, the spatial change in the z direction becomes 3T inside of the permalloy. This unidirectional variation of the magnetic properties may generate the non-zero spin current via the spin Hall effect in permalloy, and the resultant damping-like torque appears. And also we proposed the toy model to do the semi-quantitative analysis of the self-induced spin orbit torque. And we introduced some parameter C, and by fitting the experimental data by using this equation, and we obtained damping-like torque, total damping-like torque, that is 0.06. This is quite small, quite small. and it is difficult to explain this large spin Hall angle, which was assumed for the spin torque oscillation experiment. And in order to realize such a large spin Hall angle, now we consider non-uniform magnetic structure is probably needed because, as I said, in order to get the damping-like torque, inhomogeneity plays an important role. And then, so if we have the non-uniform magnetic structure, more non-uniform magnetic structure, that may lead to the enhanced spin current generation. Okay, this is a summary of the second half of my today's talk. So in this study, we evaluated the self-induced spin-orbit torque in the permanent single layer by using the STFMR technique. And we discussed the possible sources of the damping-like torque and field-like torque for the permanent single layer. And another important point is, so single layer STFMR method is beneficial to evaluate the magnetic dynamics for very thin ferromagnetic layer because we evaluated the 1.5 nanometer thick permoy by using this STFMR technique. All right, so this is a summary of my today's talk. Thank you very much for your kind attention. And also I would like to thank the collaborators. This work was done in collaboration with several researchers, especially I would like to thank you for the Professor Yonchan Rao, and also Ihama-san and Taniguchi-san. Okay, thank you very much for kind attention.
Thank you, Professor Seiki, for a very nice talk. And now the session is open for questions, so we can take 2 or 3 questions. So any questions from participants?
Well, maybe I can ask a question.
Yeah, please, Wanda.
Yeah, very nice talk, Seki-san. I really enjoyed. For the second part, the Pormalloy, where you saw the self-induced spin orbit torque, or one can call it intrinsic spin pumping, whatever. So you showed the results for taking an asymmetric and symmetric L2O3 or LOX system. If you don't take any LO, just let's say you deposit Pormalloy directly on top of the substrate. So did you check that if that also leads to the self-induced SOT?
Maybe. Yeah, actually, so yeah, problem is if we prepare the sample without an oxide capping layer, maybe the oxidation problem occurs. However, actually, so different interface condition may leads to some damping-like torque, I think.
Okay. All right. Thank you.
Okay. Any other question? Okay, Professor Seki, I have a small question. Okay. In your second this part, that,
yes,
I didn't get exactly that with film thickness. So if I hear correctly, you mentioned that with film thickness, interface scattering is increasing the resistivity. Did I get correctly?
Yes.
Yeah. So, so if you increase the film thickness, then interface. So I am not the expert of this thin film thing, but so I think the interface is similar. Only film thickness is increasing. So how you correlate with this interface, the scattering? Huh?
Sorry, pardon me.
So you have increased the film thickness. So the interface means I consider that interface should be similar. You are only changing the thickness. So
yes.
So,
actually, so there is a 2 passes. One is the bulk contribution, and if the thickness is very thick, that the bulk contribution is remarkable. However, with decreasing the permanent layer thickness, the interface scattering becomes visible, remarkable, and the interface scattering basically generally shows a large interface becomes a scattering center. Therefore, the resistivity increases if we have the remarkable interface scattering. Therefore, we can see this resistivity as a function of the permanent layer thickness and the low thickness region. We can quickly observe the quick increase of the resistivity like this.
Okay, thank you. Thank you. So if there are no questions, then let's thanks to Professor Seki, and we have
There is
a
a Sanjay. There
memento
is a
for
question.
you.
Sanjay, there is a question in the chat
Yeah,
box,
okay.
but I think if Seki-san is available during the break,
Yes.
maybe.
Vedanta-san,
Maybe, yeah, there.
I have one question in the chat box.
Okay.
Thank you. Thank you so much for interesting talk. Did you calculate the orbital and spin contribution in self-induced spin torque? No, we have not evaluated yet. But actually, it is quite difficult to separate the orbital contribution and spin contribution. Mainly, so we just consider the spin contribution.
Okay, Abhishek, please share the screen with the memento. Okay, Sanjay, kindly present it to Professor Seki.
Yeah, so we present this memento from Symposium on Magnetism and Spintronics, National Institute of Science, Education and Research, Bhubaneswar, India. And we take immense pleasure to present memento to Professor Takeshi Seki, Indian Institute for Material Research, Tohoku University, Japan. So thank you, Professor Seki, and this is memento from
so
our
much.
side. Let's clap. Yeah.
Thank you
Great
very
pleasure.
much.
Thank you so much.
So let's move to the next speaker. Our next speaker in this session is Professor Susana Cardoso from INEST-MN, Lisbon, Portugal. So Professor Cardoso presently is Associate Professor at the Physics Department, Instituto Superior Técnico IST, University of Lisbon. She received her PhD degree in physics from University of Lisbon, Portugal in 2002. She was a researcher at IBM and INEST-MN. She has over 260 publications and has an active international cooperation within project and industrial contracts on advanced thin film, microfabrication, process, and sensor. Professor Cardoso was a recipient of Honorable Mention in Scientific Award University de Lisboa in 2016 and 17, and the Magnetic Society of Japan Distinguished Publication in 2014. She was one of the team member awarded as the second finalist for the EU Discuss Prize for Research in 2004. So let's welcome Professor Cardoso for lecture. Please, Professor.
Okay, so good morning, everyone. So I'm very happy to be able to join you today for this conference. Can you hear me well?
Yes.
Yes,
okay.
yes.
Thank you. So I decided to choose some ideas that are key points in our research areas. So we work on materials and integration in applications. And so we have suffered from the highly demanding requirements and highly demanding, exciting growth in the past years, where spintronic sensors and magnetoresistive sensors in particular have been used for many areas. So what happened is that it's impressive how things are made use in real applications, in real world, and are sold as products. But on the other hand, it's also interesting to see that there are still a lot of points that are not solved. And so there is a lot of physics that still needs to be recovered. So I just pick up some of these ideas here to share with you, just to open the discussion. So I decided to point out on noise and extracting signal out of noise. So magnetoresistive sensors have been used for magnetic recording, and this is very well known, and there is no doubt that this was really the trigger point for these technologies. However, there are other applications, and in particular, we have been working a lot on biomedical applications. And in biomedical applications, the challenges are not only to detect small signals coming from nanoparticles or from the body, residual currents, electrical currents, but also the issue is the frequencies at which these signals appear. So for high recording, it's high frequencies. For biomedical, is almost DC, so low frequency. So there is huge span in terms of goals to achieve. And then I'm going to illustrate one example that shows what are the limits, and especially here the key word is to be able to detect picotesla, so very small magnetic fields. And the motivation here is why to go to biomedical at this point. So and what motivated us was to look at the competitors. So that the people working on neurosciences in particular, for example, they work with the neural cells, so and study the synapses and the electrical currents that occur at cellular level. In the nerves, and actually the competitors and the techniques that they use is optical and electrical and chemical. So there is a huge number of tools available for monitoring the neural activity. However, all of them, although they are very well established in the market, each of them have difficulties, and they have problems because of this the large area. They are not scalable. They cannot be so local as they should. And then there is actually the challenge to develop monitoring tools that or sensors that enable to combine some of these detector parameters like electrical parameters and chemical parameters, but also something that is not related with the interface with the media that is being met. And in that case, magnetic is a very interesting characteristics, because magnetism propagates without the need of interface. So electrical requires a connection. So if we have our media and our electrical field, it depends dramatically on the composition of the interface layer between the sensor surface and the biological media that is being monitored, like in this case, cellular. So there is always a layer there that masks the signals. And the signal that is read by for example, in this case, a electrical electrodes, the signal depends on the time, because during time and with the experimental time length, the surface gets covered naturally by a cellular environment that masks the final results. And this means that for example, for electrodes in neurosciences, there is always a 10 micrometer depletion layer that masks the real tissue characteristics. So this means that it's very important and very relevant to develop tools that can be located on the media we want to detect and still do not being affected by the media itself. And magnetism becomes one of these more promising tools. So also magnetic field is a vectorial, so it comes with a reference from the 3D environment, which is something that seems very good when we sell this to the colleagues in neurosciences. But for us working on extracting magnetic fields from the environment, this is actually a challenge. But in fact, there are very good advantages in using magnetoresistive sensors for neurosciences because of the size, the room temperature operation, which is something that is still a good option, and also the low power consumption. This is important because we don't want the sensor to heat, or the probes to be heated and and also we want them to be portable as much as possible. So the big challenge starts with how to read populations of neurons where the electrical signals are triggered from one point to the other. And this is an example of neuronal cells where there is a lot of, so these are cells, nothing magnetic, but the magnetism appears as soon as the electrical simulation starts. As soon as, for example, our eyes see something, there is also a triggering in these cells. So small ionic currents flow every time we do a motion, mechanical activity, eyes, sound, so anything that we are doing. So this means that intrinsically we are not magnetic, but magnetism reveals ourselves as soon as we are alive. And this is the idea, is to be able to measure very small currents that flow on these populations of neurons. There are, fortunately, they are not isolated, so we don't have just one neuron in the body. Normally, there are populations of neurons that are close together. And fortunately, in many occasions, they respond as a cooperative entity. It means that if we have synchronization of the signals, we can have an interesting magnetic field created by this generation of ionic currents. So this is just to make the context and for you to understand what are the challenges here. And the challenges are, if we measure these magnetic fields really near the space where they occur, so inside the brain, they have the estimated fields are of the order of picotesla or even nanotesla for some of those. But however, what are the competitors doing? So the competitors are using the squids, so low temperature measurements, but the squids are an environment machine, and that they can only detect the signals from outside the brain. So typically at 2-3 centimeters, and at that point, so away from the brain, the field is something like 3 centimeters or 2 centimeters. The field is of the order of femtotesla. So it's a huge challenge to have a magnetic sensor replacing the squids to measure femtotesla. But actually, this was the goal initially, was to have femtotesla magnetoresistive sensors. This turns out to be extremely challenging. So the goals are now a little bit more revised, and the goals are to be able to measure picotesla. And this is a very realistic number to provide as a target for the sensitivity exploration in the magnetoresistive sensors. So how important is biomedical applications in the market of magnetoresistive sensors? So there was a paper published, it was a result of a task force that was done a few years ago to identify current and future applications for magnetoresistive sensors, and those cover from electronics and industrial applications, but also we saw that it was a huge market appearing in the past 10 years already, related with bio engineering, with medical, so not usual applications for magnetic sensors, and also for robotics. And this is a very, very interesting area that is really going exploring very, very fast. And the goals of all these applications were not only the small size of magnetic sensors and the price, because the cost is very low at the moment, but also the ability and the promising characteristics to detect ultra low magnetic fields. So this is actually something that is still going. So there is still a lot of work to be done, but a lot of expectations as well. So this is very interesting and very, very exciting for the new researchers starting to work on the area. So not only magnetic recording, this is my motivation when I started working on this in 20 years ago, let's say. But now there are many others. Now I'm not going to go into detail of what are the options in terms of when we talk about magnetoresistive sensors. So at the moment, these 4 families of magnetoresistive sensors work competing with each other in different niche applications or different massive applications. So they are all valid and still actual in the world. I'm going to focus more on the TMR, so tunneling magnetoresistive devices, where we have the maximum voltage output, and this is where we have been exploring recently. So I'm going to highlight in in diagonal, let's say, the key points that are looked at whenever we want to design and optimize magnetic sensors for these challenging applications. So we want definitely at the end, the goals are not only to read low signals, so this means that we want to have a huge sensitivity in these sensors, but what does it mean? So it means that we need to have that, but still maintaining a high spatial resolution, still working at room temperature, still having sensors that are cheap and compatible with the large scale integration with the large wafers for production. Otherwise, the costs will be increasing. And also, we want to have a sensor that is easily tunable from high sensitivity to low sensitivity, so that the market can use them, and we are not just frozen with one product that only works for neurosciences, for example. Nobody wants to work only for one market. So versatility. So the two most common architectures, this is a GMR and this is a TMR, so tunnel magnetic effect. So for the TMR in particular, I'm not going to go into detail. I think you have been seeing several of these stacks where the films with the tens of angstrom are packed in engineering a very complex structure. So we don't have simply an oxide, a tunnel barrier, and two ferromagnetic electrodes. This is a very simple vision. So at the present, we need normally more than 8 targets, different materials in the machine to deposit a full tunnel junction device. We require engineered structures for the reference layer, so where we have a synthetic antiferromagnetic layer here. We want to have a free layer. The free layer is not just a simple ferromagnetic layer that is rotating, so there is here something else. The cap layer, the bottom layer, everything plays a crucial role in the performance of the device. So not only structural attention needs to be done, but also from the magnetic perspective, from the interface perspective, and from the cost perspective. So there is several things to be accounted. This is a well-known and a very solid area of engineer and physics. So normally when a young researcher starts to work in this field, like a master's thesis or a PhD researcher, what they learn immediately is they learn the tools that enable to understand how these structures work. They are not just 1 or 2 layers rotating magnetically under a field. There are several layers that have very well-known interface and cooperative couplings between them. So it's normal to have macromagnetic and analytical models to elaborate the dynamics of these multi-layers, and also experimental results are from the magnetic, in this case it's magnetic behavior measured in VSM, in unpatterned stacks. The experimental results are always compared with simulation, so to refine the models and to be able to have a realistic model for the stack that is ongoing in the lab. And then what is the issue here? We want to build sensors. So if you want to build a sensor, we need to have a linear response. So we don't want to have a linear decay of the resistance as a function of the external field. This is actually the biggest challenge of all. So I would say that it's relatively easy to have a decent or a good tunnel magnetoresistive value. So if we have very good materials in a very good sputtering tool, we can have a reasonable magnetoresistance value. What is difficult here is when we talk with the materials that are the most top chosen for sensors, like MgO tunnel barriers and cobalt iron boron alloys for the ferromagnetic interfaces. Typically, these materials are rich in iron. It means that the crystalline anisotropy is very large, so it's difficult to have the linear range being in a very low magnetic fields. And also it's very difficult to have a good control of this rotation of the free layer at low fields, avoiding high coercivity, avoiding noise and bumps and jumps in the Barkhausen noise, and also these jumps at low fields. So there are several strategies, and I'm going to choose some to illustrate the examples, but you can see more of those examples. So for example, we can have a huge sensor and play with crossed anisotropy. So when the reference layer has induced anisotropy in one direction, and the free layer have forced anisotropy in a perpendicular direction, and this will force a natural 90-degree orientation for these two layers. However, this looks easy in the drawing, but it's very difficult to perform in an experimental stack. So what are the goals here? It's reaching the limits of magnetoresistive sensors. So we have typically magnetoresistive sensors go to few nanotesla. So this is typical to see. We want to extract them down to clear picotesla and eventually to femtotesla. So what is detection of ultra low signals? How do we know that we are measuring something, or how do we know? So a simple way to operate is to place our sensor here in a small coil, and from the coil we can apply this AC current, so that we can tune not only the frequency of the magnetic field that is created inside, but also the intensity of this field. And from this simple apparatus, we just measure the residual resistance of the sensor as a function of frequency. Here, please notice that this frequency are low, so we are less than 100 Hertz. So this is very far away from the frequency levels that are used in magnetic recording, for example, which lies to 1 gigahertz. So here is really low frequencies, and in that case, everything is bad for the plays against electronics, because low frequencies mean that we are picking up everything that is from the environment. For example, we have the 50 Hertz here from the grid power that we need to avoid. And from here, this is a typical signal. So we measure here, we see a lot of oscillations. So how to know this is a signal or the noise? So this is actually the big difficulty here. And we need to understand, if we know the source, and this is the case, we have a setup, we know exactly that we created 32 Hertz field, so we should see a signal here at 32. Okay, good, we have it there. But if I did not tell you that it was a 32 Hertz field, we could think that this was a signal or this was a signal. So it's very difficult to identify clearly where is the signal. Even worse, if we go to lower intensity, the signal here, for example, 32 Hertz, our sensor could not distinguish this signal from the other signals that became noise. So knowing what is signal and what is noise is an art. So we need to have very good eyes, let's say, and this is a big difficulty. So this is how we go. And ideally, we should always go with a ratio between the signal to the noise higher than 1, means that you have a higher signal than the noise. But in the limit, all the calculations, when we estimate this detectivity, the calculations assume that the signal is equal to the noise, because this is at least the limit of the detectivity. And why is low frequency so difficult to understand? If we see the noise spectra for a magnetic metallic device, we see here that for frequency, and this goes to high megahertz and higher than megahertz. So this is in mega. So here is gigahertz. We see that there is a very nice low plateau here at a certain range of frequencies, but unfortunately, biomedical applications require almost DC. So almost DC, we are in this regime here, where we have the so-called 1/f noise. So this is an intrinsic and unavoidable noise source that is proportional to the inverse of the frequency, so 1 over f. So and this is what we see here. So the noise in volts per hertz is proportional to a constant, to the current square, to the resistance square, to the area of the device, but also to the frequency. So we cannot avoid this. We don't have a constant noise. We have a noise that increases if the frequency goes low. And in many cases, for example, for the biomedical and biometric signal parameters, we cannot change the frequency. We cannot modulate the frequency. The frequency is what the body provides. So what we do very simply, we play with the two entities. We have the voltage from one side, or the resistance, and we have a nice transfer curve. We can play with the variation of resistance with the linear range for the delta H, and this gives us the sensitivity or the signal. And on the other hand, we have the voltage noise, and for the noise we have again the 1 over f dependency, and then we go to the thermal. So if we can work on the thermal, perfect, we have the lowest, perfect. And if we cool the sensor down to cryogenic values, perfect, we are always in the thermal, and then also the thermal will reduce down with the temperature. But unfortunately, we are here. So we need to include this as a term here, like here it is, the same that it was in previous slide, depending inversely proportional to the frequency. So at the end, if we play the detectivity limit and we want to calculate it and have it signal to noise ratio equal to 1, so we equal the signal and the noise, and at the end we have this, and we have to work with this. So what have we done in the past 10 years or more maybe, is to try to improve the signal to noise ratio and the sensitivity as much as possible. So decreasing the delta H, the linear range, increase as much as possible the magnetoresistance, so playing with better materials, decreasing the Rouge parameter, so this is an adjust parameter for the noise curves, I will show you later. Increase the area of the sensor, okay, but please remember that we don't want to increase the area because we want small size sensors, otherwise they are useless. And then ideally increase the frequency as well. Good luck, in some cases we cannot increase the frequency. So if we want to play with the materials perspective, from the materials perspective, we want to reduce the linear range, for example. So let's choose one example where we have done a large effort to reduce linear range. And one obvious strategy is to include magnetic flux concentrators. So this will enhance the magnetic fields at the sensor region, so here, and then we just have to add on top of the chip sensor a soft material that concentrates the flux. And this means that here, for example, we can compare a normal transfer curve, so this is the blue curve with a very nice linear response, and as soon as we and this is this case, so a simple sensor, but as soon as we include magnetic flux concentrator, we are enhancing the magnetic field that is visible at the sensor level, and in that case we have a clear gain in sensitivity. So we have a very much sharper response. So the sensitivity goes from 1% per millitesla to 10 times or 30 times higher, better. So this is a strategy that has been used, and this is of course been explored also by us from the local sides in a cross view. What can we see? We can see that this is done by thin film flux concentrator. So normally permalloy with an angle that brings the field as much as possible to the sensor that is buried below the oxide. And then this structure, what we call a tapered flux concentrator, this enables to obtain and to have higher signal to noise ratio, because we are enhancing the sensitivity. So if we look here, some examples where we have the noise level that is decreasing for higher frequencies. So for 30 Hertz, we have a lower noise level, but if we increase the frequency, decrease the frequency, of course, the noise is improving with the 1/f. So, but still, if we compare this with what we have without magnetic flux guides, we see that this is much better. So we have a 10 times gain in terms of detectivity. And if we look here at if we have the detective level plotted now in units of field, so how many picotesla we can detect, we see here that for 100 Hertz, we are already in the 100 of picotesla regime. We could go to much lower. We can go to 1 picotesla, ideally if we extract to megahertz or gigahertz. But unfortunately, we cannot look higher than 100 Hertz. We need to focus here on this region. And still, we are not below picotesla. We are in nanotesla. So this is what we have with this sensor, right? So other strategies. So we have to change all these phase parameters. So increase the area. We don't want to do that, but unfortunately, we should do it as well. So another example is to play. So this is I'm not going I'm not expecting that you understand fully this picture. I'm sorry, this is too crowded slide, but see, this is a zoom very, very clear here, where we have the tunnel junction. So the TMR sensor is here with a large area. So large area because normally the sensors are a few micrometer, and in this case we have hundreds of micrometer square sensor. And if we have that, we can see here again the spectral noise in units of picotesla. You can see that these three curves, they have the sensors with 10 micrometer square. So this is the black curve, and then we have the two color curves with 100 micrometer square. And from those, you can see that you have candidates, good candidates, where you can read 100 picotesla at 10 Hertz. So again, another strategy that could lead to contribute positively to improving the detectivity. And what else can we do? Of course, we can artificially increase the area of the sensors. So we don't want to modify the sensitivity of one sensor, so it should be sharp. If we have a square or a huge sensor, we cannot have a good transfer curve, but we can artificially connect hundreds or millions of several hundreds of sensors in a series configuration. Yes?
You have to last 2 minutes, please.
Okay, perfect. So in this case, we can artificially increase the area, and this enable us to have better sensors. But again, the space counts, and we don't want to have the device area to be more than a few millimeter square. So there are not many options that goes to picotesla, but we are always in nanotesla and below nanotesla if we increase the area. So this is what goes. And another strategy that I would like to finish with this one is we can use the space wisely. So instead of just having one sensor flat in the wafer, why not to have sensors packed vertically? So several hundreds of sensors deposited on top of each other, so that we can gain space in the chip. And also even better, then we can connect several of these vertical sensors in series, so that at the end we have a huge amount of sensors. So here we have 440,000 sensors in the same small area. So this is what we do. And in that case, we can detect definitely few picotesla at room temperature, still playing. This is the real signal that was measured, still occupying the minimum size so much less than 1 millimeter square. So at the end, I'm going to jump to the end just to tell you. Just to show you how this is integrated. We integrate this in needles. For these needles, we can choose, and we want to have the sensor just here in the tip, occupying a minimum place as possible, and then have them tested with the correct electronic interfaces for biomedical. We also have done flexible, and this finish my presentation. Okay, so just to tell where we are now, so playing with the size, shape, and materials to bring the best sensors down to the biomedical devices. Okay, so thank you for your attention. I'm open to questions.
Thank you very much for a very nice talk on sensors. So, it was really a great information for people like me who is not working on a biosensor side. We are working on different kinds of sensor using this magnetoresistance thing. Thank you very much. So now we can take quickly 2-3 questions. So, okay. So Professor Seki raised hands. Please.
Thank you very much. Can you hear me?
Yes, yes.
Thank you very much for a very nice talk. So you showed the GMR sensor. What kind of material did you use?
Okay, so for the GMR sensors, we have used spin valve-like. So we have a copper spacer, and then the cobalt iron and nickel iron electrodes.
I see.
So yeah, so this is what we use. The idea, we always have a pinned layer. So we always
use conventional ferromagnetic materials, right? So
yes, yes.
Something like a Heusler alloy with a high spin polarization, do you have any idea to reduce the noise or increase the sensitivity?
So yeah, that's a very good question. I never worked on those materials, in fact, but definitely they bring advantages, and the biggest advantage is normally these materials can be made amorphous, or in some cases they can be made amorphous, which reduces the noise dramatically for TMR sensors. If we have GMR, even if they are not amorphous, they have higher polarization. So this brings a big signal. What are normally the drawbacks of those materials? They have much higher resistance. So this in some cases is a disadvantage, because they are prone to electrical discharge, and also they create the sensor with a huge resistance. In some cases, it's not easy to reduce the size, because then the resistance gets prohibitive.
All right.
But in terms of signal, definitely they are very promising. Yeah. Okay. But I never use them. My machines are for ferromagnetic and cobalt iron boron. So yeah, but there are some good works on those that are emerging now, especially doped with metals to reduce the resistance.
All right. Okay. Thank you very much.
Thank you. Any other question? Okay, then if there are no questions, then let's thank the speaker, and
thank you.
Ivanka, let's present the memento.
Yeah, thank you so much, Susanna, for this very nice talk.
Okay, so from National Institute of Science, Education and Research, Bhubaneswar, we present memento. So we take immense pleasure in presenting the plaque to Professor Susana Cardoso and in Czech and then Lisbon, Portugal, in appreciation for being a valuable speaker to give lecture on strategic for improvement of signal to noise ratio in spintronic sensor. Thank you very much for great talk.
And thank you so much for this. This conference is amazing. Very good. And I'm very happy to see good friends in life, right?
Yeah. Thank you so much, Susanna. Best wishes. You can stay for some time. Yeah. Thank you.
Okay, sure.
Thank you.
So, okay. So let's go to the second, another lecture, or third lecture of this session. And the title is Homo and Heterometallic Lanthanide Complexes as a Single Ion, Single Molecule Magnets, which will be presented by Professor V. Chandrasekhar from TFR Hyderabad, India. Professor Chandrasekhar currently is Center Director of the Tata Institute of Fundamental Research, Hyderabad. And he received his PhD degree in 1982 from the Indian Institute of Science, Bangalore. He then worked as a postdoctoral research associate at the University of Massachusetts, USA. He was also the director of NICER Bhubaneswar from 2014 to 17. That's very nice. So this institute is holding the conference. He is an elected fellow of all science academies in India and the World Academy of Science, Trieste, Italy. He has been on the editorial board of several journals, including Organometallics and Dalton Transactions. His research work is documented in 360 plus publications. He has been a recipient of several national and international awards, including the Santiswarup Bhatnagar Award and the Friedrich Wilhelm Bessel's Research Award of the Alexander von Humboldt Foundation, Germany. His major research interests are molecular materials, inorganic rings, polymers, main group organometallic chemistry, and polynuclear metal assemblies. So let's welcome Professor Chandrasekhar for his talk. Sir, please.
Yeah. Thank you very much. I hope you can see my screen.
Yes, sir.
Yes.
We can see. Yes.
And thanks a lot, Shubhankar. I mean, I have no business to be in this conference, except that this is Shubhankar's 10th year or probably the 11th year of his lab. And that is why I'm giving, although I am probably the only chemist, and I apologize to you for speaking about chemistry because that's what I do. But congratulations, Shubhankar, for completing 10 wonderful years, the 11th year, and I'm sure that your lab will do and go from strength to strength. And indeed, it's a great pleasure to come back to NICER, even electronically, and to be able to speak to you about this. So my lab works on different aspects, and one of them is on molecular materials to do with magnets, but these are molecular magnets. So because this audience is, I think, mostly from physics, I just will take a couple of minutes to tell you what we are doing in terms of the background of this work. So we work, the single molecule magnets are essentially molecules, and they contain a lot of paramagnetic metal ions. They are completely encapsulated by diamagnetic organic ligands. So whatever magnetic property we are observing is from the molecule, and that is completely from the molecule and nothing else. And the molecules, for example, if I take a simple paramagnetic substance, I put it in a field, the orientation of various spins, now they get oriented. But of course, if I switch off in a regular paramagnetic, they go back to the disoriented state or the randomized state. But in a molecular magnet, they will retain this order for a long time, particularly if the temperature is such that it is above which it gets randomized, but below which it remains in this particular state. So once magnetized, therefore, these molecules can show, can retain the magnetization, and slightly above that temperature, they show slow relaxation of magnetization. The important point is to emphasize that these are, that this particular phenomenon is molecular in origin. Now, there are many types of such compounds. There is this first one, which is a manganese 12 compound, which was discovered several years ago, which is a molecule, a cluster of paramagnetic metal ions that are held together. Then there is, you don't need to have many such ions at all. You actually can have only one of them. And this is shown over here, a simple compound where only one paramagnetic metal ion is there, but the design is such that it can also exhibit magnet type behavior. Or you can have chains, like in a one-dimensional polymer, where you can have, for example, this particular chain has nickel 2 and manganese 3 alternating with each other and are communicating by means of oxide ions. So, and there are also different types of systems. You could have ligands which are organometallic, like, for example, you have this cyclic aromatic systems which are sandwiching the lanthanides, or you can have a simple amide ligands and so on. So there's a plethora of complexes that are available. And in fact, that gives chemists the opportunity to really play around with them. Before I just get into what we have been doing, the first example concerns this manganese 12 complex, which, as you can see here, has manganese 12 oxides, some acetates, and water molecules. So this contains two types of manganese ions. There are manganese ions in the oxidation state 4, which is in the center. and there are manganese ions in oxidation state +3, which are in the periphery. Now, within themselves, they interact ferromagnetically, but between them, that is between the manganese 4 and manganese 3, they interact antiferromagnetically. But still, the overall spin state for a molecule is very large, is 10, and that then gave rise to this phenomenon, which was first christened as the single molecule magnetism, a work famously done by Roberta Sessoli in Italy in collaboration with Gatteschi. And so since then on, the field has really exploded. Particularly where this is a very wonderful interface between chemists, physicists, material scientists, chemists doing the designing of the molecules, and with theoretical understanding coming from both physicists and also experiments being held by physicists. So the requirements for a single molecule magnet, if for example one has to read out a recipe for it, is that it should have a bistable electronic ground state, a large ground state spin, and most importantly, a large uniaxial magnetoanisotropy of the Ising type. Now, if you have this is, for example, can be measured in terms of the zero field splitting parameter D, and this gives rise to a combination of an energy barrier where one of these MS states can be stabilized upon application of a field. And higher the barrier, the magnetization is retained for a longer period of time. The relaxation from one to the other can occur by stepwise thermal sort of a process where the spins can climb up this hill, and that would depend upon the energy barrier, or they can simply quantum tunnel if the conditions are favorable. So this is given in this very beautiful article written by Frank Nies in Faraday Discussions at about a decade back. So this is how the spin states are in the absence of a magnetic field, where you have equally populated spin state in the lowest available MS states, -s and +s states, and there is a barrier that is separating them. You switch on a field, put them in a field, then you find that one of them gets populated. You switch off the field, you find that they are still in one of the states, the population still remains, but there are opportunities for it to equilibrate through the thermal process. In fact, a large number of processes are available. Also, quantum mechanical tunneling is possible. Now, we ourselves, when I was in NISA, along with my students there, we wrote up a comprehensive review article on this entire phenomenon. And we for example, there are several mechanisms that are possible, as shown over here. The green one, essentially a thermal process. Then you have a direct and Raman process. Then you have quantum tunneling mechanism. You have a thermal assisted quantum tunneling, and so on. So these processes are there, and the aim is to see chemically, of course, for the chemist, to see if it is possible to control some of them, to obliterate some of them, to reduce some of them. Okay, now the importance of anisotropy was in fact illustrated by a very, very beautiful paper by Annie Powell from Karlsruhe. Now, what she showed was that in a compound which had a very large spin, but it never showed the single molecule magnet property because it had almost no anisotropy. So the replacement of the central manganese 2 with dysprosium 3, and dysprosium 3 being a lanthanide ion has a large unquenched spin-orbital magnetic coupling, and that is spin-orbital angular momentum, which therefore also reflects in spin-orbit coupling, and therefore you have magnetic anisotropy, and the SMM property is dramatically restored once you replace just one particular ion with dysprosium 3. This kind of emphasizes that there are subtle balance of both the ground state spin and magnetic anisotropy that are needed to prepare such compounds. Now, therefore, once again, to summarize this, a linear increase of just the spin does not lead to an increase in the U effective, which is the energy barrier that is separating these two states. And in fact, it has been shown theoretically that ferromagnetic exchange between ions leads to a zero field splitting parameter, which is much smaller than the corresponding single ion. Therefore, the conclusion that currently is available is that single ion anisotropy is a very, very important criteria in the design of SMMs. Okay. Now, I hope that with this background, let me take you to some chemistry. Now, if you are, for example, looking forward to implement these ideas in preparing compounds which can exhibit some of these properties, what would you do? So one of the strategies is, can you prepare compounds which have large number of transition metal ions, so that the collection of them hopefully can lead to a large ground state spin. And hopefully the structural parameters you can incorporate in them also will introduce anisotropy. The other strategy is perhaps if the first one is very difficult to do it, then you can have a combination of a 3D metal ion, that is like for example a transition metal ion in the first row transition metal ion, and a 4F metal ion, which is a lanthanide metal ion. Combine them in a possible strategy and use the fact that many lanthanide ions have this unquenched orbital angular momentum, and utilize this in the construction of a compound where anisotropy is present. Or you can also have homometallic lanthanide complexes. So I'll just show you how do we do this. Now, this is generally done by this very powerful synthetic technique, which is coordination chemistry. So coordination chemistry is a very old technique. And in fact, Alfred Werner, the famous Swiss chemist who systematized this, got the Nobel Prize as way back as 1913. But this technique is now actually is being reinvented for the discovery of number of molecular materials. Essentially, what it contains is you have metal starting materials, you have organic ligands, you combine them, and you can prepare molecules or in fact even one-dimensional, two-dimensional, or three-dimensional materials of your choice, depending upon how you manage to get this interaction done through the process called coordination. So here I'll talk to you first about 3D 4F complexes. So what you need to do is develop a ligand, and this ligand can selectively bind to both the 3D metal ion and the 4F metal ion. You don't want a system, you don't want a situation where you're not able to do this selectively. So your ligand itself should have the pockets so developed that this particular pocket will selectively pick up a transition metal ion, and another pocket would pick up a lanthanide metal ion, and there should be connection between them, through some atoms such as oxide or sulfide or something like that. So with that sort of a knowledge, about a decade back, in fact, we were not working in molecular materials at that time. So a student of mine who was working on this system for some other purpose thought that this ligand may be quite interesting for the design of such systems. So here you have these nitrogens that are in blue are coordination sites that can prefer transition metal, and the ones that are in red can prefer both transition metal and lanthanides. And in fact, the nitrogens also can bind to lanthanides, but given an opportunity of selecting, they would prefer to have a transition metal. So with that, we prepared our sort of a first foray into this, and you can see this very beautiful trinuclear compound where you have on either end in this light blue, you have this cobalt 2 ions, and in the center you have the gadolinium, and the connection between the cobalt and the gadolinium is brought by these phenolate oxygens, and therefore you have an electronic communication between the central gadolinium and the cobalt. And of course, you can have by detailed crystallography, one could analyze the structure of this. The gadolinium has a coordination number of 12 with an approximate icosahedral arrangement around it. The cobalt has an approximate octahedral arrangement around it with 3 nitrogens and 3 oxygens. And this molecule was shown to be a very, very good candidate, and in fact showed ideal single molecule magnet behavior. With that, we thought, does it mean we simply can prepare other trinuclear systems, and would they, for example, behave similarly? So we thought, okay, let us change the ligand system completely, but with the objective of creating trinuclear systems. So here is a ligand which is totally different. The previous one was phosphorus supported. Here is simply an organic ligand, but has features that a chemist would easily recognize. So for example, you have a central phenolate, you have coordination sites in the form of nitrogen, and peripheral hydroxyl groups which can be deprotonated. And to cut the long story short, we can prepare several trinuclear complexes exactly similar to what we had shown in the last instance. So you have a cobalt, you have a lanthanide, and you have a cobalt. And the cobalt and the lanthanide are interacting with the oxides, that is the phenolate oxygen that are present. This is a deprotonated, derived from this phenol, which is deprotonated, and so that is binding this cobalt and lanthanide. We looked at the structure of this, and of course we noticed that there are 2 4-membered rings. There is one on this half and other in this half. And these 2 are actually in a somewhat in a perpendicular to each other, not perfectly, but approximately perpendicular to each other, as you can see over here. So you have this is like a twisted planar arrangement of the 4-membered rings, but they are approximately perpendicular to each other. Now that already sent off some signals to us whether the local anisotropy axis, would they be functioning together or would they be working against each other? And in fact, when we measured the magnetic measurements, and in fact, typically one of the ways you determine whether the molecule that you have is a single molecule magnet or not is through these AC susceptibility measurements as a function of temperature, and you look out for signals maxima in the chi double prime versus T plots. And we find that there are, while there is a variation, we don't see a very good maxima in these plots, and which kind of indicated that these are not good candidates, or they're not good single molecule magnets. And even in the presence of small fields, because typically what happens is when we do this AC susceptibility measurements at zero field, there is a possibility of quantum tunneling, and that might obliterate any property of single molecule magnet behavior. So we did it in small fields, which should allow that such quantum tunneling is minimized, but it doesn't pay any dividend at all. But we wanted to check it. Is cobalt the only case that is giving this particular property? Or if I put other types of paramagnetic metal ions, like for example, nickel over here. So we did with nickel, the central lanthanide is still gadolinium, terbium, dysprosium, holmium. And in this case, also the structure is perfectly reproducible. You have a linear arrangement of nickel, dysprosium, and nickel. And again, the structure, as you can see, the two four-membered rings are perpendicular to each other. And therefore, we anticipated that the property should be similar, and indeed they are. So which means that we hypothesized that while there are factors, that is, we have injected everything properly into this molecule, it should contain anisotropy, it should contain spin. It simply is happening that the local anisotropy axis of the two four-membered rings are not working in unison, but they are working against each other. And therefore we said, okay, how can we solve this problem to this point? We said, okay, let us remove the paramagnetic metal ion from the periphery, and let's put a diamagnetic metal ion. Then this entire process of local magnetic anisotropy axis completely vanishes. The entire anisotropy would come from the central lanthanide ion, and therefore there would be no question of interference. So what we did was we removed using the same ligand, we got rid of the paramagnetic metal ions and put, for example, magnesium or zinc in their +2 oxidation states. And of course, they are diamagnetic, and prepared analogous set of complexes. And now you can see this restoration of this beautiful behavior of a single molecule magnet behavior, which immediately tells you that this particular compound has the SMM property has been restored in these molecules. And you can also measure the U effective, that is the energy barrier between these systems by means of, you see, for example, it is 70 K, and in another situation it is 67 K, and so on. I mean, those numbers are not so significant or important for us. The principle of the design is important, that the anisotropy therefore is extremely important, and it's important to align the anisotropy properly. Okay, this we took pains to see that this is demonstrated in other systems as well. So for example, in the previous case, we had the magnesium 2 or zinc 2 as a diamagnetic metal ions. So we thought, let us replace it with cobalt 3. So cobalt in an oxidation state 3 in a strong field ligand environment is diamagnetic. And so we put a strong field ligand environment and had cobalt 3 on either side of dysprosium. So we knew that cobalt was in a +3 oxidation state, and cobalt 3 is a D6 system, therefore it is diamagnetic, and therefore does not contribute anything to the magnetism. The central dysprosium is one that contributes completely to the magnetism, and indeed, as we had previously shown, this also shows very nice single molecule magnet behavior with the U effective being about 88 K. So these principles allowed us to kind of, in fact, theorize and write about the impact somewhat counterintuitively. Therefore, you would think that diamagnetic metal ions actually have a beneficial effect in the overall magnetic behavior of compounds that you want to aim to prepare as molecular magnets. And we wrote up a perspective in Dalton Transactions in 2018. We are not the only people who have worked on this. Maheshwaran from IIT Bombay has also shown some very dramatic effect in these two compounds, where, for example, here there is just the dysprosium, he has a zinc ion that is now attached to it, and the U effective increases considerably. And we ourselves, as I told you, we shown this in a couple of years before that. And then a couple of years later, Colegio from the University of Granada has also shown that this can be implemented in systems that have cobalt and yttrium, where it's a reverse now. It's cobalt that is paramagnetic and yttrium that is diamagnetic. So we wanted to look at this particular system. So this was published later than ours, but using the same sort of a principle. So we thought instead of trinuclear compounds, can we have dinuclear compounds where one of them is diamagnetic, the other is paramagnetic. And this was what Colegio had reported. And so we thought, can we do this? Of course, using our ligand system. So we were working on this ferrocene supported ligand systems over here that allowed us to prepare selectively dinuclear compounds with a 3D and a 4F metal ion bridged by the phenolate. So this sort of an experience allowed us to very recently carry out this work, where we had cobalt-2 as the one that supplies the paramagnetism as well as the anisotropy, and yttrium simply a diamagnetic metal ion. So, you know, this ligand was built on this ferrocene scaffold by techniques that are quite commonplace in chemistry. And so you build this multi-site coordination ligand, where one of these sites labeled P1 is selective to transition metals, and the site P2 is selective to lanthanides, and the central OH attached to the aromatic ring upon deprotonation will serve to connect these two. So that is essentially what happens here. So you have the cobalt 2, you have the yttrium 3, and the central phenolate connects them very nicely. So you have a set of complexes where yttrium, which is a diamagnetic species, has no role except to support the cobalt in terms of the influence it has on the oxide in terms of the orbitals on cobalt. So the, of course, the molecular structures were determined very precisely. We knew what was the geometry around cobalt-2, what was the geometry around yttrium-3, and the connection between them, how they are connected to each other. In addition to the phenolates, we also have the carboxylates that are bridging these two centers. And then we studied their magnetism, and you can see very beautiful, very ideal sort of a behavior that is elicited from these compounds in the chi double prime versus nu or chi double prime versus t plots. And you can see that the AC frequency can be varied quite large, up to almost 10,000 hertz. And you can see the maxima that is obtained, and you can obtain the parameters in terms of the U effective and so on. Okay, now I will shift the gears. And in the time that is available probably for another 10 minutes or so, I will focus on just compounds which only have lanthanides. And this, in fact, was a review that we wrote up a couple of years back in the Journal of Magnetism and Magnetic Materials on pentagonal bipyramidal lanthanide complexes. So this work is based on this very seminal work carried out by Chibutaru, who is a famous theoretician in Belgium. And so he predicted that there is a correlation between the crystal field around the metal ion and the U effective. And what he predicted for hypothetical compounds, where on dysprosium, he varied the fluorides ranging from 1 to 12, and found out that when the coordination number is 12, that is when the geometry is linear, you have the opportunity of generating the largest U effective values. Now, of course, such a linear compound has not yet been prepared. It is extremely difficult to prepare such compounds. What you can prepare, excuse me, are pseudo-linear compounds. So pseudo-linear compounds are where the ligand field in one particular direction is very strong, and in the other direction, let us say in the XY plane, it's quite weak. So for practical purposes, the behavior that you are obtaining is like what you see in a linear complex, not quite, of course, they're not linear, but because the ligand field in the equatorial direction here in the XY plane is completely weak, and only in the axial field you have strong field, it might be considered similar to mimicking a linear compound. So such compounds are known in the literature, and in fact some very nice examples are known, including one from my colleague Dr. Murugavel from the Indian Institute of Technology, Bombay, and showing this particular principle. So we were looking at similar examples also very simultaneously, and had a collaboration with Jean-Pascal Sartre in Toulouse in France. And we were intrigued by the possibility of creating a ligand platform that fixes the metal in a pentagonal bipyramidal geometry. So this is the scheme of how we made this particular ligand. You can, even if you do not understand the nuances of it, it really doesn't matter. You can see that all of these ligand atoms that are there, like nitrogens and oxygens, they're all directed towards the center of that particular motif. And therefore, the chances of it providing pentagonal planar coordination environment around lanthanide are dramatically increased, and that is basically what you find. So you have a lanthanide with a pentagonal plane, and in the axial site you have two chlorides. So we looked at this compound A, whether it is really pentagonal bipyramid, and you can see over here with dysprosium and terbium. These are pictures that are obtained from the single crystal diffraction studies where the molecular structure were obtained. So it's a pentagonal bipyramid, and also from theoretical shape analysis, you can figure out that they're very regular, nearly regular pentagonal bipyramid geometry around the dysprosium and the terbium centers. And then we looked at the magnetic measurements, and you can see that as the characteristic of this single molecule magnet behavior, as the frequency increases, the maxima shifts towards higher temperatures as is anticipated. And you can do one more thing, and this is what you do is you do a trick called dilution. That is to find out if the observed magnetic phenomenon is really from the molecule and not a collective behavior. What you do is you statistically enable this by diluting it in exactly isostructural complex, but where the metal ion is diamagnetic. So for example, we have yttrium, a complex which is exactly has the same structure, and then it is present in 90% excess compared to the dysprosium. So there is no statistical probability of a dysprosium seeing another dysprosium neighbor, and such a sample you measure again to kind of reaffirm that the property that you're seeing is molecular, and it is very beautifully seen, and you see the U effective, a good U effective value being drawn. This also gives us great opportunity because we can keep the entire environment in the equatorial plane constant and change the axial ligands one by one. So we had chlorides, so we replaced one of the chlorides with a phosphine oxide, which is known to be a very strong binder to lanthanide. In fact, if you are aware about the lanthanide and actinide chemistry, the separation of some of these nuclear isotopes in nuclear industry is carried out with the help of these phosphine oxides, which bind with different stability constants to different actinide elements. So this we have been able to prepare both with one chloride has been replaced by a phosphine oxide, and then that we establish their molecular structures again. You can see that this angle, which is the axial angle over here, is about 170 degrees. The ideal angle is 180 degrees, which is obtained in this particular compound, 178 degrees. So it is as perfect a pentagonal bipyramid as you can obtain, and you can obtain the magnetic properties from the magnetic studies. You can see very beautiful curves in illustrating the principle of this that is validated in terms of the fact that if you are able to prepare pseudo linear complexes which have very strong crystal field in the axial direction, then you have a good chance of having this property. Okay, then we also looked at other complexes, but this is really kind of repeating the same thing. So the principle was known to us, and we've tried to establish it in various other situations. So almost I'm near the end of my talk. And most recently, for example, we tried to illustrate this with examples where we have two such pentagonal bipyramidal systems as shown over here by a different ligand design, and where there are two dysprosiums in pentagonal bipyramid. There is again one with in an unsymmetric sort of a coordination environment. As you can see, this particular lanthanide has an azide, whereas this one has a methanol that is binding to it. And so these results kind of validate the hypothesis that we began with, and we are proceeding in this direction to see how we can modify the ligand to extract the properties that are as close to ideal as possible. So with that, I kind of give you a summary. So we are synthetic chemists and looking forward to utilize our synthetic sort of strength in preparing molecular materials. And I've shown you today how we can use that for preparing 3D 4F and 4F complexes. And the trend is really how you can design appropriate ligands for the creation of such molecules. And in this particular instance, how do you, for example, maximize the anisotropy? And it appears from the studies from our lab and of course across the world that mononuclear single molecule magnets or single ion magnets hold the largest promise. Before I close, I should thank all the people who have worked. And I must mention NISER here. Pankaj Kalita was a PhD student from NISER who joined me when almost immediately when I joined NISER. But since I could not stay completely in NISER and came to Hyderabad, he moved with me in Hyderabad. And then there are other colleagues who worked at IIT Kanpur, at NISER and at Hyderabad, and many other colleagues who have collaborated with me, like Jean-Pascal Sutter, Fabrice Pointelet from France, and for theoretical studies, Gopalan Rajaraman from IIT Bombay, and Saurabh Kumar Singh from IIT Hyderabad, and the institutes I was associated with, Kanpur, NISER, Bhubaneswar, TIFR Hyderabad for their support, and funding agency SCRB for its support. Thank you very much.
Thank you very much, sir, for a nice talk and giving us flavor for us. It's a new field of something, and so now session is open for questions, so we can take few questions. Okay. So, sir, I have one question.
Yeah.
So the structure and the environment which you were showing around this ion. So this structure, which technique do you use?
Single crystal X-ray diffraction.
Okay. So the next question is around that. So this gives you the long range ordering. So single crystal diffraction. So do you think that whether some local ordering may also affect the properties of these magnets?
No, this doesn't give the single crystal gives you precisely what the structure is, molecular structure is. It doesn't give you the magnetic ordering that you have to obtain, for example, by neutron diffraction or something. It just gives you how the atoms are organized and in terms of their distances, where they are, and so on.
So basically, you can get precise these all distances.
You can get exactly precisely the bond distances, bond lengths, bond angles, and all that.
Okay, thank you. So okay, so someone raised hand, Mahendran. Yeah, please.
Thanks, Professor Chandrasekhar. I am Mahendran from National Institute of Singapore. I'm wondering whether the ESR-like studies at higher frequencies were done on this material.
Yeah.
And so, what's the new information you get?
I mean, it is true. One can, for example, for the determination, particularly I mentioned about the zero field splitting, those parameters are much more accurately obtained if one does high field EPR studies. Now, we ourselves haven't carried them out because we did not have the ideal systems, but we are not averse to doing it once we get the ideal candidates for doing it. Yes, that's a very good technique to do.
Okay, thanks. I will contact you separately.
Yeah, sure.
Thanks very much.
So any other question?
Oh, maybe I can ask a short question. I think I have asked to Professor Chandrasekhar before on similar question. Towards end, when you showed this AC susceptibility, you see like a frequency dispersion. Was it fitted to the critical power law to check if it is showing some kind of glassiness?
No, okay. So this is, of course, an issue that is people do get, I won't say confused, but because spin glasses also show similar type of a behavior, therefore this question does arise. But the answer, I mean, we haven't done it because it's so obvious in the field that nobody would ask us, because these are molecules. The question of a spin glass would arise where you have magnetic movements that are dispersed in a lattice, and therefore they are not able to either reconcile between the various magnetic domains, the movements that are present, and therefore that becomes quite important there. So the short answer is no, we have not done that because it is kind of established in the field that these are molecules, and therefore they do not need that structure.
Yes, but maybe I think we have discussed this before probably, but maybe still there is a long range interaction can happen from one molecule to the other.
Yes,
because there are like many oxide, maybe superexcision interaction or other interactions can come into play.
Yeah,
this may still lead to some interacting regime.
Correct. But the thing is that all of these are surrounded. You're right. That's always a worry that is there. But all of the metal ions are surrounded by an enormous sheath of organic ligands which are diamagnetic. So the possibility, therefore, of one metal ion of one molecule interacting with the other one is kind of minimized by the ligand design.
Okay.
Yeah, but I mean, what you're saying is in principle correct. That should be done. But because of this, therefore, people kind of think that not necessary. That's all. But yeah, you're right.
Okay. Thank you. Very nice talk. I really enjoyed again.
Thanks a lot, Shubhankar. And once again, congratulations to you for all your achievements, and wishing to see you do much more and do fantastic things.
Okay, so there are no more questions. So let's thanks to Professor Chandrasekhar, and let's present the memento. Okay, so on the behalf of Symposium on Magnetism and Spintronics from NICER Bhubaneswar, it's take immense pleasure in presenting the plaque to Professor V. Chandrasekhar from TFR Hyderabad in appreciation for being a valuable speaker to give lecture on homo and heterometallic electronic complexes as a single and single molecule magnets. So thank you, sir.
Thank you. Thanks a lot.
Yeah, I mean, I just want to say, although he has moved to Hyderabad, but it is still felt that he's here. So he's one of us.
Thank
so
you.
thank you, sir. Thank you so much.
Thank you.
Yeah.
So let's move to another talk of the day. So our next speaker is Professor J. Raut Chelwane from DMRL Hyderabad. So Professor Chelwane, he is scientist at Advanced Magnetic Group at DMRL Hyderabad. He received his PhD from Indian Institute of Technology, Madras, and he was awarded Young Scientist from Andhra Pradesh Academy of Sciences in 2012 and DRDO Laboratory Scientist of the Year in 2010. He is a guest editor in various reputed journals like Journal of Magnetism and Magnetic Materials, FICCAB, Journal of Superconductivity and Novel Magnetism. He has over 125 publications, and his major research interests are on magnetostrictive thin films, design and fabrication of magnetoelectric based magnetic field sensor. So let's welcome the speaker. So Professor Chelwane, it's over to you.
Good evening, everyone. I thank Shubhankar for giving this opportunity to present our work. And I also take this opportunity to congratulate Shubhankar for successfully completing 11 years, I suppose, like with very good academic research and very good publications. Okay. So with this one today, I would like to present the work which I am carrying out at DMRL Hyderabad. Basically, being a defense lab, our main motto is to work for defense systems, develop materials, develop devices, develop systems required for defense. So the material program which I am presenting today, basically on the magnetostrictive material, is also one among them. When one of our sister laboratories, Naval Physical Oceanographic Laboratory, Kochi, was demanded materials for development of sonar transducers, we have taken up this material program. So with this one, like I will present my work. Okay, so let me give a brief introduction first of all to
Professor Chelwane, sorry to disturb you. Can you make a full screen?
Yeah, it's in full screen. Already
Okay.
it's in full screen.
No, it is not in full screen.
One second.
No, Jack, did you say, when you share your screen, did you share the whole screen or only the PPT?
Whole screen, yes, complete.
Then maybe you go to the presentation mode.
Yeah.
1 second.
So on right, yeah, presentation from beginning.
No, just 1 second. This
No,
is
at
the
downside, at right side.
yes.
Yeah.
This is still like my screen is showing a full screen. I don't know.
Can you please stop sharing and share again?
Okay, 1 second. Yeah.
And when you share, please share the full screen. You will see many windows. You
Yeah,
please
yeah, 1
share
second.
the full screen. Now you please go in the presentation mode.
Still.
At bottom right corner.
Yeah. No, is this okay now?
No, we don't see the full screen. I think, okay, at least you can do one thing, this view on the left side, you see the number of slides that you can close.
Just
and just go ahead. Like
key.
Yeah, 1 second. 1 second.
You may press the F5 key. Maybe it works.
1 second. I'll close this one. I press the F5. Is it okay?
Yeah, it's not full screen, but I think it is okay, Sanjay.
Yeah, we can.
Okay, please continue.
Okay.
Thank you.
Okay. Sorry for the trouble. Okay. So as I told you, let me give you a brief introduction about this magnetostriction, and I'll proceed what are the work we have carried out at DMR. Okay. So basically, magnetostriction is defined as the change in the dimension of a ferromagnetic material when you apply an external magnetic field. For example, if you have a magnetostrictive material, any ferromagnetic material with the length L, and if you apply a magnetic field to that one, the length of the material either increases or it decreases. Okay, the increase or the decrease, that's basically the magnetostrictive strain, is defined as magnetostriction, and it is given by the formula change in length by the original length. However, if you take the same material in the form of a thin film, since the film is well adhered with the substrate, the film cannot come out of the substrate when you apply a magnetic field. So what happens is, the film substrate assembly bends. And again, in magnetostrictive material, we have two kinds. One is the positive and the other is a negative. Positive, I mean that there is an expansion of the material, and negative, I mean there is a contraction of the material. So similarly, when you consider in the form of a thin film form, the positive magnetostrictive material bends in the downward direction and the negative material bends in the upward direction. However, irrespective of whether it is positive or negative, the change in the magnetostriction is something like this. It increases and then it saturates at some peaks. So this is very similar to how the magnetization curve looks. So the inverse of magnetostriction is also true. Like the basic magnetostriction, the increase or decrease in the length is also called as Joule effect, and the inverse or reciprocal of this Joule effect is also true. That means there is a change in the susceptibility or the permeability of a material when you are subjected to a mechanical stress. That is, when you give a mechanical stress to the material, the magnetization state of the material is getting changed. Okay? So this effect is called Villari effect. So there are several aspects or the contributions or the manifestations of the magnetostriction. As I told you, the first is the direct and the second will be the inverse effect. The first one, as I mentioned, that the increase or decrease, and the inverse effect is the change in the magnetization due to the applied stress. The second one is the delta E effect. See, whenever there is a change in the dimension, the Young's modulus of the material is also getting changed. That means the magnetoelastic contribution coming because of the magnetic anisotropy is called the delta E effect. And similarly, the magnetically induced changes causes the change in the elasticity of the material. So this is the inverse effect. The third one is the Weidmann effect. In the Weidmann effect, a torque-induced helical anisotropy. When you apply a magnetic field, there is a torque happening in the material. And the opposite one is called the Maitucci effect, where you have a helical anisotropy and EMF is induced with a torque. The fourth one is the magneto-volume effect, in which the volume of the material is remaining unchanged. Okay, so or the volume change due to the magnetization.
Chelvane, sorry to disturb you.
Yeah,
the slides are not changing. We are still on the first slide.
I don't know, like I'm able to, shall I make a new share once again?
I think, Jack, when you are sharing, in the beginning, when you start to share the screen, let's say in your computer, there are multiple windows are open.
Yeah, okay.
Zoom asks which window you want to share. Sometimes you just share, let's say, the PPT window.
No, I have only one Windows bunker. I don't have any window. That's what I closed all the windows. Okay, so I have only one window. What I'll do is
okay, you don't need to close, but when you want to share, that time you need to choose the full screen. And once you choose the full screen and then you maximize the PPT, then automatically that should come.
If you're facing problem, then you can also email us the presentation. We can.
Yeah. So
if possible, you can email. Then we can change.
Okay, I'll email it.
Jack, just email me.
Yeah.
And I will play it for you.
Okay.
Yeah. Sorry, friends. We'll just take 1 minute. Did you send me, Jack? I think he's out. Oh, he's there. Hello, Jack. Jack, can you hear me?
Subhankar, you may call in his mobile if possible.
Yeah, I'm calling him because otherwise we can start X's talk.
Yes,
and come back to Jack maybe after half an hour.
Just confirm over phone once. Or should we go for the next talk?
His phone is also not reachable.
Oh, then let's go for the next talk and then we can come back again.
Yeah. So Ixi, his phone is not reachable.
Yes. Hello, Subhankar.
Hello, Ixi.
Can you see me? Can you hear me? I don't know. I also want to check the system because you can hear me. Yes.
Okay. So should we start your talk? Anyway, it's already 4 o'clock, so we are already delayed by half an hour, so it just fits.
Yeah, fine. I'm ready. Yes.
Okay, so then please start the talk, Ixi. Sanjay.
Okay, let's also make a check because I do not know if my system works or not. Okay, so let me see. First, let's go to sharing. Okay.
Yes.
Sharing screen to my PPT. Yes.
Yeah.
Mm-hmm.
When I go full screen, can you see that?
Yes.
Okay. So can you see the change from the laser point?
Yes. And can you change to next slide?
You see
yes,
that?
It's working. It's working.
Okay.
It's working fine.
Okay, then technically fine. Yes.
Okay. So let's move to the next lecture. So So it will be given by Dr. Ixi Su from JCNS Garching, Germany. So Dr. Shu is currently the group leader at Quantum Phenomena Group, MLZ Garching. He has received his PhD in experimental condensed matter physics from Durham University, UK in 1999. He also have worked as a postdoctoral researcher fellow at Hazy Lab DESY and Hamburg University and at Institute of Solid State Research IFF, Forschungszentrum Zurich. He has over 100 publications in the international reputed journal, including Nature Physics, Nature Communication, PRL, and other physical review journals. His major research interests are neutron and synchrotron radiation X-ray scattering studies of topological quantum materials, strongly correlated electron systems, highly frustrated magnets, and unconventional superconductors. So let's welcome Professor Shu and hear his talk. So Professor Su, it's over to you, please.
So thank you very much for your very kind introduction. And also, Shubhankar, thank you so much for giving me this opportunity to present our recent work. Okay, I think for last 2 days has been a great pleasure for me to really, to be interact with the Indian community in Magnetism, Spintronics. Really, I'm deeply impressed by this fantastic work. Okay, so today I will try to give you a introduction about our recent, let's say, endeavor about this neutron scattering from correlated topological materials. Okay, let me see. This will be my talk outline. So first, I will. Okay, I do not know. Okay, how the audience. So I think most from Spintronics, I will give you a little bit general context and introduction about why topology and the correlations are important for the quantum material research. Okay, then I will present three of our recent studies. Okay, so you can see here. First study, I will show this magnetic Dirac semi-metal. Okay, second, I will present our just recent experimental realization of topological Magellan insulator in two-dimensional van der Waals ferromagnet. Okay, the fourth part actually was not planned initially, but because I saw there is a large spintronic community. Okay, I also would like to show, based on one of our collaborations, this studies of synthetic antiferromagnetic superlattice, where we found a solid-mediated magnetic reversal mechanism. That I think it's okay. Of course, before I give my talk, I would like to thank a lot of people because all those results showing today were exclusively done by neutron scattering. Okay, different neutron scattering technique. So of course we have involvement from many colleagues at different neutron centers. But I would first particularly thank the three persons. Okay, Feng Zhu and Xiao Wang. Okay, in my group. Okay, they are now formal members now. Feng Zhu is now back in China. Xiao Wang is Feng was my former postdoc. Xiao Wang was my former student. She's now in University of Cologne. Also, I would also like to particularly point out, since I did this synthetic antiferromagnet, Ke Xuan Zhang. So she's from group of Wenbing Wu in University of Science and Technology of China. So in order to investigate this system by polarized neutron reflectivity, she spent 1 year as an exchange student with me in Garching in a very difficult time in the pandemic time. But I mean, I'm very glad that finally the things worked out. Okay, I will present that to you. Okay, of course, a lot of I also would like to point out particularly a theory group from the Stefan Bluger's group in the Peter Grunberger really helped us a lot to for the interpretation of the topological Magellan data. And yeah, you can see I cannot really name everyone, but I'm really grateful for all the help, for all the support I received from my co-workers and collaborators. Okay, so now let's go to the general context. Okay, so here I try to list the previous 4 times of the Europhysics prize. Okay, starting from 2010 to 2016. In my personal opinion, these 4 prizes, I think it's just a perfect, let's say, summary of the quantum material. Okay, for instance, 2010, this is a discovery of the quantum spin Hall effect topological insulator. This really opened the door basically for the talk I'm going to give today. And 2012, this is about magnetic monopole in spin ice. This is yesterday, Professor Sama has given a fantastic introduction along this line. This is down to the research about spin ice, quantum spin ice, and into quantum spin liquid. Okay, also we have seen a lot of talks on the heat structure, because this basically paves the way for the studies of emergent electronic state oxide interfaces. Then magnetic skirmions. This is again a topological phenomenon in real space. Yeah, this I think also was shown by Professor Sama yesterday. Okay, so why we study quantum material? Apparently, because as he mentioned yesterday, because this is internal computing degree freedom can be easily influenced by the external perturbations. Okay, therefore you could really use this material to explore or create these emerging functionalities. Okay, for instance, like those new direction with topological electronics or topological spintronics, botronics. Okay, particularly quantum computing. I would like emphasize here a little bit because there is a huge drive in Germany, I think all over the world, about the creation of the, let's say, the new generation quantum computers. Okay, this was demonstrated, for instance, quantum supremacy by Google in their 54 superconducting qubit-based quantum computer 2 years ago. But of course, those computer has a big problem, because the big problem is they have to be cooled in a very low temperature. Okay, because, and the second is the coherent is very short time. Okay, short life. Therefore, you really, for the real, let's say, the long-term future would have like decoherent free this topological quantum computing. For instance, you could use in the anionic qubit. Okay, that will keep long time. Also, perhaps we could find this kind of anions in the quantum materials, which could survive at a room temperature. Okay, that would be, of course, absolutely our dream. But let's hope one day we could be achieved. Exactly, this is why we have to study quantum materials. Okay, now I don't know what is background. Maybe I give you just a little show about this very essence concept topology. Okay, you can see here. Okay, this mark can be changed in forms, deformed into a, let's say, easily into a donut. Okay, but I mean, you cannot change, for example, from this. In Germany, we call this Berliner or muffin, whatever. You cannot change between them or between this bretzel. Okay, this is also commonly with German food. Okay, between these two. Why? Because this three object has different topological invariant. Okay, here this topological invariant basically is number of holes. Therefore, this we call topological protective phases are very stable. Okay, are not subject to any perturbations. This is of course this topological invariant mathematically can be expanded to many systems. You could, for instance, for magnetic skirmions, you could introduce Vandy numbers. Okay, for topological, let's say, band structure, you can introduce Chern numbers. But all are sharing basically the same essence. Okay, that is topologically protective phases. Yeah, there is actually, you know, as I showed, since the discovery of the topological insulator is about 20 a decade ago. Now there actually already formed a new paradigm for this, you know, band structure topology. What basically you can say is, okay, I want to perhaps quickly, please remind me time, please go through here. Okay, in the electronic band structure, we know that you have gap, that is conventional insulator. When the gap is closed, you can have the semi-metal. But I mean, for those topological systems, often you have the single band inversion here. Okay, this blue band is valence band, conduction band. Then in the Fermi surface, you form kind of the Lola lines. Okay, if the system has a strong spin orbit coupling, what would happen when the spin orbit coupling is really strong? It would open a gap in the Fermi surface. Okay, then topological protection starts to appear. So you could have this topological edge state, what we call surface DR cone for the three-dimensional case formed. If you look at the surface bark correspondence, you could see in the bark, you have a gapped band structure, just like conventional insulator. And on the surface, you have this Dirac cone, but there is no gap. So this is actually the topological insulator. Another case is you may have spin-orbit coupling, but this is not sufficient enough to open a gap. But nonetheless, this still could lift the degeneracy in the Fermi surface for this load rings. Okay, then you could have this so-called, for instance, if the band dispersion is linear dispersing band, you could have Dirac points near Fermi surface. Even in some case, for instance, if the system has no inversion symmetry, or if you have this time reversal symmetry breaking, you could form even the surface Fermi arc, render essentially the kind of wire semi-metal. Okay, you could also see the difference between the, for instance, what I showed this Dirac semi-metal, wire semi-metal. Okay, Dirac semi-metal has a rotation symmetry, but wire semi-metal you have no rotation symmetry, but you have this wire point. Red and the blue point on the surface has different chirality. Okay, for topological insulator, why this was fascinating, attracted really the huge attention of the condensed matter community, because in this for instance, for this two-dimensional topological insulator, what you could have, this is edge current state. Okay, this, as I said, they are topological protected. You could imagine this is like a one whole system. If you could easily, for instance, you could deform the system in any direction, and you will not perturbate this topological current. Okay, that's why it's interesting. Okay, but of course, for the conventional topological insulator, you have to remember that for the spin electric current, you have two different spin states. Spin down, spin are separate, but both existing. Okay. Okay, this is also one of my favorite figure, also showed yesterday by Professor Sama. I'm really happy to see that. Okay, now come back to actually the complexity in quantum material, because as we introduced yesterday, okay, so we have two axes. So this is electronic correlations. Okay, this is a U. Basically, you could imagine this kind of Haber potential, or is a strength of the electronic correlation. T is a Hawking amplitude. You have a spin-orbit coupling. In the system, as already presented yesterday, so you could have the in this left corner really simple metal and the insulator with hardly any correlation. Okay, if along this line, you could go into, let's say, okay, if you want to increase spin-orbit coupling, we know solid-state physics will have a trick, is we play with the heavy elements. Okay, then the spin-orbit coupling will be scaled up. Then you have often chance to get this topological insulator, even topological superconductor. Okay, this line you really go into strongly correlated system as we defined in last 2 decades. For instance, we started cuprate, we started iron plictite. Yeah, what's really interesting is in the right corner here. Okay, so you get into a region where, let's say, they both electronic correlation and spin-orbit coupling both are strong. So that means topology and correlation will play very important role here. Okay, so for instance, you have a lot of, okay, I think one system we are talking about now, it's really one of the hottest topic, is about the multi-angle twisted bilayer graphite. Okay, this is basically you could classify it as a correlated topological material. Okay. Yeah. Okay. Before I want to, of course, I'm an experimentalist. Okay. I try and give you my thinkings. I think this is really a rapidly evolving field. Okay. I would say it's in explosive development. Nobody really write a book about the topology, how topology could meet correlation, but this really is my thinking. Okay. First, of course, it's easy since we have this established paradigm of the single electron band topology. You know, an easy idea approach, let's add magnetism, okay? Flat band, then stable. Wave this, all of those electronic correlation factor phenomena into a topological, let's say, treated topological system. Then we might have something really unusual would happen, okay? For example, this magnetic topological insulator here. Because, you know, magnetic topological insulator, let's look at this a 2D system, okay? Yeah, so you have, again, this edge mode, okay? because of this exchange splitting, then you would basically gap out another, let's say you have this edge electric current, you gap out another edge current with the opposite spin direction. This is fantastic. That means you essentially, with magnetic topological insulator, you could create dissipationless chiral edge mode. This is, okay, in another talk, we call it quantum non-multiple effect. This will be fascinating, I think, for future spintronics, because it will be cheap, will be faster switching, you know. Yeah, I think this is still a matter of studying now, how to achieve this, okay? There are a number of material which are possible candidate material. This is a really active field, okay, in this. Another approach is, okay, for instance, in this Kagome system or honeycomb system, because the band structure intrinsically, you can have, you know, these two important features. One is Dirac comb, okay? Second, you could have flat band. This is just the nature of this atomic configuration. For instance, if you have a Fermi surface in the Dirac comb, okay, then you have all these Dirac fermions to play around, okay? But if you shift your, could manage to tune your Fermi surface, okay? I don't know how, okay? Tune your Fermi to flat band. I bet you would see immediately a tremendous amount of the correlated electron phenomena. Why? Because flat band, you have a very high electron effective mass and also high density of states. Often these are fertile ground for electronic correlations. Okay. Yeah. This is the first route. Second route, of course, is we talk about the topology in electron band. That is a forming system because the electron is forming. Yeah. But we could, all those topological protected phases can be samely recovered in bosonic system. For instance, in magnons, phonons, or even the optics, okay, photons, okay. So basically, here you could also play all this topological concept to, for instance, search for topological magnon insulator, while magnons even, okay. Yeah, so recently there is a nice review paper, so you can also look at that, okay? So in this topological magnon insulator is the same. You can have this magnon edge excitation mode, then they will generate, you know, in real space, this kind of edge mode, okay, which can be also experimentally, let's say, evidenced by the thermal Hall effect. Third approach, of course, is a very distinct one. I think yesterday Professor Sama also mentioned that. I think it is a topology of a different type. This kind of topology we call topological water in quantum spin liquid. This is a, okay, I can see here. So for instance, based on this Anderson's model, you could have this resonating valence band quantum spin liquid. Okay, in this phase, it's no disorder down to the lowest temperature, just as shown in the example by Professor Sama, okay, but they are strongly correlated, highly dynamic, okay, but it's not just disordered. There is topological order or non-local quantum entanglement in the system, okay. The fractionized quantum particles in this kind of system are anyons, okay, or Majorana Fermis. They are just perfect for the quantum coherence-free quantum computing. You could look at this reference here, I cited here, particularly from Xiaogang Wen, is really advocating this concept of topological order in quantum spin liquid. Another type of quantum spin liquid is a P-type quantum spin liquid. This is based on highly bond-dependent exchange interaction in an icing system. Okay, this is a simple Hamiltonian, but you have three different type of bond. This system actually was proposed by P-type. You could analytically solve this. Okay. The ground state of this very model is a quantum spin liquid. Okay, the process is basically by the fractionization you into this, let's say, a localized a Majorana forming and also itinerant Majorana forming. Really amazing is this model has found a perfect example to realize, that is alpha ruthenium chloride. Okay, this is this system, of course, in the low temperature is magnetic water, but if you apply for in-plane field, okay, you kill this magnetic water in the intermediate field strength, you go into a phase which is claimed to be exactly K-type function spin liquid, okay, because they have the half integer quantized thermal Hall effect. So more or less like this. You apply field, you generate this Majorana edge current, okay? But this is by thermal conductivity. Recently, the same group also confirmed that basically this non-zero Chern numbers for this thermal Hall effect, even without this applied field. Okay, that means it's kind of anomalous zero Hall effect. This is really truly confirmed. This system is highly topological. Okay. Yeah. Okay, I want to, before I finish it, I want to say yesterday, I think the last 2 days I wasn't heard. Actually, this, for instance, from professor in this topological quantum insulator, okay, Professor Marti, yeah, and Professor Prandhan. So they really give me the, I think this, I would say, topological quantum insulator is another perfect way or perfect platform to combine topology and strongly correlated electrons. And also other systems also being studied widely in Indian community magnetic skirmion. For instance, if you find magnetic skirmions in strongly correlated electron system, that would be also phenomenon would come up. Okay, what is the interesting phenomenon? Of course, we do need the materials. Okay, in Gaussian, I have a small little capacity to do the single crystal growth and the exploration quantum material. Okay, so our interest in to grow those interesting system primarily by the flux method and chemical vapor transport. And of course, we could do also some floating low method, which needs to be done in our headquarters in Village. Okay, there is a, but you can see these are some systems we recently grew. Okay, this is a magnetic Dirac wire semi-metal, correlated topological cargo metal, two-dimensional van der Waals material, for instance, alpha silicon chloride, as I mentioned. And of course, we were extremely interested in quantum spin candidate material, but this is really beyond the talk today. I will not talk too much, okay, about this, okay? Yeah. Okay. How much time I still have? Introduction finished. Now I would really give you.
You have 10 minutes, Ixi. You have 10 minutes.
So first example is about Dirac semi-metal. Okay, this one is interesting because European magnetic bismuth is a quasi two-dimensional magnetic Dirac semi-metal. In the early study by our Japanese colleagues, basically they found this quantum Hall effect in when the field is applied into this system. Okay. So they found some changes of magnetism. Of course, they proposed is a spin flow anti-ferromagnetic phase. In this phase regime, they found a strong quantum Hall effect. Okay, of course, this would render the system as a potentially interesting one for the topological spintronics. But there is a key remaining question. Of course, is what are the exact magnetic structure? Okay, neutral, of course, neutral scattering is the most precise way to solve this. Second is what's the nature of this spin flow transition? Is there any interplay between the localized European magnetism, itinerant magnetism, Dirac fermion? Because if you look at here, maybe I've quickly give here, the Dirac fermion is in the bismuth sheet here. Okay, this is what Dirac fermions. You have this Dirac fermion sheet is sandwiched by manganese, is magnetic water, is itinerant, and the localized European. So you see, what is interesting to see these three guys, if they interact with each other, if there are any interplay. But of course, our early work is really suggests this. Okay, we would like to do single crystal neutron diffracting on the applied magnetic field. Yeah, so this is a with neutron scattering. So you could easily say, for instance, here this the manganese magnetic water happened about 340K. So European water takes place about 20K. Okay. Yeah, we determine the magnetic structure comprehensively. So what the structure information are showing here. Yeah, then we add magnetic field. Okay, the field is applied along the C-axis of crystal. Okay, we started this, for instance, by following the European magnetic water and both. That is the advantage with the neutron scattering, comparing, for instance, to old data here, because this you measure magnetization. Okay, that is a contribution from both magnetic sublattice. Okay, with neutrons, that you can show here, for manganese and European, they have a different modulation vectors. Therefore, we could follow each magnetic sublattice in detail. Yeah, this red line, for instance, is a manganese water. You see, when you apply field about 5 Tesla, immediately you see a sharp change. This is a spin flow transition start. But for manganese water here, we do not see any change from here. Okay, so okay, the first thing, of course, we try to do is we try to model the spin flow transition by these formulas here, okay? Then we can get this magnetic anisotropy in the system. I would say this is really a wonderful approach because you do not need the expensive inelastic neutron scattering method to do this, okay? Usually you have to do neutron scattering to phase spin wave to get all this exchange period. We employed this XXZ model, okay? Then what we get is this system basically it has two different types of anisotropy, okay? You have exchange anisotropy, you have single ion anisotropy, okay? So we determine each term, okay? The exchange anisotropy is rather small, but we have a size for single ion anisotropy. This is a spin Hamiltonian here. I think this is very interesting, okay? Then we basically established the nature of the spin flow transition comprehensively. So next, then we have to answer a question, is there any interplay between all those interesting ingredients? Yes. So for instance, first we think is we follow the temperature dependence of manganese water here. Start when you cooling down the sample just below the European near temperature, you find a jump immediately. This is a step jump. So that means when European waters, manganese magnetism is strongly impacted. We also found at this spin flow critical field, okay, there was a jump of manganese water. This is a jump here, okay? So that means when the European starts to spin flow, the manganese water also impacted. Okay, this is we interpret this as a strong evidence of the interplay between localized European itinerant manganese magnetism and Dirac forming. Okay, I think based on, of course, this observation of a quantum Hall effect in this region, we believe that this coupling of European magnetism may pave the way for the magnetic tuning of Dirac forming in the system. I think this is really interesting, provide a very interesting prospect for the future. Okay. Okay. Second example, I come finally to our recent discovery of the topological Magnum insulator. I think yesterday the professor was give a comprehensive introduction exactly about this. So this our interest in community are stimulated by these two discoveries. So it's intrinsic ferromagnetism.
Sorry to interrupt you.
Yeah.
So it would be nice if you can finish in 2 minutes. So
okay. Yeah. So in this system, what we are interested is there are some indication early the topological magnums. What we are interested in is using inelastic neutron scattering of our single crystal, for instance, this crystal overgrown, okay, to study the inelastic magnum excitation. Okay, this is what our observation of magnum excitation. We can clearly find this magnum band inversing along this high symmetry gamma k mk direction. We found also clear gap opening at the k point. Okay, this is a strong indication of the presence of the DM interaction. Okay, then we model this comprehensively by linear spin wave theory. Okay, so we really conclude that in these two systems, so you could intrinsically choose this topological gap while engineering a DM interaction in the system. Okay, yeah, we also, of course, calculate magnum band topology edge state. Okay, so this is truly confirmed. This is a topological nature with Chern number. This is 3 plus minus 3. And we also predict a large thermal conductivity due to topological magnum. I really would wish any people would like to test this. We'll be very happy to provide samples. Okay. Yeah, our conclusion is simple. These two systems are pristine topological magnum insulators. Okay, they would have expect huge applications, for instance, in the future, magnum waveguide, chiral traveling wave, or magnum amplifier, and so on. Okay, yeah, this is just an artist view of this topological in our system. So in the back, you do not see in a certain magnum dispersion mode, you do not see any propagations, but on the edge, they propagate along the edge, just like topological insulator in the sense of the electric current. Finally, I just like to advertise our work. Okay, it's very fast. Okay, so we want to see. Okay, in 2017, based on collaboration with Professor Wenbin Wu's group in the University of Science and Technology of China, we discovered this all oxide-based synthetic antiferromagnetic distributing layer result magnetization reversal. Okay, so we really used the polarized neutral reflected in basically the antiferromagnetic state and the polarized ferromagnetic state. We confirmed this. Okay, but yeah. always we have a question, because this is a magnetization history is new. We always say we measure at 1 and this saturation state. What about this intermediate magnetization stage? How's the lateral stage? How the magnetization process is taking place there? It's not answered in our science paper. Okay, so therefore, as I said, this Ke Zhang came to me in 1 year exchange. So we really decided to follow the magnetization history through by poor resolution reflectivity on the same sample as we measure in the science paper. So this is a pretty comprehensive new PNR study. Okay, you see, we followed at a different stage of magnetization history. So very interesting things is in the stage 3, this intermediate phase and full phase. What we found basically is you always form. Okay, I will put like this. Okay, you have this solitone. I would call it kind of, okay, you say magnetic defect, or you could kind of, this is still being argued whether it's topological defect or not. But you could have, you say the whole process is like this: initial atomic ground state, then you have a solitone degradation, then you have a solitone expansion in the stage 3. Then you have the solitone shrinkage, you come back to initial antiferromagnetic state. This is okay. Because of the presence of these two, from at least our PNR data, we ruled out possible way of this route. Okay, so yeah, that is of course what is interesting point about this is this provide basically a route towards 3-dimensional spintronics. Okay, you have another dimension by just simply governed by the solitone propagation. So yeah, this is a summary of my talk. I hope I already, perhaps the first part is too long, but you can check our papers for the details or these examples. I would like to thank you for your attention.
Thank you, Ixi, for a very nice introduction of topology and correlation effects. And so we can take one quick question because we are running late already. So participants, anyone?
I think, Ixi, I would request you to join the frame virtual room, maybe after the next talk. During the poster session, I request all the speakers to be there, and I am sure discussions can happen. So we are a little bit late actually. Yeah. So I think you can present the memento. Thank you so much, Ixi, for this.
Thank you. Thank you for a very
nice talk.
Introduction.
I really enjoyed. Thank you.
Okay. So.
Okay. So it's
yesterday I was wondering which photo you would took from the internet. Because you seem really find interesting photos. Thank you.
On behalf of organizer of Symposium on Magnetism and Spintronics, SMS-221, and I Sir Bhubaneswar. So it's take immense pleasure in presenting the plaque to Dr. Ixi Shu from Zurich Center of Neutron Science, Germany, in appreciation for being a valuable speaker to give lecture on topology, basically means correlation. So thank you very much.
Thank you very much. Very kind of you. Thank you.
Thank you.
Thank you.
So I hope our okay. So you are already. So I hope you can start your talk immediately. So you have been already introduced, so we all know you. So.
And Jack, I would appreciate if you can finish your talk in 20 minutes.
Yeah. Okay. Is my slides visible?
Yes. Now it is changing. It's all fine. Great. Okay. Thank you.
Thank you. Yeah. So I have already introduced, like as I told you earlier, I have already introduced you to the magnetostriction. Magnetostriction, as I told, is a change in the dimension. In the case of a thin film, like what happens is like either there is a bending of the film in the upward direction or the downward direction based on the magnetostrictive phenomena. That is whether it is a positive or negative. When positive, it bends in the downward direction. When it is negative, it bends in the upward direction. So the converse of magnetostriction also is true, as I mentioned earlier. Like the converse is called Villari effect. That means like there is a change in the permeability or the magnetization state in the material when you apply a mechanical stress to the magnetostrictive material. So there are some direct effects and inverse effects. There are manifestations of the magnetostriction. The Joule is a linear effect and the Villari is an inverse linear effect. The delta E effect is a change in the modulus of the material, and we have also an inverse effect. The Weidmann effect is a torque which is happening in the material, and the inverse is given by the Maitucci effect. The last one is a magneto-volume effect, and the inverse is the Nagoka-Honda effect. So these are the different manifestations of magnetostriction. The simple manifestation is like humming sound what you get near a transformer. So there are several applications also for this material, like we have a mechanical, medical, instrumentation, other field. However, being a defense lab, our interest is to look for solar applications, smart wings, and mine detection. So these are the applications with which we are focusing this material development program. So the same material has also several applications in thin film forms. It can be used as a force sensor. It can be used as a microform, and the microform is found to pump in nearly 50 microliters or 100 microliters per minute. So coming to the material which shows magnetostriction, all the ferromagnetic material to some extent shows magnetostriction. The simple transition metal, namely nickel, shows -38, iron -9. However, the highest magnetostriction is shown by the rare earth metals like dysprosium and terbium. But the Curie temperatures of these materials are relatively very low, less than the room temperature, but they cannot be used for any practical application. So there is a requirement for making new compound or alloys which shows a better magnetostriction at room temperature. So of this one, like the two compounds TBFE2 and DYFE2 are the alloys which have been discovered by Clark in 1978 for which to exhibit good magnetostriction. So coming to the structure of this material shows a large magnetostriction, and basically the reason for the large magnetostriction is because these materials are having high magnetocrystalline anisotropy. And these materials are found to crystalline in C15 type cubic level space structure with FD3 bar M as the base group. And these alloys are found to have an easy magnetization direction along 111 direction. So the right hand side shows the figure shows the various magnetostriction of TBF, rare earth transition metal alloys. And if you see, like the highest magnetostriction is shown by the TBFE2 alloy, and the highest negative magnetostriction is shown by the SMFE2 alloy. However, if you see the value, the saturation or the high value of magnetostriction is achieved only at high magnetic fields. So practically, if you want to make any device out of it, it is very difficult, and we need to apply a very high magnetic field, and the devices become very bulky. So there is a requirement to reduce the field requirement so that we can achieve good magnetostriction at low magnetic. So for that one, new compounds were discovered by having anisotropic compensation. Here, anisotropic compensation, what I mean is, like they take two rare earth transition metals, which is having a positive K1 and negative K1, but the magnetostriction direction is both of them are positive. So when they alloy both of them, at some composition, what has been observed is these materials are found to show high magnetostriction, but relatively at low magnetic field, because basically the compensation of anisotropy is happening. So this compensation has occurred in this particular composition, that is dy.7, tb.2, dy.73, tb.27, and Fe2. And this is one of the very famous compound, and this has been commercialized, and it is commercially available in the name of called terphenol D, manufactured by Etrima. There are several challenges are also when processing this material, because the rare earths are highly reactive. Like rare earths are highly reactive. So the processing, when processing, stringent oxidation prevention and high vacuum levels are required. And second one is like compensation. See, when you have going to have slightly a deviation in the compensation, what happens is the field requirements are going to be accordingly higher. Okay, so this is very important to have a melting practice is very important in this alloy. And second one is, since these materials are anisotropic, that means they have different crystallographic direction along with the properties are different. We need to do some direction solidification techniques to achieve required grain orientation. Essentially, I mean, it is something like a twinkle crystal where the polycrystalline sample where the number of grains what we are having is very less. Okay, so the size of the grain will be around 1 centimeter or 2 centimeter kind of thing in a 10 centimeter rod sample. So this is basically the crystallographic phase diagram of this alloy. The crystallographic phase diagram or the material phase diagram shows that this material is formed by a peritectic reaction. Peritectic reaction, as you always know, like it is formed by a reaction between a solid and a liquid, giving rise to a solid. So always we know in a peritectic reaction, reactions are very sluggish, and always we end up with in a high temperature phase because of the freezing zone. So here in this compound, the high temperature freezing zone is the adjacent compound, which is the DYFE3 alloy, which is having a higher temperature when compared to the DYFE2 alloy. So this DYFE3 alloy is detrimental for magnetostriction. So we need to do processing in such a way that we don't get this DYFE3 phase. And secondly, as I told you, like the other important thing is the reactivity of the rare earth is very important. And the third one is getting single crystal composition. Sorry, single phase is also important. So to achieve these properties, that is like to achieve like crystallographic texture, to achieve anisotropy, or to achieve a phase devoid of the secondary phases, what we adopted is we adopted direction solidification technique. That is the processing route we have used. And in direction solidification technique, we have used two techniques. One is the Bridgman technique, and the other is the modified Bridgman technique, and the other is a zoning technique. In these parameters, we have two parameters to velocity, and the other is the temperature gradient. And the characterization we are planning to do is the phases present, the grain sizes, the texture, and the property what we are envisaging from this is the saturation magnetostriction, static strain coefficient, dynamic strain, and the coupling coefficient. These are the parameters. So our aim is to evolve a structure process property correlation by optimizing the process parameters in this material. So with this one, like we have gone for doing carrying out direction solidification technique. The first and foremost thing in a direction solidification technique is vacuum induction melting and casting. And these alloys are vacuum induction melted and casted at 10⁻⁵ vacuum. And these cast alloys are made in quartz tubes with required dimensions like 6 mm to 12 mm dimensions we have taken, and we are done by zoning technique. In a zoning technique, what we do is like we take the alloy and then we pass this alloy in a induction coil, and this coil is moved from bottom to top. When the coil is moved from bottom to top, the solidification trend, that is the solid liquid interface, moves at a predetermined speed. So we have moved at three different predetermined speed. One is at 18 cm/h, 36 and 72 cm/h. So after doing all these things, we have characterized the for structural magnetic characterization. This curve shows the variation of magnetostriction with respect to the magnetic field when we are done this solidification at different rates. I mean like 18 pulling rate, 18, 36 and 72. What we observed is like at higher pulling rates, the magnetostriction is found to be higher. So to understand this one, we have done a detailed microstructural studies. We have done a cross-section microstructure studies. Cross-section microstructure studies show that the as-cast alloy showed a secondary phase, that is a primary properitic RFE3 phase. However, the solidified alloys does not show the formation of the properitic RFE3 phase. It showed only the parent RFE2 phase and the grain boundary phase, which is the rare earth rich phase. But still the magnetostriction is found to be higher for 72 cm/h, but that is puzzling. So to understand this one, we went for studying the texture present in the material. So we have gone for studying the texture by using X-ray diffraction technique, and also we have used a stereographic projection, that is pole figure generation also has been carried out. From the pole figure studies, what we observed is the crystals grown at higher pulling rate, namely 72 cm/h, showed a strong crystallographic texture close to 112 direction. Okay, when compared with the 18 cm/h, the major texture is along 110 direction. So from this one, we could identify that since the easy direction of magnetization is along 111 direction, the 112 direction is close to 111 direction. As a result, we are going to have a higher magnetostriction in this material. So accordingly, if you see, like the low field magnetostriction also shows that the magnetostriction increases with increase in the pulling rate. So we are also not stopped with that one. We have machined this rod, and we have also developed a small flux functional transducer in collaboration with our sister laboratory, NPOL Kochi. So, but there is a requirement to grow bigger rods with diameters greater than 10 mm. So we have also taken up this development program by designing a indigenously developed direction solidification furnace based on modified Bridgman technique. This furnace was completely designed by us, and it was manufactured by a private company. And here we have a heating chamber which can go up to 1400 degrees centigrade. So we have developed the magnetostrictive rods by modified Bridgman technique, and we have grown at different speeds, like what we have done for zoning at this 18, 36 and 72 cm/h. Accordingly, when we found, like again 72 cm/h was found to be higher, and this is again because of the strong 112 texture what we have observed. We have studied the magnetostriction in this alloy, and the magnetostriction showed that a 1600 ppm was the magnetostriction in this alloy, and this magnetostriction values are found to be much higher than what has been commercially reported or commercially available manufactured by Etrima USA. We also try to understand the microstructure of this alloy. The microstructure showed a pure single phase microstructure devoid of any secondary phases, and this is one of the machined magnetostrictive rods which has been developed in our laboratory. So we have not stopped with this one. In the next stage, we have gone for developing a mechanical like magnetostrictive transducer. We have used a 4-rod multiple transducer assembly using magnetostrictive rod, and these rods have been used for testing underwater characteristics, and we have used the NDFEB permanent magnets and biasing coils, everything, and we found that the sound pressure level was found to be very high, as high as 178, around 177, 175, which is as good as in par with the piezoelectric material which has been currently used. So having done this one, we have also taken up a program for developing this material in the form of a thin film. The motivation for taking this material in the form of a thin film, because like as I told you earlier, like this rare transition metals, rare shows high magnetic moment and transition metal shows a great higher Curie temperature, and these shows a variety of magnetic anisotropy which will be used for magneto-optical recording, and also it can be used as a sensors and actuators like when it comes for a magneto with in-plane magnetic anisotropy. The magnetic phase diagram, that is the composition versus the magnetization behavior, it shows that around the composition with the TB to FeCO ratio, we have found that based on the TB to FeCO ratio, the material is found to show in-plane magnetic anisotropy and out-of-plane magnetic anisotropy. So what we have focused is to tune the magnetic anisotropy in TB FeCO system by changing the composition, by changing the film thickness, and also by using external perturbations like rapid thermal annealing and ion irradiation. So this is one of the TB-FeCO thin film which has been grown by electron beam evaporation technique, and this film shows a strong perpendicular magnetic anisotropy. The MFM images shows that the magnetic anisotropy is like out of plane magnetic anisotropy is really very strong. The power spectral density also shows a random nature. The magnetization shows a strong out of plane magnetic anisotropy, and the in-plane components are nearly nil in this one. So we have tried to understand the magnetic behavior, like the structural behavior, by taking a cross-sectional transmission electron microscopy. The cross-sectional microscope shows that the films are nearly amorphous in nature, but there is a columnar growth of grains in this one. These columnar growth of grains or columnar structures are responsible for the out-of-plane magnetic anisotropy. The film substrate interface is also found to be sharp without any deviation. I mean, like there is no overlapping, or there is no overlapping of composition, or across the interface is very clean. We adopted to tune the magnetic anisotropy. We adopted rapid thermal processing. Upon doing rapid thermal processing, what we observed is the anisotropy was found to slowly change from out of plane to in plane direction. The bubble domains are the labyrinth kind of domains what we have seen is slowly becoming horizontally aligned, and it is found to become very discrete. And with further increase in the annealing temperature, what we found is intermixing of two contrasts we have seen, and finally we got the feather like domains which is having a very zero or very negligible out of plane contrast. The magnetic phase contrast difference also shows it changes from 21 millidegrees to nearly 1.3 degrees upon rapid thermal processing. So we also try to see the magnetic behavior. You can see very clearly from with 5 minutes to 30 minutes, what we observed is the out of plane direction is becoming an in plane, and the in plane direction becoming stronger and stronger. The tilt angle has been calculated, and the tilt angle is also found to increase with increase in the annealing temperature. To understand this one further, we again gone for a detailed depth resolved studies using transmission electron microscope. As I told you, this is the film without any like processing. It shows a clean interface which shows a crystalline nanocrystalline structure. But however, when we increase the rapid thermal annealing, we could see the formation of urine FeCO nanocrystal crystallizing in V2 structure. And with increasing the RTP, rapid thermal processing time, we also found that the interface is going to become very rough. There is a diffusion of FeCO going inside the silicon substrate, because at higher temperature, this is found to happen. And the selected area diffraction patterns also showed the formation of 110 thing. However, with increase in this, the reaction zone is also found to become more and more. So the basic reason for increase in the in-plane magnetic anisotropy with increasing the annealing time is because the formation of FeCO. FeCO tries to tilt the magnetic anisotropy from the out of plane direction to in-plane direction as the concentration of FeCO is increasing with increasing annealing time. So we also try to see the effect of thickness. We have taken one more composition. Earlier was around 80-20 and this was around 10-90. In the 10-90 composition, what we observed is the films are found to be nearly crystalline in nature, which founds in 217 kind of structure, and the microstructure showed a triangular kind of surface morphology. And this triangular kind of morphology, we try to understand along cross section when we found that it showed a nice columnar structure. These columnar kind of structures have been observed when we cut the sample, and accordingly, as we increase thickness, because of the columnar structure, the out of plane magnetic anisotropy is also found to increase. So the magnetostriction measurements carried out using laser Doppler vibrometer, what we observed is as we increase the film thickness, the magnetostriction is found to decrease. This is because as we increase the thickness, because we are trying to measure the magnetostriction along the in-plane direction, but however, when the film thickness increases, we found that the anisotropy is going to become the out of plane direction. The film thickness is found to have an adverse effect on the magnetostriction. So the thickness, films with low thickness are found to show higher magnetostriction. So with this one, like having developed these films, we have gone to the next stage of developing them in the form of a magnetic field sensors. For that one, we have chosen a magneto-electric place magnetic field sensors, and this is very useful for detecting magnetic signatures in our naval system. You know, like Earth magnetic field, at least around a particular field is constant, but when a huge steel-hulled ship goes near this test bed, in a water bed, there is a local disturbances in the magnetic field. These local disturbances can create naval ordinances. So it is important that we detect these magnetic signatures, and the magnetic field change in the magnetic field is around 0.25 to 0.6 Gauss current of thing. So if you see, like this is how like the simulated diagram shows how the magnetic field intensities are going to get changed when a naval system or a ship or submarine moves. So to detect this one, we have planned to develop a magnetic field sensor that is basically a magneto-electric based magnetic field sensor, which is having a piezoelectric layer and a ferromagnetic layer. And as you know, the magneto-electric effect is the generation of the electrical output with the application of a magnetic field. So this work has been carried out in collaboration with the Siri Pilani, and this we have planned to make these sensors using like normal lithography process by device fabrication technique.
Professor, so the first and foremost, you have lost 1.5 minutes.
Okay, so the the fabrication techniques are by the standard lithography process we have used. We have fabricated the cantilevers, and the cantilevers are found to resonate at different frequency based on the dimensions of the cantilever. So we also studied the magnetostrictive cantilever by depositing the film, and we found a maximum deflection of around 2.5 microns happening in the cantilever of a length of around 800 microns. So we also deposited zinc oxide based piezoelectric films, and we found that the zinc oxide films are found to resonate along 10.75 kilohertz, and the maximum deflection is around 2.5 microns, and this is one of the very high values reported in the literature. And this picture shows the deflection of the cantilever. This is actually a cantilever before and after applying an electric field. So the final process is to fabricate the device, and the fabrication devices is a 7-mask lithography process, thermal oxidation of wafer, window opening, bottom electrode, top electrode, zinc oxide deposition, iron like magnetostrictive deposition, and finally the release of the cantilever. And these devices appear something like this in a microscope, and this has been packed in a dual inline pin package, and this is how a packaged device looks. We have studied the device characteristics, and this device characteristics was found to be high around the resonance frequency of the cantilevers, and a maximum output voltage of around 250 millivolts have been obtained, and the sensitivity at capability has been tested up to 0.25 oysters, which is the lower limit of the Earth's magnetic field. Magnetic field sensors have been developed for detecting magnetic signature with a sensitivity of around 25 millivolts per oysters at 1 kilohertz frequency. So this measurement have been carried out using a magnetoelectric measurement setup, which has been homemade in-home magnetostriction measurement setup. So with this one, we like to conclude we could successfully develop magnetostrictive material both in bulk and thin film form with high magnetostriction. This material R&D, we have not stopped with material R&D. We have also taken up extended it towards developing devices, bulk and thin film devices, and in bulk we have gone for an acoustic transducer, and in the thin film we have gone for a magnetic field sensor. Okay, with this one I would like to wind up. Thank you very much.
Thank you, Professor Chelwane, for a nice lecture on magnetostrictive material. So I will just ask a quick question because we're running the time.
Yeah.
So, like you have other material which shows large strain with magnetic field, like ferromagnetic shape memory alloy. Are these not important for this application?
Yeah, you are absolutely trained. Ferromagnetic shape memory alloys are useful, but the magnetic field requirements are in few Teslas. Particularly the nickel manganese gallium based alloy, we require a single crystal and we require at least 2 Tesla magnetic field. Here the magnetic field requirement are up to 100 or 200 oysters. So that is the advantage of using this material.
Okay, thank you.
Okay, I think Sanjay, you can wrap up now. Thank you so much, Jack, for this excellent talk.
Thank you.
And sorry guys for this technical glitch, but we managed, and I'm glad that finally Jack could present. Yeah, please present the memo.
Thank you.
On behalf of organizers on the Symposium on Magnetism and Spintronics, so it takes pleasure in presenting the plaque to Professor J. Chelwane. He's from DMRL Hyderabad, and in appreciation for being a valuable speaker to give a lecture on processing and characterization of magnetostrictive material. So thank you, Professor Chelwane. And
thank you.
Thank you, Jack.
Thank you.
Abhishek, please put the memento for the chairman of the session. I have to make a small announcement. So
Subhankar, there is one straight question from Professor P.S. Anil Kumar. What is the typical magnetic field detection threshold?
Okay.
I think this is very good question. So
So we haven't gone for actual test bed for detecting the magnetic using it as a sensor. We have only characterized with our existing Helmholtz coil, and we could sense up to 0.25 oysters.
Okay,
good.
Thank you. So let's.
I request all the speakers. I request all the speakers to go to the frame platform. You see today program file, whatever was sent this morning, the different room number and zone number for allocated for different speakers. You can click on the frame link and you can go there, and anybody interested to interact with the speakers are also requested to go there and interact. We will have a poster session break or poster session now, actually no break, few minutes, from 5 to 6 p.m. The chairman is Professor Vivek Mallik and Professor Ashish Nandi. They will conduct the poster session. So, but before that, I like to thank the current chairperson of this session, Professor Sanjay Singh. So, Symposium on Magnetism and Spintronics SM 2021. NISER Bhubaneswar, India takes immense pleasure in presenting this plaque to Professor Sanjay Singh for chairing the session. So, thank you so much, Sanjay, for your kind efforts to really very nicely organize this session. Now I request Professor Vivek Mallik and Dr. Ashish Nandi to coordinate the next session, a poster session. If you have any issues, you can actually write also here. We have volunteers in every poster rooms. In case you face any difficulty, you can write in the chat box in the frame platform or here, and volunteers will always assist you. And I think Vivek will monitor both here and there. And if in any case, if you are facing any issues, you can always write. So let's have a very interactive poster session now. And at 6 o'clock, we will be back with the session 9, where we have 3 interesting talks by Professor P.S. Anil Kumar, Professor Perumal Algarsamy, and Professor Soibal Basu. So until that, let's go to the frame and interact. Thank you, Sanjay, and thank you all. See you. By the way, the Zoom link remains the same. You don't need to log out. You can just keep it, or you log in again whatsoever. The Zoom link is same. Thanks. So Vivek, hi. Thanks. Hi. So you also log in into the frame.
Yeah.
And so, if you see any issues, you just tell us. Ashish, the links for the frame are all, announced in the SMS conference website.
So there is no break.
Well, the break is kind of consumed. We have to now take a break, including the poster
session. Yeah, okay.
I have not gone to bathroom now. I will go to bathroom.
Okay, so yeah, Good evening, everyone. Good evening, good morning, good afternoon, whatever the time zone we are. And welcome to this poster session on behalf of organizers and Professor Nandi and myself. I welcome to this poster session. I think session number 9 of this symposium on magnetism and spintronics. So there are approximately 47 posters available in this session, and they are available, I think, from room number 11 till room number 14 of the frame network. I suppose you already have all the numbers, abstract poster titles, etc. to you. This poster session is primarily focused on the bulk samples and bulk measurements. So this poster locations are also available in the list. You can go to different location depending upon your interest. And I hope you are familiar with this frame network. So if there are any issues or questions, let us know. There are volunteers, as Vedanta announced. So yeah, welcome. All of you.
Yeah, I forgot to actually introduce Vivek. He is Professor Vivek Mollik from IIT Roorkee, big expert on heterostructures, magnetism, multiforex, many things. And the chairman is Dr. Ashish Nandi. He is a reader in physics from NISER Bhubaneswar. He works on various things like domain wall dynamics, fermions, and many other theoretical aspects of magnetism. So both will coordinate. So thank you all. And I think room links, let's say for the posters are given on this link. I'm just putting it here for convenience, and you can just go to this website, website and click on wherever room you want to go. And also we have requested yesterday's presenters to be present next to their posters. So still there are a lot of posters from yesterday still be available for discussion. Okay, Vivek. Okay, I take a break now. I will see you guys in some time. Okay.
Yeah. Thank you, Shankar, for the information. Yes, as Professor Nanta said, that there are also posters available from the previous day poster session. So you can also go and check those if you want. Thank you. So now you can log into the frame network and you can be available here also, I suppose.
Hello, Shashwati. I don't have the access to share the screen.
Yes, I think the organizer will be coming and they will help you to share the screen.
Okay.
Okay.
Okay, good.
Okay.
Who are you?
I'm Shashwati.
Yes, yes, I know you.
Oh, yeah. Yeah, I'm fine. Thank you. How are you?
Yeah, fine, good.
Okay.
So green can be used.
No.
Yeah, Professor Arun Kumar, am I audible?
Yes, I can hear you. I can hear you.
Okay, yeah, properly hear you. Okay, yes, okay, thank you.
This frame thing where when I went in, because of that 360-degree rotation, I also got a little bit disorientation. So
Yeah, you can start. You can try sharing because I think I can share actually.
okay.
Okay, so you use that green button, share
let me
screen
see.
button. Yeah.
Can you see my screen?
Yes. So can you go to the full screen mode?
Yeah. Are you seeing the full screen?
Yeah, and change the slides. Yes, fine.
It's moving, right?
Yeah,
Okay.
it's good. Yeah. Okay.
Good. Let me then unshare. Yeah, it works.
So, Professor Anil Kumar, are you open? Is the institute open 100%?
Pardon?
Yeah, is your institute open 100% or?
It's 100%, and this semester is still online, but most likely from next semester onwards, it's going to be in person unless there is no other issues.
Okay.
It's fully open. All students are in the campus. We also administered around 9,400 vaccines in the campus.
Right. Yeah, since you have campus students, so you have to arrange for those. Otherwise, it can be difficult because they cannot go home frequently, and
yes,
it's difficult for them.
Will you give me an indication at 20 minutes?
Yes, sure. They have not told me that whether it's 20 minutes or 25 minutes. So if you cannot if you can make it to 25 minutes, I don't think there will be a problem. Okay.
No, what I was thinking, totally is 30 minutes, 5 minutes I should leave for question answer.
Yes, 5 minutes for
And
question
if
answer.
I get 5 minutes prior to that, 20 minutes, so then I can wrap up in 5 minutes.
Yes.
Yeah, Professor Borman can give a small reminder after 20 minutes. That would be very helpful.
Yes.
Yeah, hello Anil. Hello
Nice
Saswati.
Yeah. Good evening to both of you.
Yes, good evening.
Yeah.
So we start in like 1-2 minutes. Because in poster session, I saw there are a lot of people discussing and, suddenly leaving, it is not easy. This is a different platform. You cannot also stop them.
Yeah.
Right.
In a few minutes, probably people will join in.
Sure.
So I heard Bangalore is cold, Anil, now?
Yeah, it's pretty cold and raining heavily for last few days.
Yeah. So somehow Bhubaneswar is pretty warm. It's very strange. It becomes little cooler, but this no luck. How is temperature in Kolkata?
Yeah, in Kolkata, it's within a day temperatures are changing. You will be feeling sometimes it's summer, sometimes it's winter, sometimes it's autumn. Yeah, it's very difficult. Actually, you don't know that which clothing to carry when you are going to office.
Wow, so much fluctuations.
Yeah, it's too much fluctuation. Yeah.
Okay, I think we can start now.
Yes.
So just I will tell my volunteers to come out of the frame. Just give a second. Yeah, I think we can start. So good evening, everyone. Again, back to the talk. So it is session 9, I believe, or session 10. Session 10. Here the Professor Saswati Borman will chair the session. She is very well known for her theoretical work, micromagnetics, computational magnetism work on magnetic nanostructures, magnetic thin films. We are really happy that you could join us. Thank you so much and kindly agreed to chair the session. We have 3 talks, Professor Anil Kumar, Professor Perumal and Professor Soibal Basu. So I request Professor Saswati Borman to kindly start the session. Thank you so much.
Thank you, Professor Dr. Shubhankar Vedantu, for inviting me to chair the session. So in this session, our first speaker is Professor P.S. Anil Kumar. Before he starts his talk, let me introduce him to the audience.
Saswati, I'm sorry to interrupt with all this. I actually missed. So before we start, we have a small formality to present mementos to the previous chairmen of the poster session. I'm sorry. Yeah, so this is a different style and it needs some practice. So Abhishek, Anil, could you kindly stop sharing for a second?
Sure.
Thank you. Abhishek, could you please start sharing the memento for Professor Vivek Mallik and Professor Ashish Nandi? Okay, so I read it for Professor Ashish Nandi, who is a colleague of mine at NICER. So SMS 2021, thanks you Ashish for co-chairing the session 9 for poster session. Thank you so much. And let's
Thank you.
Thank you. And let's have for Vivek. Yeah, so Symposium on Magnetism and Spintronics, Naisar Bhubaneswar takes immense pleasure in presenting this plaque to Professor Vivek Mallik from IIT Roorkee in appreciation for chairing the session 9, that is poster session. Thank you so much, Vivek. Thank you. Okay, I'm really sorry, I apologize. Now, Saswati, please continue.
Yes, Professor, yes, please. Okay, thank you. So let me introduce Professor Anil Kumar to the audience. He is currently a professor at Department of Physics, Indian Institute of Science, Bangalore. He received his PhD degree in 1998 from University of Pune. He has worked as a postdoctoral fellow at University of Twente in the Netherlands until 2000. He then moved to Max Planck Institute of Microstructural Physics in Germany as a Max Planck postdoctoral fellow and also an Alexander von Humboldt Research Fellow till 2004. He has received numerous awards in his distinguished career, to name a few: ASI Scopus Young Scientist Award, Elsevier, UK India Education Research Initiative Research Award, Microsoft Research India Outstanding Young Faculty Award, Raja Ramanna Lecture Award, JLCSR, Professor Y.T. Kacheri Prestigious Research Award, Brahmana Trust, Dean Young Scientist Research Award. His major research areas are spintronics, magnetic nanostructure, surface and thin film magnetism, magnetotransport in metallic multilayers, and oxide spin polarized electron scattering. The title of his talk today is Enhancing the Spin Orbit Torque Efficiency in Platinum Cobalt Iron Boron Platinum Based Perpendicularly Magnetized System. Without further delay, let me invite Professor Anil Kumar to deliver this talk. Sir, you have 20 to 25 minutes for the talk and 5 minutes for question answer.
Thank you, Professor Saswati, for the introduction. Let me thank Shubhankar for inviting me to this symposium, and also I congratulate him for continuing successfully. Completing 11 years of a very productive research group at Naisar Bhubaneswar. And today I will be talking about enhancing the spin orbit torque efficiency in this kind of perpendicularly magnetized systems. And this work is carried out by Shauvi Kyle, who has just submitted his thesis and waiting for the defense. And of course, the funding from numerous funding agencies to be acknowledged. So, it's working. Let me stop sharing and then share it once again. Yeah, it's working now. Sorry, share.
I think Anil, when you share your screen, as you know, please share the full screen.
Yes, that's true. Actually, I was sharing the same way, but there is some technical glitch I'm facing now. Okay, let me try now. Are you seeing my screen? Yeah.
Yes.
Fine. Okay, so this work is carried by Shauvi Kyle, who just submitted his thesis. So the content is that I'll give a brief introduction, why we do these things and the motivation. And then I will discuss about the asymmetric magnetic domain wall motion under this lateral as well as a normal space inversion symmetry with interfacial Jakushinsky-Muria interaction. And also I will tell you the ways by which we engineered the structures to improve the spin orbit torque efficiency in this kind of perpendicularly magnetized systems. So if you look at, all of you are aware in the last 2-3 days, all of us are hearing that, data storage in ferromagnetic system is very important. And there are 2 ways of controlling the magnetization switching. One is by applying a magnetic field or by applying electrical current. So all of us know that there are obvious advantages and disadvantages for magnetic field induced switching of magnetization. And at the same time, people are trying to switch the magnetization with the electrical current. So the idea is to have lower power consumption in memory devices. The main candidate that was initially proposed was based on spin transfer torque to switch the magnetization state. But if you look at the spin transfer torque, all of us know that there's a high current density that is needed for switching, which is of the order of 10 to the power 12 ampere per meter square. So then people started looking at suitable candidates to replace the spin transfer torque with spin orbit torque. And this has become, a very successful story so far. First, this was observed in semiconductors with broken space inversion symmetry. And then people found that, this can also be obtained in, perpendicularly magnetized system where we have a proximity of a ferromagnet with a heavy metal. So of course, the origin is still being worked out. The advantage is that you can have, 1 order of magnitude lower current density compared to the spin transfer torque. So there are a lot of progress that was happening in this side, and with this kind of a material combination, people can achieve up to 5 to 10 ampere per meter square. So the aim of this particular work, which I'm showing here, is to look for even further reduction in this critical current by which is used to switch the magnetization of this kind of materials. So the root cause of, the main principle is here is Jaworzinski-Moria interaction. So all of you are aware of this kind of interaction. So what I'm trying to say here is that suppose if I nucleate a bubble domain in a magnetic material which is perpendicularly magnetized. Now by applying successive, if it is perpendicularly magnetized, what I can do, I can apply outer plane magnetic field and then switch the magnetization like hysteresis loop I can get. So in addition to that, if I can apply pulsed magnetic field, if I first nucleate a magnetic domain, and then I can start expanding this magnetic domain successively by applying a pulsed magnetic field. And at the same time, if I apply an in-plane magnetic field, depending upon the strength of this in-plane magnetic field, the domain wall expansion can be asymmetric. And depending upon the Jaworzinski-Moria interaction, whether this coefficient is greater than 0 or less than 0, you can find out in which direction this domain wall is going to expand faster compared to the other side. So if you say that, if the domain wall is expanding, the right side of the domain wall versus the second left side of the domain wall can have 2 different velocities depending upon all these interactions. So from there, this kind of experiments, we can also estimate the DMI field. So the DMI field can also be estimated here. In this kind of structures which I'm talking about, generally the Neal wall is preferred because of the energy conditions. So another interesting thing, so what we are, the experiments which I'm going to show you today is always in this creep region where this domain wall velocity is of this particular form where this mu is 1 quarter. And now if you look at the domain wall energy density in this kind of system, for a block wall, it takes this particular form, and for a Neal wall, it takes this particular form. Why I'm showing this one here is that if you look at in this equation, you see Hx, which is a magnetic field I am applying in plane of the sample. And HDMI is the DMI field in this system. So here, if you look at very carefully, the moment you have an equal and opposite field of HDMI like an Hx field, what can happen? This term can completely vanish. So since this has got a negative sign, the maximum value of this term comes when this factor is 0. So that means when your HDMI is equal and opposite to your applied in plane field, this energy density goes through a maximum. Suppose if there is no HDMI in the system, And if you don't apply any magnetic field, this maxima will appear at 0. Now, due to the presence of this HDMI, this can shift either to the left or to the right. And by doing proper experiments, you can estimate this HDMI. Or this domain wall density is, energy density is connected to the velocity in an inverse way. Or you can see that the minimum velocity at which the field, the HX field at which the velocity attains a minimum can be the HDMI or this DMI field. With this, we can estimate this kind of DMI field, and also I will tell you how to extract various parameters from this kind of systems. So we do this in a the material is prepared in an ultra high vacuum deposition system with the multiple targets, and it has got a load lock so that you can transfer up to, we have around up to 12 samples can be transported inside and out through this load lock system, and we can have very high throughput. So let me just discuss some of the salient features. So let us take one system to begin with to give you some idea how do we do things. We take a silicon dioxide substrate on which we grow 3 nanometers of tantalum, and then in the first set I'm going to show you that we grow multiple platinum bottom layers, that 3 nanometers, 4 nanometers, or 5 nanometers. And then we have a cobalt iron boron structure, which is approximately 0.4 nanometer. And this is also prepared in a slightly in a wedge form. But this wedge should not be misunderstood by the figure that is shown here. This is a very, very shallow difference between these two, in the sense that over a distance of 1 centimeter, if I put 50 nanometers of COFEB, then hardly I will have a couple of nanometers of variation. So then you can see that hardly there is any variation, but at the same time, there is an asymmetry here. So now we do X-ray reflectivity for each of the samples and then fit it and then extract the exact thickness of these films and its surface roughness, etc. So this is how we get our sample. And then once we have the sample, in this particular system where you have a thickness gradient, a slight thickness gradient, the magnetization is from an ideal perpendicularly magnetized state is getting slightly tilted. So first we estimate the tilt in the system by doing a particular experiment where what we do, we take this vertically applied magnetic field HZ and we draw get a hysteresis loop. When you apply an in-plane field which is 0, and then what we do, we apply an in-plane magnetic field, say in this particular case minus 20 millitesla, and you get this hysteresis loop. And then you apply a plus 20 millitesla in-plane magnetic field and you get another hysteresis loop. Now, depending upon the direction of this applied in-plane magnetic field, the hysteresis loop gets shifted either to the right or the left. Now, what we can do for a different phi angle, say keep this a phi angle which is 0, then what we do for different applied in-plane field, you calculate this delta HC, which is a shift in this hysteresis loop, and you get a linear curve and you get a slope of that curve. And that slope of the curve you are fitting with, you are plotting with the different tilt angle, phi tilt. So then from these experiments, we can calculate the tilt in this material. So it is not ideally perpendicularly magnetized system. It is slightly tilted due to this thickness asymmetry. So this is the first experiment where you estimate approximately the thickness, the tilt in the anisotropy in this material. Now, what we do, the second effort is to estimate the DMI field in the system. What we do, we nucleate a bubble domain in the system, and you apply an in-plane magnetic field in this particular experiment. I'm just giving you as an example, an in-plane magnetic field of 60 millitesla, and you apply a vertical magnetic field of say 5.2 millitesla. And this field is applied as a pulse, 10 millisecond pulse. Then I'm just imagine this particular domain here. Now I apply the next pulse with the same magnetic field, then this domain expands. And if I apply the next pulse, the domain again gets expands. And if I put one more pulse, again, it is getting expanded. So I know the width of the pulse which I'm applying, and I know the distance this domain wall is traveling in all the directions. From there, I can get the domain wall velocity as a function of my in-plane applied magnetic field. For example, now this experiment is only with the 60 millitesla field. Now what we do, we vary this in-plane applied magnetic field from say minus 60 Tesla to plus 60 millitesla. And then for a given perpendicular magnetic field of 5.2 millitesla, you get this kind of a plot. And this plot I can again fit with the creep law fit. And from there, I can find out what is the minimum of this, this velocity and the field at which this minimum of this velocity can be estimated. Now what we do this experiment. Now for different applied perpendicular field, in this particular case, there is a tilt here. You apply the in-plane field in this direction, which is phi tilt is to 90 degree. And then you get this contours, velocity contours for different values of HZ. The previous experiment is for one HZ. For varying this H in-plane field, you get this velocity minimum. Similarly, you get the velocity information for different perpendicular applied magnetic field and for different in-plane applied magnetic field. From there, from this velocity plot, see in this case, we have applied theta phi tilt is 90 degree. And in the next case, it is applied is along this tilt direction where phi tilt equal to 0. And from there, what we can do, we can estimate several parameters. And for example, in this particular case, we have a series of samples, S1, S2, S3. From there, we find out what is a DMI field in the system. And from there, we can find out the coefficient here. The interesting experiment, the result from this experiment is that as I vary the thickness of the platinum layer, say from 3 nanometers to 5 nanometer, you see that this D effective value is going from a negative to positive. So there is a crossover of the DMI field from a negative to a positive thing. So this is one information that we have. Now what we do with this information, now we wanted to improve the spin orbit torque efficiency in this kind of system. So we prepare 4 different samples just to give you a feel: tantalum, platinum, COFEB, platinum, tantalum, platinum, where the COFEB has got a uniform thickness without any thickness variation. Whereas in the second case, we have a slight wedge, a thickness asymmetry here. And in the third case, what we are going to do, we are going to have a constant thickness of COFEB. And we also put a thick COFEB on the top that gives you an in-plane magnetic field. So in the previous experiments, you saw that we had to apply an in-plane magnetic field. So our aim is to get the stray field that is coming from this COFEB to assist the magnetization reversal by applying lower current. In a third case, what we do, we vary the thickness of COFEB along with this stray field. Now, again, we go back and then start doing this experiment. Again, we do, X-ray reflectivity analysis and estimate the exact thickness of these layers. And, we can assess the thickness of the individual layers, the interface roughness. So this tells you that the quality of the film is extremely good. Now let us look into how the current induced magnetization reversal happens. So this is a structure here, and this is patterned by lithography into a bar kind of a structure where we know the exact width of this bar and the thickness of this bar, from which we can apply, for example, I'm giving you an example where I apply 4 millitesla magnetic field in this direction. And then I start varying the current through this pad. And I nucleate a domain, and you see that this domain can move, or the magnetization can be switched from plus Z to minus Z by applying a current density. So that means we know the thickness, we know the width, we know the applied current. Now we vary the current, and then you see that the magnetization is reversed as a function of applied current. But at the same time, if I don't apply an in-plane magnetic field, I don't see a well-defined switching, so I don't get deterministic switching. Whereas if I go from 4 millitesla to 60 millitesla, you see that I get well-defined switching of magnetization by applying an in-plane current. So this is the way to find out the critical current density by which you can switch the magnetization. So now another experiment also we do, we can from here, for different in-plane applied magnetic field, you can calculate the current density. Here you can see that if I don't apply any magnetic field, then I don't get a deterministic switching. I need the help of an in-plane magnetic field to achieve the switching, and here you get a switching of the order of 10 power 11 ampere per meter square. And another experiment which we do at the same point is to find out the spin orbit torque efficiency. So here what we do, we apply an in-plane magnetic field, and you apply a particular current, and then you get your HZ, you switch the vertical magnetic field, you sweep, and you get the hysteresis loop. Now, because of the presence of the current, the hysteresis loop gets shifted. If you apply a plus current in one direction, if I apply a minus current in the other direction, and then the loop shift we can find out for a given current density. So that is the chi value, and then that chi now we do for different in-plane magnetic fields, and you get a plot like this. So this is chi versus Hx. And here you can see that above a particular field, the chi gets, so I've completed 20 minutes.
Yeah, it's 20 minutes, so you have 5 more minutes.
Sure, clear. So above this field, you see that it becomes constant, and we found from independent experiments that this field is exactly corresponding to the DMI field. So this is another way of estimating the DMI field. In the previous case, I showed you from the velocity measurement, we could estimate the DMI field. Now, current-induced magnetization reversal from that switching phase diagram also we can estimate it. So I will not go into those details. Then we have different samples. So this is the next sample which has got an asymmetry. You see, all this time we estimate this efficiency, and we can calculate the switching, the HDMI field, and also we can measure the phase diagram, switching phase diagram. Now, if I get into the wedge-shaped sample here, more interestingly, you can see that even without applying an in-plane magnetic field, you are able to switch. So that means here, there is no gray region here. Even at zero magnetic field, I can switch. And you will see here that, okay, let me just, you will see here that the current density has come down to 5 into 10 power 10. So in the previous case, it was 10 power 11. So now it is with the assistance of a magnetic field, we can reduce it to 5 into 10 power minus 10. From there, we go further, and we started putting the COFEB. Probably I will go to the data where we have this wedge-shaped sample with the COFEB. You can see that even at zero field, you are able to switch. And also you will see very soon that the current density required to switch this magnetization has gone, I mean, the requirement of an in-plane magnetic field has gone down because of the presence of this in-plane magnetized COFEB that is in turn giving rise to additional stray field. So interestingly, we are able to get in this kind of structure a current density of 3.3 into 10 power 10 ampere per meter square. with one more structure. Let me just wind up this talk. So here we are able to get, extremely low current density for switching. And without magnetic field, you are getting, approximately 8 into 10 power 10 current density. Now we will look into one more structure. What we are going to do, we are going to have the COFEB layer as the bottom layer, which is giving you the stray field. And then we are putting a very thin layer of platinum on top, and then different thicknesses of tantalum on top. So 2, 3, 4, 5, 6 nanometer thick tantalum on top. The idea is that the spin Hall angle for this platinum and tantalum is opposite. That should be able to give you an additional freedom, in the sense that my critical current density should go further down. So again, all these things are done. Now, if you look at here, you see here, even at zero magnetic field, you are able to switch the magnetization because there is an thickness gradient. And now if you look at the values that is coming as the critical current density is going below 2 into 10 power 10 ampere per meter square. So this has now given us a lot of information. So like this, we do experiments for all different samples, like different thicknesses of tantalum, and we found that at an optimum thickness of tantalum, we get a critical current density which is 2 into 10 power 10 ampere per meter square. So this experiments within the idea was to use the same material combinations that we are using and see the novel methods of reducing this critical current density by using different aspects, and we have succeeded in that. So the next step would be to look for different material combinations. So now this is with the same material combinations, you are able to switch the current density. So in summary, I would like to say that, look, we can achieve down to 2 into 10 power 10 ampere per meter square of a current density with an in-plane applied magnetic field of a millitesla, or 3 into 10 power 10 ampere per meter square without applying an in-plane field. So this is the engineering that we are doing to control the critical current density in this kind of structures. And we are also able to estimate the DMI field and tilt angle. So this experiment I was just demonstrating to say that we can estimate the tilt angle, we can estimate the DMI field, we can estimate the critical current density, and we can improve the critical current density. Thank you.
Thank you, Professor Kumar, for such an enlightening talk. I can see some questions in the chat box, and some people have raised hands already. The talk is now open for question answer. So, shall I read out the question, Professor Bidanpur, or people will be asking questions? Okay. Well, first question is that I cannot understand why in-plane magnetic field and in-plane current can switch perpendicular magnetization.
Yeah. See, the point is that the switching is happening not by the in-plane magnetic field. The switching is happening either by the perpendicular magnetic field or the current density that we have, the current which is passed. The in-plane magnetic field is assisting you to reduce the current density. For example, if I have a perfectly perpendicularly magnetized system, then I cannot break the symmetry. So because of that, the switching of the magnetization cannot be deterministic. But if either you apply an in-plane magnetic field or tilt this magnetization, so that is why in the case where we didn't have a thickness variation, we could switch the magnetization only by applying an in-plane magnetic field. Whereas if there is a thickness gradient, then there is an intrinsic tilting, then you could apply a torque and switch the magnetization. So it is not the in-plane magnetic field that is switching. It is the vertical magnetic field which is switching, but in-plane magnetic field is assisting.
Okay. So I can see a lot of questions in the chat box, and Dr. Shogata Mullik, he has raised his hand. Shogata Mullik, can you ask a question?
Yes. Okay. Good evening, sir. It was a very nice talk. I assume that the DMI in your sample is coming because of the wedge structure of the cobalt iron boron, because both side is platinum. So since you have very low DMI because only due to the gradient asymmetry of the cobalt iron boron layer, don't you think it will be better to choose a different layer in compared to platinum on top? And also the next question is, do you really see a big difference by adding the different contribution of platinum and tantalum from the other side? Because when we try to do this, that for specifically skyrmions, we don't see that much of advantage in a platinum cobalt tantalum based chip stream. So it would be nice to have your opinion on this.
Yeah, see, if you look at the platinum thickness, which I was using all the time, the top platinum thickness is much lower than the spin diffusion length. So the effect of the bottom platinum is not offset by the top platinum. That's one thing. Second thing is that, as you said, ideally platinum, cobalt, tantalum could be a good structure, but our experience says that this tantalum destroys the COFEB below that. So the structure gets affected. That's why in the second case, you saw that we have put a very thin layer of platinum, which is 0.4 nanometers of platinum. And then if you put tantalum on top of that, we could get large spin Hall angle, as well as we could reduce the critical current density. I hope that answers your question.
Okay. Okay.
In case of current induced domain wall motion, how domains are nucleated in the track initially? Is it nucleated by outer plane pulse field or? Yeah. I mean, you can do that. See, the good thing about this kind of structures, there will be some defect somewhere to get a domain, nucleated. And if it is not happening, then you can have artificial ways of nucleating this by destroying the structure.
Yeah, I'm sorry to interrupt. I think we can move on. During the break, there is half an hour before the next session. During that time, I have actually many questions for Anil. I would personally love to go to the frame platform. I see there are many more questions. So maybe if Professor Sashwati Burman agrees, then we can do that during the.
Yes, please. Yeah.
Very exciting talk. Of course, many questions. Yeah. So please stop sharing screen, Anil. And Abhishek, please share your screen.
Okay, let me read out. This is a virtual memento. Symposium on Magnetism and Spintronics SMS-2021 National Institute of Science Education and Research, NISE, Bhubaneswar, India. Takes immense pleasure in presenting the plaque to Professor P.S. Anil Kumar, IISc Bangalore, India, in appreciation for being a valuable speaker to give a lecture on enhancing the spin-orbit torque efficiency on platinum cobalt iron boron platinum-based perpendicular magnetized system. Thank you, Professor Anil.
Thank you so much for this very, very exciting talk.
Thank you.
So our next speaker is Professor Perumal Algarsamy. Sir, are you here? Professor Perumal Algarsamy?
Yes, I am.
IIT Guwahati. Yes. Can you share your screen currently?
Can that be seen now?
Yeah, let me check. No, I can see your desktop actually.
Yeah, that's fine. So just want to confirm first desktop, then the screen.
Yeah.
Now you have shown us the apples.
Yeah.
Can you go to the full screen mode and can you check that where the slides are moving? Yeah, can you change the slides? Let me check. Yeah, okay. Thank you. So let me introduce Professor Perumal with this audience. Professor Algarsamy is currently a professor at Department of Physics, IIT Guwahati. He received his PhD degree from Department of Physics and Meteorology, Indian Institute of Technology, Kharagpur, India in 2002. He visited as a postdoctoral fellow at Center for Nanospinning of Spintronics Materials in MS, Korea, Advanced Institute of Science and Technology, South Korea. He received several awards, to name a few, Young Scientist Award from Indian National Science Academy and Young Scientist Research Award from Board of Research in Nuclear Sciences, the Indira Gandhi Shabdhana Gold Medal Award in 2013. He has visited NIMS Japan as a Japan Society for Promotion of Science Fellow. He is a life member of Magnetic Society of India and member of IEEE Magnetic Society. His research work is mainly focused on the following areas: linear current-induced CIP GMR for magnetic sensors, novel materials for energy harvesting, transition metal oxide-based films for Spintronics, multi-layer thin films for soft magnetic fields and spin bulk structures, magnetic nanoparticles, and nanocomposites. The title of his talk today is Ferromagnetic Nanocomposites, the preparation using mechanochemical synthesis and the exploitation towards energy harvesting. Over to you, sir.
Thank you for nice introductions, and very good evening and very good morning or very good afternoon, however the way you take it. So
you have 20 minutes, sir. Huh?
Yeah, 25 minutes, correct?
25 minutes plus 5 minutes question.
Okay, I'm counting my timeline also. I'm running, watch is running now. Okay, so today I'll just discuss about a kind of a different angle compared to the previous speech. So this is a kind of ferromagnetic nanocomposites, like how we can produce in a cost-effective way of it using a simple mechanochemical synthesis using ball milling, and see what we can do it with these material for energy harvesting. So these are the people that participated in this work. So first I'll give a brief outline that how these nanocomposites are playing a role, and what are the advantages of this mechanochemical synthesis and what we are really looking for, and what is the result that comes out during this mechanochemical synthesis, and how we can transfer it to make these triboelectric nano-generated devices, and see what we can do if I just do exercise, just can I charge my cell phone during walking myself, and so on. We can look at it. And then okay, so we know by now that what nanocomposites are. Like, there are a variety of nanocomposites to say. So we can have either a particle dispersed in a medium. I think it doesn't permit. So anyway, so the particle, let me change, dispersed in a medium, are kind of nanofibers dispersed, or continuous fibers, or laminated structures. So in nanocomposites, despite having various part of like different combinations, at least one of them or all of them should be in a nanometric dimensions if you want to do it. So basically the metal oxide is a kind of nanocomposite we can create if you can segregate metal and metal oxide having different properties, and thereby we can generate the possible applications in catalysis or plasmonics and sensors or ore reductions or metallurgical process, whatever is possible, we can try for it. And these materials generally produced by numerous ways. So we can start with the hydrothermal, sputtering, electrodeposition, so on. Although every technique has its own pros and cons, we are specifically looking for milling process because that's one of the simplest and inexpensive technique that can create a lot of materials and industrially viable if possible, and you can tune the production of nanocomposite based on a lot of tuning parameters very easily. It's just like starts from bulk and then generate this nanoscale quite easily. So particularly what happens in a mechanochemicals, so you have both mechanical, because we all know that in ball milling, just putting a material A and B, you can able to produce the alloys or solid solutions or amorphous materials of combination of choices. But if you can simultaneously create reactions, then it's going to be much more interactive. So therefore you start with mechanical and then generate a chemical reaction to produce the mechanochemical based nanocomposites. So either we can have a binary oxides or ternary oxides, or even nowadays people try for high entropy oxides by using mechanochemical process, and successfully you can make it, without any temperature process involved. All these possibilities are there. Okay, now how they generally work. So what we need to do it. So if you take a material combinations in some form of it without reaching the stoichiometric process to happen, then we can end up in two different ways of it. One is you start with the gradual reaction process, which means the reaction from one part to the other part takes place progressively without rapid process, which means that in the process, eventually you will have your parent system larger than the produced nanocomposites. On the other hand, if you can go for self-propagating reactions, where if you take any combination of stoichiometric limit, then this mechanical process helps to form the reaction, and that reaction can lead to form a nanocomposites completely towards 100%, and it just in the room temperature environment and so on. So the only the process, it needs a kind of ignition time. So the critical time of mechanical milling to produce these nanocomposites or create the reaction process to produce the nanocomposites. So we consider it to be the ignition time that is very important for it. Now, the advantage is that because, the mechanical alloying generates a large grain size reductions or particle size reduction or crystalline size reduction, however we take it. And therefore, when the large size reduction happen, you have large surface area allowing to have high reactivity, and therefore the reaction temperature reduces largely, and you can increase the reaction rate and then reaction time. All this combination can be played with that. And then this process allows for, what not possible by any other techniques. So all equilibrium which are not achievable by any other method can be also easily produced by optimizing the process. Now, if you look at back, what are the things done? Like this, what people do, take a silicon dioxide, put aluminum, and then just go for milling it. So you will have either silicon come out and then aluminum oxide is formed. So you form a nanocomposite of silicon in alumina is possible. Similarly, a lot of combination is possible, and it has a lot, depending on the application they look for. And this is what people try, all these various materials. We particularly interested in magnetic nanocomposites. So when we look at the magnetic nanocomposites, like we take transition metal oxides, so like nickel oxide, manganese oxides, and so on. So particularly nickel oxide is a very interesting material adapted for a lot of applications, including as a typical antiferromagnetic materials, because it has a very high Néel temperature among most of these transition metal oxides, and they are easy to produce. And this is a typical structure that you see through here. It has a FCC structure with the NaCl formation. And normally in a typical stoichiometric, they look green color, light green. And then if you can produce a non-stoichiometric, that means if you can create a vacancies of oxygen and so on, they will tend to be dark green, and thereby we can play with the material properties. So I'm not going to details about this arrangement of spins, but the idea is using a simple nickel oxide structure. So people already tried just like, taking aluminum and then adding with the nickel oxide, see how I can take away the oxygen to form alumina and the nickel. So you have option for nickel, alumina matrix, and then you can play with the properties and so on. And people tried with the hydrogen, carbon, and zinc. But some of the process they tried is only limited to either it's a gradual process or self-combustion process, but there's no systematic study happen. So that let us allow to look for a systematic way. So what we do is take a nickel oxide and then put titanium. So in osmic state, you have both of the powders, and then you allow this mechanical alloying to take place. So to form eventually such that the oxygen is taken away by the titanium, so forming a nickel TiO2 combinations, or if you do magnesium in a proper combination, so it can form nickel magnesium oxides. Now the oxide that forms eventually may not be perfect oxide. It can have a lot of vacancies depending on the time that you control for reactional process, and thereby allowing oxygen vacancy induced process and the properties tunable, and so on. So this is a schematic that is shown here. So the mechanical alloying has a planetary ball mill motion. So the stage rotates in one direction and the vial rotates in opposite way. So thereby this nickel oxide, particularly magnesium, that mixture when passed through these balls and they get crushed, and when a suitable combination of stoichiometric ratio comes in, then they start forming a reactional process. So you will have an ignition of chemical reaction that you see here in the bottom, and producing these composites very easily. Very simple technique, nothing to take care of it. And what is important in mechanical alloying, because the way we take the ball and powder weight ratio, and also how fast we mill it, and how much time you want to do it. So type of grinding medium all allows to do a lot of manipulation in the formation of nano composites. Finally, what we are looking for it. But then our idea is to make magnetic nano composites. They're having nice magnetic in oxide environment. Obviously, we do a lot of characterization. That's anyway not very important. So let me summarize the results of nickel oxide when we take with the titanium. What happens? So we play two ways. One way is that you take the composition of titanium from 0 to stoichiometric range, and the other way is that you fix it at two different composition, one close to stoichiometric, one away from stoichiometric, to look at what happens. So first I'll explain what happens in the case of varying the titanium composition. So this is the pure just mixed case. So you have both nickel oxide peaks very clearly and titanium peaks, and then as we mill, now you can see without titanium, so you have a broad peak of nickel oxide, so reaching nearly nanoscale of something like 12 nanometer nickel oxide particle, and then some may induce magnetism and so on. But as soon as we add titanium, so even a 5%, then still you can see the reaction is not taken because titanium is still trying to mix with the nickel oxide, and up to 20%, we don't see any kind of reaction. But about 25, you can see this, the major nickel oxide 200 is splitting into multiple peaks, and then finally is trying to reach completely the nickel phase. So along with the titanium oxide formations. So basically what happens as we add that titanium more and more, so it starts reacting such that the oxygen from nickel is transferred to give titanium oxide, leaving nickel nanoparticles. Now, how do we calibrate? So we do a lot of, if you can particularly look at this particular peak of nickel oxide 200, you can clearly see that it is shifting to nickel by the formation of nanocomposite. So that we can resolve it by carefully analyzing it, and thereby we can quantify how much reduction of nickel oxide takes place to finally form. So we can reach up to nearly 80% of nickel oxide reduction takes place. So if we can control up to 100%, fine, but we intentionally stop it because you will have a combination of nickel oxide, nickel, and titanium oxide. This titanium oxide would be neither proper titanium oxide, so oxygen vacancy induced titanium oxide formation. That for a particular reason I'll later explain it. So the formation of nanocomposites can be seen through the TM images, fine nanoparticle dispersions. So when we quantify two ways. You can use this XRD integrated area to calculate the reduction. We can also quantify by monitoring the magnetization change happens. So as you can see that the pure nickel oxide shows a very weak moment, almost the hysteresis loop passing through the origin. But in plot in logarithmic scale, you can see that they show like a very low moment. But as we increase the titanium, there almost no change happens till certain percentage of titanium. But as we increase the titanium about 25%, because there's a formation of nickel, the magnetization continue to increase. And for particularly 35%, you can see the large magnetization happens because 80% of the nickel oxide reduction happened in eventually. So that is what we can see here from the magnetization. So the magnetization continuously increases because of the formation of the reaction process and forming a nanocomposite. in the process. But are these titanium really reacting to form complete reduction process? So that only we can see if we can see the temperature dependent studies. So when we look at this thermomagnetation data as a function of temperature, you can see here the magnetation start falling down, but then at a particular temperature, you can see again the magnetation increases because the some of the titanium that does not react earlier now start reacting because the temperature is raised, allowing to form more reduction and thereby increasing the nickel fraction to give magnetation and then doing it. So what indirectly it says that the titanium, although it's supposed to react completely because it's forming a independent milling process, there are some unreacted titanium still exists in a nano phase and thereby so allowing extra reaction process with increasing temperature. Okay, now when we look at for a particular composition to see what is the ratio of antiferromagnetic ferromagnetic combination that we can play with, so we choose one at lower side of stoichiometric, another one is just around that stoichiometric, and see what happens in that. So anyway, as you can see here, when we take only 20% of the titanium, it doesn't form a nickel enormously because it doesn't allow to form the actual reaction. It only takes the gradual reaction, and therefore you can see majorly the nickel oxide phase stand by without much reaction that happens. But once you take 35%, you can see the nickel oxide is completely transformed into nickel and making it to change the properties. So to compare it, if you plot the amount of nickel reduction that takes place for the 20% of titanium, it's a very gradual process and thereby the reduction is very limited, not more than 15%. But as soon as we take the stoichiometric process, we can see even within 5 hours of milling or 10 hours of milling, you can see a sharp jump in the reduction process happening and thereby leaving a lot of reduction to take place. But with increasing the milling time, these formed nickel further reduces and thereby this kind of, there was a problem in evolving the peak and therefore there's an error in calculation of it. But nevertheless, this nickel oxide reduction is reached to be something like 90% and above. So this again, the morphological features, but that's not happened. So in the case of 20%, you can see here, because there is a large nickel oxide still, along with the formation of nickel, you can see that non-saturated behavior of magnetization is the finite curve formation occurring here. In the case of 35%, because you compare to you end up in forming a complete nickel with the titanium oxide, so the magnetization increases very rapidly. So this allows us to optimize the amount of magnetism that you want to really take into account while designing the materials, with whether you want rich antiferromagnetic or rich magnetic, all you can play with the choice of the material and type of the reaction that take place and thereby producing the nanocomposite selectively. So the same way we can correlate it to the magnetization formation. You can see that magnetization increases gradually for 20% of titanium, which is lower than stoichiometric, and towards stoichiometric, you can see the magnetization reaching very large, giving the transformation of nickel in the process. That you can compare all the way, but same way we tried for looking at the reactional process. Once you form, in the case of 35%, once you reach the nanocomposite, you won't see kind of reaction that takes place. But when the non-self-combustion process or gradual process, you end up seeing this kind of rise in the magnetization. But the idea is to compare whether we are forming stable nickel properties or not in the nanocomposite of it. So in the similar line, we also try for magnesium and try to see it. So the same way we try to look for the different composition and try to produce it after a lot of optimization. And this is what exactly happens. So here we can see the nickel oxide and magnesium peak in the mixed states. So as we keep on adding the addition of magnesium and up to 25%, we don't see any reaction. All magnesium gets into the nickel oxide without doing any reaction process. But as we increase more than 25%, you can see start splitting the peaks. The nickel oxide 200 splits to nickel, and then that splitting become more prominent and forming eventually the magnesium oxide and nickel environment. So same way, we can also quantify very clearly, it's not nickel oxide, this is a magnesium oxide. So we can see the peak positions are completely different locations. So thereby we can quantify how much the nickel oxide reduction takes place. Here we can even go up to 96% successfully in the simplest process without involving any temperature. And we look at all the microstructures and the magnetic properties. So again, this also showing a very systematic variation depending on the type of reaction takes place. So all we construct it and look at how the magnetization can be tuned by producing the nanocomposites. And like titanium, magnesium also unreacted when the composition is below 10%, because while magnesium is made to be solid solution with the nickel oxide, they do not form any reaction. But as we increase the temperature, the magnesium start reacting with the nickel oxide and removing the oxygen from nickel oxide. Therefore, nickel fraction increases, giving kind of peaks here in the thermomagnetization process.
Excuse me, you have 5 more minutes.
Yeah, 5 minutes, noted. Now, how do we transform these materials to devices? So this is the small concept of triboelectric nanogenerator. So what you all need is you need 2 different materials. One should have a positive layer, the other one should have a negative layer. So when you bring them together, then the charge transfer take place. And if you can repeat that, bringing together and separating them. So you can see here. So these 2 materials, when they brought together, then the charge transfers takes place. And when you separate it, then you can see the current flow takes place and voltage potential difference is generated. Similarly, again, you push back, then they are coming close to it and thereby generating again current signal, so negative way. And thereby, if you keep on moving back and forth by repeated movement, we should be able to generate the voltage potential difference and the current flow between these 2 materials effectively. So this is the idea of triboelectric nanogenerator. So the requirement is how to enhance this performance of this nanoelectric, this nanogenerator by choosing the materials. So a lot of trial and error method happens. So in this particular case, what we do is like, you take this nickel oxide composite with the magnesium, in this particular case, schematic shown, and then you put a copper electrode, and on the other side, you have a kapton, which actually acts as a negative side, and then there's another copper electrode. So you can move this distance back and forth by control way, and thereby you can vary the charge generations between these materials effectively. So either you can, how do we make the motions uniform? So when we do walking, you can see your foot, uniformly steps down and steps up in a proper motion. And thereby, if you can repeat this process, and thereby you can generate the, current and voltage. So this is what we do. So basically, how this voltage is generated by adapting these nanocomposites into that. And then you can see that the voltage generated is more or less uniform, and the current also evolve. And how long these devices are stable, that you can see here, even if you go up to 1500 cycles or so on. So every individual, the motion is quite uniform to generate the electric signal from here. So thereby, we can also check whether this device can be enhanced. So we make devices of different sizes. So if you go by 2 centimeter device, so the voltage is something like 15, this is almost 35 voltage. But if you increase to 3.5, we can increase the voltage to be something like 80 volts or so on. So you can choose the size of the device and then increase the performance of the device accordingly. And then we can see how we can really generate it. So you can either just go by palm pressing. So again, back and forth and see how the signal is generated, or put it inside the chapel. And then you just, take a step process and then see how the voltage is generated. So by optimizing this invariably, or you can add it to spool back, because we often play with the school bag when you were a kid. So you can just bend or walk, or you just do exercise, yogas, like we normally play with, like stretch, bending, all the way you can generate the signal out of it. And obviously the idea is to put it finally on a kind of shoes and so on. So when you walk in, so you just start generating a power to do these powers are very low power. So mostly charging the low power electronics, suppose watches, mobiles, which are low power requirement, and you can do successfully. You don't need any a kind of typical power that you use electricity for charging such devices. And it can be adapted not only here in all the locations, like different remote locations. Suppose, for example, like ATM machines, if somebody steps in, so automatically on the steps you adapt it. It just allows the lights to on and thereby camera on, so can trace it instead of continuous running of power. So all other remote locations like army securities can be used for making them alert, depending on whether a cat jumps or man cross over the barrier and so on. So with that, so the idea is to use nano composites for energy harvesting from the biomechanical activities and looking for kind of applications for the real world in the future. And with that, I thank you for your kind attention, and thanks the SMS team for giving this opportunity to just share the current results. So if somebody is interested, they can look at the publication that happens here mostly. Yeah, thank you very much, ma'am. I'm done with that.
Thank you, Professor Agasami, for your nice talk. The talk is now open for question and answer. Professor Mahendra, can you please ask your question?
Well, thanks, Perumal, for the very nice talk. But I don't understand what is the role of Rayleigh nickel oxide, the composites here.
Okay, so basically composites, you know that they have a lot of defect, which can be oxygen vacancies. So that is the one way of holding these positive charges, which is, you need to create the charge transfers when they come into contact. So people normally use polymers and metals, and these polymers, metals, you need a lot of processing that to take place in order to improve these triboelectrifications. And that is much better in the case of defect-induced nanocomposites. And now if I can play with this in a way of magnetic field, which we are testing it, we are yet to bring it, that whether we can increase the efficiency of these charge generations, that we are looking at it.
Okay, so that is the reason for your choice of nickel oxide, is it?
Yeah, that is the choice of nickel oxide, because iron oxide, it if it goes lower below room temperature, Neal temperature. So that's a problem with that. So the choice of nickel oxide is, so that's
okay. Okay, thanks very much.
Is there any other question? Yeah. Okay. So let us thank once again Professor Agasami. Professor Vedanto, is there anybody to share the memento, virtual memento?
I think there are people just.
So there is a virtual memento. SMS 2021, NICET Bhubaneswar, India takes immense pleasure in presenting the plaque to Professor Perumal Agasami, IIT Guwahati, India, in appreciation for being a valuable speaker to give a lecture on ferromagnetic nanocomposites, the preparation using mechanochemical synthesis, and the exploration towards energy harvesting. Thank you, sir.
Thank you.
Thank you, Perumal. Very nice talk. Yes. I see somebody has raised hand. So I request that we discuss during the next break, which will come just after the talk of Professor Sohail Basu. The speakers are requested to go to the frame platform, and there you can virtually interact. Very nice interactions there. Yeah.
Thank you.
So, we have our next speaker, Professor Sohail Basu. Professor Sohail Basu, are you?
Yeah, I am there. I am here.
Okay. So can you share your screen, please?
Sure. Yeah. Can you see my screen?
Yes, yes, I can see your screen, and you can check that whether you are able to change the slides.
One second.
Can you check it? Yeah. Yes, fine. Yes, fine. Okay.
Yeah, I can.
Let me introduce Professor Sorbal Basu to the audience. Professor Basu has joined as a scientist in Bhabha Atomic Research Center in 1983. His main focus is studying properties of thin magnetic fields using reflectometry. Professor Basu was a Raja Ramanna Fellow and a senior professor at Homi Bhabha National Institute. He has been working in condensed matter research using neutrons for nearly 4 decades. His specific field of interest has been neutron scattering, development of neutron spectrometers, and development of cold neutron sources. He was the leader of neutron beam research at BRC as head of solid-state physics division. He developed the first polarized neutron reflectometer in the country for characterization of thin films. His special interest has been thin films as novel new materials. Presently, his work is heavily in the field of interface magnetism in ferromagnets and superconductors and protons. Professor Basu had worked as a research reactor specialist in International Atomic Energy Agency, Vienna during 2001. He was also a visiting scientist at National Institute for Standards and Technologies Reactor Center during 2005 and 2006. Professor Basu has more than 100 publications. Professor Basu was a board member of Asia Oceania Neutron Scattering Society. Presently, he is a member of the editorial board of Elsevier Journal of Material Science. With this, let me invite Professor Sorbal Basu to present his talk. Over to you, sir. You have 25 minutes for the talk and 5 minutes for question answer.
Thank you, Chairperson. I must thank the organizers at the onsite for giving me this opportunity. I would title it as Characterization of Interface Properties in Ultra-Thin Films, Pathways to Novel Magnetism. Actually, today, specifically that we are talking about the spintronics and magnetism, most of the devices are based on thin films. We all realize, and the fact is that when you create thin films, it is not just a bulk material which has been thinned down, but when you put different layers of a thin film, you create a new material whose behavior and properties you haven't seen in the bulk. And so most of the research today with respect to devices, memory storage devices or other devices are based on thin films. And that way I'm a little lucky to have been working on neutron reflectometry, because this technique helps you to understand the layered structures in a thin film. And I will share with you some of our most recent results that we obtained. I cannot put too many examples, but both of them are, I think, fit candidates for future materials of use. But I would right now discuss the part of characterization that we made. So basically, as I said, that always we are talking about interfaces in thin films. Actually, the interface, the moment I make a multi-layer, and first question comes, what is the crystallographic structure? And what are the bulk and microscopic structure? What is the alloy composition at the interface? What is its magnetism? Last and most important question is the magnetism. Today, the examples that I choose, they will focus more on magnetism, but I will go where we have done the experiment, the way we have gone from bulk to mesoscopic characterization. And for that, I have chosen, my plan of the talk is interface of ferromagnets. Very simple ferromagnets, cobalt and gadolinium. One is a transition metal, other is a rare earth. Both of them are ferromagnets. I will show you the fascinating structure, magnetic structure that we obtained. So we'll start discussing its bulk structure, bulk magnetism, and then we'll get into the layered structure. But before I tell you what I got in the layered structure, I'll very briefly try to introduce you to reflectometry technique, because unless you understand a little bit of the technique, which I'll give you, it is difficult to appreciate the results that we obtain. And another problem which I have been working for last 5-6 years, and we got very fascinating result. I can say a fascinating phenomena, a new proximity effect, that also I'll present to you. So I'll present two sets of results to the audience where we have found novel structures and magnetism in the thin film multilayers. So when, as I told you sometimes back, that interface of A and B is not an average property of the two. It's a new thing. Interface has unique structure, strain, magnetism, and it also dictates the behavior of the A and B layers, which you may not see in bulk. And actually, when I discuss cobalt gadolinium, I'll bring up this point more silly. Like here, I just took an example. I will not discuss this in detail, but all I want to tell you that you see this is a cobalt film. I am just showing you the high resolution transmission electron microscope. This cobalt film, actually at the interfaces, this was an FCC structure, unusual. Cobalt is HCP, but these are the structures at the interfaces. It was grown on a highly clean silicon surface, and you can see that the interfaces, they are FCC. And we reported it earlier. That is not the discussion topic today, but this interface cobalt was actually non-magnetic. So we got a non-magnetic cobalt, which actually you can get under high pressure in this thin film at the interfaces. So this is an example where the interfaces of a thin film can deviate from the bulk behavior and give you very interesting properties. So this is an FCC. So this is one work which we have recently done. This is antisymmetric magnetoresistance. So what I wanted to say, that cobalt, we know it's a three-dimensional magnetical transition element ferromagnet, Curie temperature around 1200 degrees, 1.6 to 1.7 Bohr magnetons per atom. And gadolinium is a rare earth magnet with the Curie temperature around 20 degrees centigrade, 7 micron. So what happens, the question we are asking, what happens to magnetic order in a multi-layer sample of gadolinium cobalt? It is not very easy to answer this question in a layered structure, because it was a challenge actually, because gadolinium and cobalt are both very strong neutron absorbers, and I will show you the fascinating result that we got. So first let me tell you that the gadolinium and cobalt multi-layer was grown on silicon 100 substrate by DC magnetron sputtering. The structure was, the gadolinium was 140 angstrom, cobalt was 70 angstrom, 8 bilayers of that were deposited. So now let's see. First, of course, we went for crystallographic structure measurement. This is the X-ray diffraction. So this X-ray diffraction actually tells you that here the gadolinium was FCC instead of being HCP, and cobalt was HCP. So there is already some difference in the structure, not at the interface, in the gadolinium layer. Bulk magnetism was done, excuse me, and we found it's ferromagnetic overall. This is bulk studies. So at 300, 200, 150, 5K, it's ferromagnetic. But most interestingly, there is exchange bias in this. You can see the shifting of the hysteresis blue. This tells you that the story is deeper than just two ferromagnets being one in contact with other. Interestingly, when you do bulk magnetic measurement, I show you the result here. See, as you go from room temperature to below, the magnetization goes down, then comes up. So it's nearly zero at around 125, 130 K. We call it compensating temperature. So this sort of indicates that there is antiferromagnetic coupling between cobalt and gadolinium. Had it been only this, then it would have been simple, but it's even more interesting. Now I will tell you that we carried out polarized neutron reflectometry on this sample and to determine the magnetic structure in the film. But before I show you the result, it is important to tell you what we get in reflectometry. The fact is, reflectometry, the name itself suggests, just like light rays, you simply reflect either neutrons or X-rays. Actually, X-ray reflectometry and neutron reflectometry are very close to each other, the way they are practiced. So as you can see that it follows for specular reflectivity, it follows the Snell's law. So incident angle equal to the angle of reflection, and this is a Q vector, the momentum transfer vector. As you go to higher and higher angles, you go to larger and larger Q values. And since this Q value is normal to the plane, so you get information further from the depth of the particle. So you get depth resolved information from the film, and how I will come to it later. There is another style of doing reflectometry where your incident angle is not equal to the reflection angle. In that case, you can see that there is a component of the transition transfer vector along the plane of the field. So because you have a vector along the plane of the film, so this data can be used to find out the height correlation function in a plane for a thin film. So this is a very advanced technique where I can say you can quantify the roughness of a surface in terms of height correlation function, and you can even determine whether it has got any fractal structure. But in this talk, I'll just mention this much and stop. My target is only specular. So polarized neutron reflectometry, see, and X-ray reflectometry. Briefly, whenever there is refractive index contrast, reflection of waves take place. It's true for all electromagnetic and neutron waves. So that means if you have a film, you will have reflection from top and reflection from bottom. And when the rays come out in the air, then they will interfere. And this interference pattern is something which you will be recording, and it will give you all the things. So refraction causes bending of rays, and total internal reflection occurs for optical rays. But in case of neutron and X-rays, because the refractive index is marginally less than 1, so you find that there will be total external reflection. How they look, I'll show you. So it's a non-destructive tool for thin film characterization. I can write in a very general statement that refractive index for X-rays and neutron is like n equal to 1 minus delta. This delta is marginally different from 0. It's 10 to the power minus 5, around 10 to the power minus 5 for X-rays, and even smaller for neutrons. So the reflection of neutrons and X-rays, they take place at a grazing incidence at very, very small angles. That is the only difficulty in reflectometry, because then you have to prepare a beam which is very tightly collimated, and you have to present your sample, place your sample at that very, very small angle, and for that typical elaborate alignment processor involved. Otherwise, the experiment is pretty simple. So neutron, the refractive index is 1 minus alpha. I beta, the I beta by beta part is the absorption part. Sorry, absorption part. But in case of neutron, neutron being a very small magnet, apart from the scattering length, which is known as B coherent scattering length, we also have a magnetic scattering length. And that's a very, very positive thing for neutron, because that is the only particle which can detect magnetism through interaction. And actually neutron diffraction is the unique tool for normal magnetic structures you find at microscopic level. But here also in reflectometry, I'll show you, it gives you information about magnetic scattering length. Actually, when we do specular reflectometry, what we get is a scattering length density, or rather we get density of the film from scattering length density. So in case of X-rays, it is electronic scattering length density. In case of neutron, it is coherent scattering length density. And if it is magnetic, then we have magnetic field is applied and we polarize neutron. They also have magnetic scattering length density. So both the techniques give us rosette from the reflectivity data, and we get depth resolved reflectivity data. Now this is in Q space. So it is like any other diffraction experiment. Here we collect the data in Q space and we get back the structure in real space. The Fourier transform is involved, and the Fourier transform is through model fitting, and it is through a model and through chi-square minimization. There are various techniques available. We use something which is based on genetic algorithm which we developed, but there are other conjugate gradient method. So it is like all other scattering experiments. The way you do Rietveld fitting for structure refinement with X-rays, neutrons, we do for reflectometry a similar process, but only the structure is now at a mesoscopic length scale. So moreover, in addition, if you polarize the beam, that means if you polarize the neutron beam, there are ways of doing it. I don't want to discuss that. Then you have structure which is we can have a positive neutron beam and reflected beam also positive. So up, I mean the polarized, let us say parallel to a field applied on the sample, and I get R++. Or I can flip the spin of the neutron beam, make it opposite to the applied field, and I can have reflections with either plus or minus. So I can have plus, minus, minus to plus, minus, plus. So I have, sorry, I have a mistake, minus to minus and minus to plus, I'm sorry. So what happens, in this case, if I can do, that means first I have to polarize the incoming beam, and next I have to apply a field on the sample. Now the thing is, suppose my sample has a magnetization in this direction, which is not exactly aligned with the magnetic field. Then I have two components. One which is along the magnetic field, and polarization of the neutron is also along the magnetic field. And the one which is normal to the magnet. Now you see, now there will be one component which will go unflipped. But if there is a component here, normal component, then the neutron will tend to precede, and then plus will go to minus and minus will go to plus. So I will have spin flip scattering. And if I can do analysis of the scattered beam, then I can find out magnetic structure. What is the in-plane structure of magnetism? And that's how I will present to you. So I just give an example. See, when you do X-ray reflectometry, then you get a data like this. So this is the critical angle. As I told you, total external reflection takes place. And then you have these oscillations. These oscillations are very easy to understand. They are called Kiesig oscillations. They come from the fact that the beam, the X-ray beam, scatters from the top and from bottom of the film, and then they come out and they interfere, and that interference pattern is this. So from this you can fit the thickness of the film. In case of polarized neutrons, here I am not doing analysis of the outgoing beam. I just collect the beam. You see, there is a reflection which is R+, that the polarization is parallel to the sample magnetization. The polarization is anti-parallel or oppositely aligned to the magnetization. Why these two curves are different? Because the potential for the neutron for up polarization and down polarization are different. When the potential is different, that 1 minus delta, what I told you, the delta is different because it was B coherent plus B magnetic or B coherent minus B magnetic. So that is the signature. That's why this is a nickel film for which you will find like this. So this is the strength, and from this we can fit and you can find out the magnetic moment density in that film. So X-ray gives electron scattering length density, and polarized neutrons gives nuclear scattering length density. Both of these can be translated to physical density. But more importantly, we also get magnetic scattering length density from this data, from the polarized neutron data. So that is something which nothing else can give you. So now let me get back to the cobalt gadolinium film. So I made 8 bilayers. If you remember, cobalt 70 angstrom thick and gadolinium 140 angstrom thick. So the first thing what we did was X-ray reflectometry. That is always the case. When you make a sample, you first make X-ray reflectometry, check that the structure is fine. Here we found that you can see we have fitted the data using the technique called Parrott's formalism, and it fits nicely and it gives us a nice multi-layer structure. Also density oscillations between cobalt and gadolinium films. So, but now I will go back to polarized neutron reflectometry. So here I have done R plus plus, R plus minus, R minus plus, R minus minus. So one is the R plus plus data, and one is R minus minus data, and another part is spin flip data. So this 3 data allows me to find out the 2 components of the magnetic moment which are along the field and perpendicular to the field, and combining them, I can get the in-plane magnetic moment. And if I add up R plus plus, R plus minus, I get R plus. If I add up R minus plus, R minus minus, I get R minus. That gives me magnetic moment density. And you can see this magnetic moment density here, which is plotted, which also is periodic at room temperature, because at room temperature, gadolinium is paramagnetic and cobalt is ferromagnetic. So you can see plus 0, and later. But now let us see what structure we got when we did R with spin analysis. This was done at Rutherford Appleton Laboratory of spectrometer. Now you see, first, let me say 300K. At 300K, the structure is very simple, was very simple. Cobalt was ferromagnetic and it is nicely aligned. You can see gadolinium was 0 magnetic moment, average magnetic moment, because it becomes magnetic below 20 degrees centigrade. Then we went to 200 degree. Here, when we went to 200 degree, then cobalt is a ferromagnet, but here.
Dr. excuse me, you have 5 more minutes.
Yeah, 5 more minutes, okay. So, and then I found, I will quickly go to the structure at 125 Kelvin, which is a compensated magnet. Here, we fitted the data, we found that there is a spiral, there's a helical structure, as I show you here in this helical structure is there at 125. So this is unique. Again, when we go down to 5K, we find that the gadolinium moment actually aligns in a helical structure, and cobalt moment is antiferromagnetic coupled to them. So this is a unique structure. I'll just take one more example. This is a superconductor and ferromagnets. What happens in tunneling geometry when superconductor and ferromagnets have an insulating barrier? So this is called proximity effect, because superconductors don't like ferromagnets and ferromagnets kill superconductivity. So I will just quickly tell you, it is an interaction between oxide superconductor and oxide ferromagnet in a tunneling geometry. So what we had actually, we had a sample where on single crystal STO, we deposited YBCO, a tunneling barrier, and an LCMO. What we found that actually the structure is highly textured. You can see the X-ray diffraction pattern. Actually, it's like a one-dimensional pattern which you can fit with sine QD by 2 upon sine NQD by 2 by sine QD by 2, which is there in Kittel. And of course, it is becoming ferromagnet around 125 and superconducting temperature around 60 Kelvin. So here, this R plus and R minus, this was done at FRM Munich. And so you see, we have got several temperature ranges. So below superconducting and below Curie temperature, what we find actually, the moment this YBCO becomes superconducting, it kills the magnetism in this LCMO ferromagnet for an interface layer of 7 nanometer thickness. So this is a very interesting phenomena, a dead layer at 10 Kelvin. And this is whether it is related to superconductivity. We did the experiment at 50K, the dead layer was there, the dead layer was there. This is all from data feed. When you went to 100K, that means we went above the superconducting transition temperature, the dead layer vanished. And it can clearly see from the feeds that it's true. So when we increase the barrier thickness, immediately the dead layer thickness reduced, but it follows the same pattern that always below superconducting transition temperature, we do have a thin magnetic dead layer. We went to another system, which is basically we changed the ferromagnet from LCMO to LSMO and the substrate to single crystal MgO. Even there, that it's highly textured. Actually, this whole phenomena is deeply coupled with the texture in the system. This is a high resolution image for that same X-ray diffraction pattern. And even here, we find that instead of dead, it's almost dead layer, but it's marginally negative. So we feel that because this oxide superconductors, this YBCO, is a P-wave superconductor. So when the Cooper pair, it enters a ferromagnet, possibly that's our guess that the Pauli principle, it aligns it opposite to the magnetism in the system and tries to kill the magnetism at the interface region. So this is something which our group, we claim that we have done it for the first time, that in tunneling geometry, we have been able to show that the superconductor and the ferromagnet, they couple and the interface magnetism get deeply modified due to this interaction. So magnetically depleted layer, you can see. So I have almost come to the end of my talk. So this is basically the data where we show the negative magnetization, marginal negative magnetization at the interface of the insulator and the ferromagnet affected by the Josephson tunneling of the Cooper pairs. All show depleted layers. So you can also use magnetic field. Actually, another group followed our work in Australia, and they found that when they applied large magnetic field, it killed the superconductivity and it restored the magnetic structure in the ferromagnet. The dead layer vanished. So we are pretty sure that it is due to Josephson tunneling. So this phenomena, we say that it is related to Josephson tunneling of Cooper pairs in these oxide heterostructures. And we find that it is strongly depends on structure. So you can tweak the thing by various techniques. Recently, we did irradiation, and irradiation expanded the superconductor and the phenomena vanished. And we also did it on reverse stacking. There also we found the phenomena got affected. So we can tweak this phenomena by playing with the structure. So that's all I had to share with you. That's why the suppression of superconducting proximity effect with ion irradiation, we have done it. So lastly, the work I presented in this through several national and international collaborations, they're all our co-authors. So I individually cannot thank all of them, but they're all our co-workers. I take this opportunity, I dedicate this talk to my colleague and friend, Dr. Champalal Prajapat, who was absolutely instrumental in preparation of all these samples that I worked with and presented to you. He was an excellent experimentalist and he passed away, unfortunately, very recently. I dedicate this talk to him. And I thank you for your kind attention. I am ready to answer your questions.
Thank you, Professor Gulbashu. The talk is now open for question and answer.
Sure.
Is there any question from audience? Yeah.
Okay, maybe I can ask one question.
Oh, sure, please.
Proximity effect. Thank you, by the way, for remembering Champalal. I mean, he was such a wonderful person.
Yes.
I really greatly miss him. Yeah, if you would be alive.
I don't want to leave you in a bad mood, but I think we have to acknowledge his
Definitely.
contribution to this thing.
Yes. Thank you. Very nice talk. I really enjoyed this proximity effect.
Yes.
Do you observe any kind of dead layer in that?
Exactly. Actually, you know, this whole game started with, if you know, Christian Barnard's group. They saw this actually, but there the superconductor and ferromagnets was just side by side. I started this thing around 2014-15. I said, why not in tunneling geometry? We know Josephson tunneling, it happens. And in the very first attempt, we got the dead layer. So when you go below superconducting transition temperature, anyway, the LCMO or LSMO, the ferromagnet, the moment the superconducting layer goes below superconducting transition temperature, immediately the dead layer appears. A magnetic dead layer at the interface. It's quite large, 70 angstrom, 70 angstrom, 50 angstrom, like that. So there are no mistake about that. It's not a tiny, it's quite a thick dead layer.
Yeah, and I think it is the power of PNR that it can reveal the.
Yes,
dead
actually,
layer.
These two examples I gave you because a bit of it is also selling selling agenda that all of you who are working in thin films, this is a unique tool, and because nothing else can give you this kind of, like, for example, that helical structure I showed you in cobalt gadolinium. This is the resolution is each layer is few angstrom thick in that helix that we created. That resolution, you can see the helix is there. There are theoretical predictions, but this is an experimental demonstration of that. Same thing is true for the magnetization profile that you can see here. That magnetization profile.
Yes, yes. Thank you. Thank you. Thank you so much.
Professor Anil Kumar, you may ask your question.
Yeah, please.
Thank you, Professor Saibal. Nice talk. Maybe a slight digression because you didn't touch upon that part. You said that you can do off-specular scattering.
Yeah. Actually,
so are you able to track the spin waves also with this kind of things? Is it possible?
See, this is a structural work. Spin wave is something which is dynamics. Okay. So for that, if you want to see spin waves, you have to really go to a single crystal. People do it. Some of our people have done it, and you have to go at low temperature and measure magnons or spin waves. But if there is a static structure or static distribution of spins in a layer, that is possible to, it is possible to do. Actually, I had shown that. Actually, in a paper, we showed that in nickel, the physical roughness and the magnetic roughness. Actually, there's a magnetic, the assumption is that there's a magnetic dead layer right at the surface. And there the spins, you can do it with polarized off-specular, and we did that. So it is possible to see, but it has to be a structural work. Spin waves are something which is dynamic. If there's a spin arrangement, then yes, you can see that with off-specular.
Okay, thank you.
Okay, I have one question.
Please.
Yes. So you are looking at the reflected beam, right? So is it possible to gather some information from transmitted beam in this case?
No, this is reflection.
This is reflection.
This is reflection. You see, transmitted beam, for example, suppose you have some, suppose there are some conglomerations inside your sample. Small angle neutron scattering does that.
Yeah.
You measure the transmitted beam and you have inhomogeneities which are of various size. You measure the size, form factor, correlation, everything. But here, the primary phenomena that you are seeing is actually reflection of the beam.
And for just to add, like for thin films, you can do grazing incidence, small angle neutron scattering.
Yes. That's a fantastic technique. Yes.
Yeah.
You can do GI sans. Yes, this has been done recently.
Yes.
Actually, right now I was attending one conference on neutron scattering. Somebody presented very interesting data. This grazing incidence data at slightly different grazing incidence angle. So you go to slightly deeper and you can see the domain or rather structures, two-dimensional structures there. Yes, you can see.
Yeah. During my postdoc time in ULIS, I did G-SANS experiment in Munich.
Exactly.
So depending on the length scale, you choose if PNR to be done or G-SANS to be done.
Yes, exactly. Exactly.
Okay, thank you so much. So
Welcome.
I think it's time. Yeah, Professor Borman, kindly present the.
Yes, yes, please. Kindly share the screen.
Yeah.
Let me read it out. It's a virtual memento. SMS 2021. Niger Bhubaneswar, India takes immense pleasure in presenting the plug to Professor Shoibal Basu, BRC, Mumbai, India, in appreciation for being a valuable speaker to give a lecture on characterization of interface properties in ultra-thin films, pathway to Nobel magnetism. Thank you, sir.
Thank you so much.
Thanks a lot.
Thank you so much.
Organizers. Bye.
Abhishek, kindly share this memento for Professor Borman. Yeah, so I think it's very nice that we still have 15 minutes as a regular break. Otherwise, all the breaks were getting merged. So I take really immense pleasure in presenting this plaque to Professor Saswati Borman on behalf of the Symposium on Magnetism and Spintronics and Nisar Bhubaneswar for chairing a session, the session 10, which went very well. Many thanks to all the three speakers, really great talks, and Professor Borman for your kind hosting of the session. So we will break now for 15 minutes. So thank you so much, Professor Borman.
Thank you.
We will now break for 15 minutes, and I request all the three speakers, if possible, to go to the frame platform now.
Okay.
Because there were some questions and probably there will be more questions.
Okay.
And we can interact there, and then at 8 o'clock we return, and there is a very exciting talk by Professor Ashwin Tulapurkar from IIT Bombay. Thank you so much, all of you. See you in 15 minutes here. Professor Basu, could you, yeah, you have already muted. Thank you so much. Thank you. Okay, Oswin, Oswin, you are already there. Oswin, can you kindly share your screen?
Yes, yeah, sure. Can you hear me?
Yes, I can hear you, but I cannot see you.
Okay.
Yeah, very nice to see you.
Very nice to see you too.
Yes. How are you?
Yeah, good, good. How are you?
Yeah, okay. A little bit tired.
Yeah, sure. Okay,
So,
I'll start
I
sharing
think
the
you are
screen.
co-host, so you should be able to share your screen.
Okay, now where is the share screen?
At the bottom of the screen, you see a green tab, share screen.
Ah, okay, yeah. Okay.
Yes. Could you kindly make it full screen and just toggle 1, 2 slides. Let's see it is possible or not. Yes, okay. It's fine. So I think we can start now. It's already 2 minutes past 8. So good evening, everyone. To the last session of this conference, not least. After this, we have a small discussion about the future of SMS. And I'm really glad to introduce Professor Ashwin Tulapurkar, who is a very well-known scientist in the field of Spintronics, one of the very few in India who actually does Spintronics. And I think you know him, but still for the benefit of the community, I will just read his credentials. Professor Tulapurkar is presently a full professor at Department of Electrical Engineering at IIT Bombay in India. He has received his PhD from Tata Institute of Fundamental Research, well known as TIFR, in Mumbai in 1999. He then worked as a postdoctoral fellow at the National Institute for Advanced Industrial Science and Technology, that is AIST Japan, as well as at Stanford Linear Accelerator Center, USA, and Osaka University in Japan. His major research interests are spintronics, quantum physics of nano devices, spin torques, spin-based oscillators, noise, thermoelectric effects, etc. So, Ashwin, I will give a small reminder at the end of 20 minutes so that you know that in next 5 minutes you have to wrap up.
Yeah,
and
sure.
we
Yeah.
will have some discussion at the end. Okay.
Yeah,
Thank
sure.
you, Ashwin.
Yeah.
It's all yours.
Yeah. So thank you, Professor Shubhankar, and also the entire team for inviting me here. So it's a very nice symposium that you've organized, and I'm happy to be part of it. Okay, so I am going to give the last talk in the symposium. So I'm going to be the last batsman today. And normally the spinners come to bat at the end. So I guess I am coming to bat at the end. Okay, so I am going to talk about how to generate charge current from oscillations of magnetization. And now we know that if we have magnetization which is oscillating, then by Faraday's law of electromagnetic induction, we can create charge current. So this is one way, and I'm going to talk about some other way by which we can generate charge current from oscillating magnetization. And this work was done in collaboration with AIST Japan. So this first 4 people here are the students from IIT Bombay, and remaining are researchers from AIST. Okay, so the outline of my talk would be as follows. I will start with some introduction to how we can control magnetization. I will talk about the reciprocal effects in spintronics and how we can measure them, and then I will talk about the reciprocal of voltage control of magnetic anisotropy. Okay, so this is a standard slide when we talk about dynamics of magnetization. So if you apply magnetic field to magnetic moment, it starts precessing. And this is the first term on the right hand side. And along with the precession, it also undergoes damping, because of which it stops precessing. So this is the second term. And in 1996, a new term was introduced by Sonjowski and Berger, which is called as spin transfer torque. And this term IS here is the spin current. So if we have spin current in the system, then we get this extra term, which is called as spin transfer torque. And by using this, you can switch magnetization or control the magnetization. Okay, so now the question is that how we can generate spin current, and there are various ways by which we can generate spin current. A simple way is that if you have a magnetic terminal junction, then you can apply a voltage across it, and then this creates a charge current, and the charge current flowing through this spin layer creates a spin current, which is absorbed by the free layer, and then the free layer can be switched. Okay. Other way is that we can use heat effect. So we can use what is called as a spin dependent Seebeck effect. So what we can do is we can maintain the free layer and the spin layer at two different temperatures, and this temperature difference creates a spin current, and again this spin current will be absorbed by the free layer, and then we can control its magnetization. Now apart from that, there are also other ways by which we can generate spin current, and in fact one of the most popular ways of generating spin current is by using what is called a spin Hall effect, and this is shown schematically here. So we have a thin film of heavy metal like platinum or tungsten, and on this we have a nanomagnet which could be part of a magnetic terminal junction. And now when we pass charge current through platinum, this creates spin current because of the spin Hall effect, and then this spin current is absorbed by the free layer, and we can control the magnetization of the free layer. Now, just like in the last slide, I showed you that we can use the heat effect. Now, a similar thing also applies here. So what I can do is I can create a temperature gradient in the platinum. Now, this temperature gradient also can create a spin current. Now, this is called as a spin nest effect. And again, this spin current would be then absorbed by the nanomagnet, and we can switch it. So apart from that, we can also control magnetization by various other ways. For example, we can use strain. And so the way this works is the following, that if we have a piezoelectric material and on which if we have a nanomagnet, then by applying a voltage, we can create strain, and then this is coupled to the magnetization via magnetoelastic effect, and then we can change the anisotropy of this magnet, and then this can be used for switching. So I'm talking about various ways of switching because switching or the control of magnetization is very important from the device point of view. You can make magnetic memories based on it. You can make logic elements, and you can also make oscillators and so on. So it's very important that we find out different ways of controlling the magnetization. Now, I'm going to now talk about a different way of controlling magnetization, which is called as voltage control of magnetic anisotropy, or VCMA in short. And this effect was discovered in 2007 by this group here, and they used a liquid electrolyte to apply an electric field across a ferromagnet and insulator, and then they could change the anisotropy of the ferromagnet. Now, this effect was demonstrated in the case of magnetic terminal junctions in 2009 by a group from Osaka University, and this is a picture from their paper. So they fabricated structure as shown here. So here we have ferromagnet, a very thin ferromagnet of iron, about 2 to 4 monolayers, and then we have a MgO insulator. And when they applied a voltage across this multilayer, they found that they could control the anisotropy of the ferromagnet. So this is what is shown in the figure here. So if we apply positive voltage, then the anisotropy increases, and if you apply negative voltage, then the anisotropy decreases. And this happens because at the interface of the ferromagnet and the insulator, the electric field penetrates slightly into the ferromagnet, and then we can control the electronic occupations of various orbitals, and this changes the magnetic anisotropy. Okay, somehow my slides are frozen. Okay. Now the way this works is the following. So I will start with the LLG equation that I showed you before. Now here there is no spin current. So all we have are these magnetic fields, and this magnetic field I am called here as effective magnetic field, which consists of the external field and the anisotropy field. So these two terms here, which have H parallel and H perpendicular, denote the anisotropy field. And if we take the H parallel and H perpendicular as positive constants, then that would mean that the x-axis is the z-axis, okay, and the z-axis is going to be the out of plane hard axis. So this is the convention I have chosen here. And now when we apply a voltage across a layer of ferromagnet and insulator, then what happens is that we can control this parameter H perpendicular, which is out of plane anisotropy. So we can assume a linear relationship. So if I apply a voltage, then I can linearly shift the anisotropy constant here. Okay, so if I apply positive voltage, it can increase. If I apply negative voltage, it can decrease. Now this is called as VCMA effect. And so essentially what we are doing is we are changing by applying voltage the effective field that a magnetization feeds. So now apart from using it to switch magnetization, one can also use it to control the magnetization in a coherent way. So this is what was shown by again the same group from Japan, and this is a picture from their paper. So they fabricated a tunnel junction, and across this tunnel junction they applied an oscillating voltage. Now when we apply the voltage, there is going to be spin current, but the spin current in this experiment was negligible. So the main effect comes from the VCMA effect, and because of this oscillating effective field, the free layer here undergoes oscillations, and this creates voltage by the spin transfer by the torque effect. Okay, so this is what is shown here. So if you record this as a function of frequency, you will see this spectra have peaks at different values of magnetic fields. So this shows that we can use the VCMA effect for coherent control of magnetization. Okay, so now we have seen that there are various effects in spintronics, and all these effects also have a reciprocal effect. So for example, if you look at the spin transfer torque effect, so this is shown schematically here. So what we have is an injected spin current, and because of this, the magnetization starts to rotate. Now the reciprocal of this is spin pumping. So if the magnetization is oscillating, then this pumps a spin current. Okay, so the spin transfer torque and the spin pumping are reciprocal of each other. Now similarly, the spin Hall effect and the inverse spin Hall effect are the reciprocal effects of each other. So here you can see that if I pass a charge current through, let's say, platinum, then I create a spin current in the transfer direction. And if I reverse the scenario, if I pass the spin current, then I can generate charge current. So this is the inverse spin Hall effect. So all the effects always comes in the reciprocal pairs, and this is called as Onsager reciprocity. So for example, for spin Seebeck effect, we have spin Peltier effect. For Rashba-Ellison effect, we have inverse of that. For spin Nuss effect, we have spin Peltier effect. For magnetostriction, we have inverse magnetostriction, and so on. So now the question that we had was that we also have a VCMA effect, and what would be an inverse of this effect, and how would you measure such an effect? Okay, so this was our goal, and for this we fabricated a multi-layer, which is shown here. So you can see it consists of many layers, but you can focus on a ferromagnetic layer here, which is about 1.2 nanometer, and then insulator MgO, which is about 2.4 nanometer. And note that in this stack we have only one ferromagnet. So this is not a stack which is used for magnetic tunnel junctions where we have two ferromagnets, but in this stack we have only one ferromagnet. Now, as a first step, what we did was we characterized this ferromagnetic layer. So we measured the ferromagnetic resonance, and the absorption spectrum is shown here as a function of magnetic field. And you can see that we could fit this nicely to LHC equation. Then we also measured this resonance field as a function of angle. And again, you can see that in the inset, we could fit this nicely to what is expected from LHC equation. And from this, we could estimate the various parameters like gyromagnetic ratio. The damping constant came out to be 0.03. And the perpendicular anisotropy we found out is 400 Oersted. So typically, if you take a very thin film, then the perpendicular anisotropy is very large. It is almost same as the magnetization. So it could be, let's say, 10 kilo-Oersted. But in this case, because of this thin film in contact with MgO, the anisotropy reduces. And though the film is magnetized in plane, the out of plane anisotropy is very small, only 400 Oersted. That means by applying a small field, I can change the magnetization from in plane to out of plane. Okay, so then to measure this inverse VCMA effect, we fabricated pillars of this film as shown here. And the pillars are of dimension 3 by 80 micron. So you can see it's a very elongated pillar. And so here I have shown you only the MgO and the ferromagnetic layer. And this pillar, we have now a top contact and a bottom contact. Okay, so this is what we will call as a port 1. Then on top of that, we deposited insulator shown by this faint color here. And on the top, we deposited a waveguide. So this I will call as a port 2. Okay, so what we are going to do is we are essentially going to connect a network analyzer here. And then we are going to measure the various parameters. But as a first step, we need to make sure that the VCME effect is present in this film. So what we have essentially done is we simply use the port 2 and measure the reflection from this port. And this data is shown here. So if we freeze the frequency and change the magnetic field, then you can see a peak in the absorption. Now this creates this essentially comes from the ferromagnetic resonance excited in the ferromagnet by the magnetic field created by the waveguide here. And then we use the port 1 to apply a DC voltage across this multilayer. And then we saw that the peak frequency shifts as a function of voltage. So if we apply a negative voltage, then the peak goes on a higher magnetic field. If we apply negative voltage, then the peak goes to lower magnetic field. So in fact, as a function of magnetic field, we measure this peak position and we found out a linear relationship. Now this shows that we have VCME effect because when we apply voltage, we change the anisotropy, and because of that, the resonant magnetic field also changes. So this is the proof of the fact that we have VCME effect in our sample. And we estimated this VCME coefficient from this linear slope to be about 100 femtojoule per voltmeter. And of course, we can also estimate all of the parameters, okay, from this data. Then in the next step, we measured the scattering parameters S21 and S12. So let's see what is the meaning of S21. So when we measure S21, what we are doing is we are applying a signal to port 1, or the excitation is applied to port 1, and then we see how much signal is transmitted to port 2. So when we apply an oscillating voltage to port 1, what we do is we excite the magnetization by the VCME effect. Now, once the magnetization starts to oscillate, this induces a voltage in port 2 because of the inductive coupling. Okay, so that's how we get S21 signal. Now, if you look at the S12 measurement, what we do is we apply a voltage to oscillating voltage to port 2. So now if you apply an oscillating voltage to port 2, this is going to create oscillating current here, and then this current is going to excite the magnetization by the oscillate field. So this is the first step here. Now once the magnetization is excited, now this creates a charge current by the inverse VCME effect, and this is what is detected in the port 1. Okay, so you can see also these arrows that when I go from S21 to S12, essentially I reverse all the steps. So here the first step was excitation of magnetization by VCME, and if I go to S12, then this becomes the inverse detection by inverse VCME effect. Similarly, step 2 here was inductive detection in port 2, where the step 1 here is inverse of that, which is excitation of magnetization by oscillate magnetic field. Okay, so essentially by using this kind of a sample, we can measure the inverse VCME effect, and these are the results of our measurement. So what we have done is we applied magnetic field in the ZX plane as well as in the ZY plane. So this shows what happens if we apply the magnetic field in the ZX plane. So in this case, we saw these kind of symmetric signals in S12 and S21. So essentially S12 of H is same as S12 of minus H. Okay, so it's a very symmetric signal. And then as a function of this angle theta, we also measured the amplitude of this. And the amplitude shows this kind of a peak here. So I will talk about why we see this peak in the later part. And then we applied the magnetic field in the YZ plane. Okay. And when we did the measurements in this geometry, we found out that the S12 and S21 now have opposite symmetry. So now they're anti-symmetric with respect to H. But whatever is the case, in both the cases, if we invert the magnetic field, then the S12 and S21 are same. So what it means is that in both the cases, if I invert magnetization and if I invert the magnetic field, then S12 and S21 are same. Now this is what is called a generalized Onsager reciprocity. Okay? And this must be followed in all the cases, and this indeed is followed here. So now in our experiment, you can see that we have only one ferromagnetic layer. So there is no question of any effect of spin transfer torque. So this is ruled out. Now there can be some contribution from the Oersted magnetic field, and this can be ruled out from this data. Okay, so essentially, if you look at the angular dependence of this effect and the fact that this changes sign here, this cannot be explained by using Oersted magnetic field. So that also can be ruled out. So let's see how we can understand this effect. So one way to understand this inverse VCMA effect is to use thermodynamic arguments. So let me go through these arguments here. So what you can do is you can look at the thermodynamic potential for unit volume of a ferromagnet. And in this case, because we have VCMA effect, we have this coupling coefficient lambda, the electric field, and the magnetization directions. Okay, so in general, this lambda is going to be a third rank tensor. And if you want to find out the effective field, then what you can do is you can take derivative of this potential by magnetization. And then this is exactly what VCMA effect is. But of course, in our case, we don't have such a third rank tensor, but we simply have one parameter lambda. So we can represent this potential simply as electric field along z direction into mz square. And then this is the effective field, okay, that we have used in our analysis. Now, instead of taking the derivative by magnetization, you can also take the derivative by electric field. And if you do that, then you will get this D, okay, the displacement D. Okay, so you can simply take derivative of this by instead of magnetization by electric field. And when we take this derivative, we have to be careful. So we need to multiply by a factor of the ratio of these two thicknesses, because when we take this derivative, we should take the derivative per unit volume of ferromagnet. Okay, so that's why we need to also introduce such a factor here. And once we get this D, we can take its derivative by time, and that gives us the current density. Okay, and if you now multiply this current density by area, you will essentially get the charge current. Okay, so now we can make a simple model of the inverse VCMA effect. So in this cartoon, what I have shown is the magnetization which is oscillating, and this is in contact with an insulator, and then we have two metallic contacts. So I can represent this by a current source where the current is given by the expression here, and plus we have this internal resistance of the terminal junction and capacitor. So we can use this kind of a circuit model to represent the inverse VCMA effect. Now, if you look at this expression, you can see that this depends upon the change of magnetization. So if I change the magnetization, let's say from 0 to 1, okay, I can integrate this out and I can find out the total current. And now this charge, which is generated, which will be stored in the capacitor. So this is the charge which will be stored in the capacitor. And of course, we have a resistor, and because of which this charge is going to decay. But if you can make a junction with very large thickness of MTO, then it is possible to observe this charge, and then this can be used to measure the inverse VCMA effect. So we are still working on this kind of observation. Now, if you look at this S12, it is not difficult to calculate it. So if you look at S12, it essentially comes from the direct VCMA effect and then the inductive pickup. Okay, so this is not difficult to analyze, and you can see the details in our paper. But essentially, this simple calculation shows that this S21 has this kind of an angular dependence. Okay, here I have a term of sine theta into cos theta, which comes from the factor here, and plus I have some term which also involves the phi. Okay, so if I take the XZ case where the phi was 0, then this S21 is simply sine theta and cos theta product. So this is symmetry. If I apply magnetic field in the YZ plane, where phi is pi by 2, then I get a more factor of sine theta into cos theta. So then this becomes anti-symmetry. So you can see that the data that we have observed clearly follows this trend. So we can clearly rule out the effect of any Oersted magnetic field in our experiment. And also you can see that this sin theta cos theta dependence gives us a peak at certain value of theta. So this is also exactly what we have seen. Okay, so now we have seen that we can explain this or expect this inverse VCMA effect based on the thermodynamic argument, but there is one more way by which we can get this effect. So what we can do is we can look at the dissipation which comes from the VCMA effect. So let's look at this. So suppose I have this tunnel junction, which I have shown by the resistor here, and then I have voltage wave which is incident on it. Now, because of this resistor, this wave will be reflected back. So this is our usual reflection of the waves. But now what happens is that because of the VCMA effect, the magnetization is going to oscillate, and because of the damping, it is going to have some dissipation. So then what I should do is I should also include the effect of this dissipation. So I'm going to include one more resistor in parallel to this MTJ, which I will call as Z magnetic. And this Z magnetic we can estimate from this expression here. So this shows you how the energy dissipation occurs. So this is proportional to damping constant into square of dm by dt. Now by using the VCMA effect, we can find out this these terms, and then we can find out this dE by dt, and this is related to the real part of this resistance, okay, because that's what gives rise to the dissipation. And so once we get the real part of this, once we get the real part, then the imaginary part is simply, yeah.
Ashwin, maybe 2-3 minutes.
Yeah, sure, yeah.
Thank you.
So once we get this real part, then we can use the Hilbert transform, and then we can get the imaginary part. Okay, so from this we can also get this inverse VCMA effect, and essentially what we find that it is exactly same. Okay, whether we derive it from the thermodynamic arguments or from this. And okay, so this is what I had shown you before, that we have tunnel junction resistance, and in parallel we have this magnetic resistance. And what we want to do is actually, replace this magnetic resistance. We want to get rid of it and replace it by a voltage source and the resistance of the MTJ here. And this voltage source should be chosen in such a way that we get the same reflected wave. Okay, and if you do that, this is how we get the circuit model that I have shown you before. Okay. And I talked about in the previous slide of one port measurement. Of course, we are doing 2-port measurement. So what we can do is a similar trick here. So we want to get rid of this Y magnetic, and instead of showing a voltage source, I can also use a current source. Okay, so this current source is shown here. So this is the meaning of this model. Okay, so what we are doing is we are trying to get rid of this Y magnetic and then use a current source, which will take care of the reflected wave. Okay, so let's look at what could be possible applications of the inverse VCMA effect. So by this effect, what we are achieving is that we are achieving the charge current from oscillating magnetization. So now this could be a new probe for magnetization dynamics. So typically, if you want to detect magnetization, what we do is we use TMR effect, but that requires two magnetizations. Also, it requires a bias current. But if we use the inverse VCMA effect, we just need one magnetic layer. Okay, so this is advantage. And also this inverse VCMA effect can also affect spin wave propagation or domain wall motion in a ferromagnet. So suppose we have a spin wave which is propagating here, and on the top we have MgO. Then because of this oscillating magnetization, this is going to inject a charge current into this MgO, and then there is going to be a back action, okay, because of the inverse VCMA effect. So this can affect the spin wave propagation and also domain wall motion. Okay, so this is our conjecture, and we still need to verify that. Okay, so with this, I will summarize my talk. So in this talk, I talked about this inverse of VCMA effect, and this is the sample that we fabricated. Okay, so essentially, whenever we want to measure an inverse effect, what we can always do is we can make a 2-port sample. And if we measure the transmission from port 1 to port 2 and port 2 to port 1, that gives us a pair of inverse effects. Okay, so that's what we have done here. And our final picture is that this inverse VCMA effect we can represent by a circuit model as shown here. Yeah, so with this, I will stop here and thank you once again for inviting me here, and thank you for your attention.
Yeah, thank you so much, Swin. Really very interesting work, and congratulations for these nice papers in Science Advance.
Thank you.
So the talk is now open for discussions. Any questions? You may Saugata, please go ahead.
Professor Ashwin, very nice talk. I really enjoyed it. This is not a question related to this work, but in general, so to say. Can you please comment, like if we want to achieve, let's say, domain wall dynamics or spin wave propagation, as you say, how does this voltage controlled approach scales with the typical current induced approach? Like how much power consumption wise, like which one is better? Can you comment on this aspect a bit, please?
Okay, so I'm not really I think there are many other people in the audience who can maybe answer your question. So so typically what people do is people use VCMA effect, and then they control the spin wave propagation. And I think there are many people in the audience who can really answer this question. But what I'm pointing out here is the effect of the inverse VCMA effect. Okay, so normally we only take into account the VCMA effect, but that effect also has a back action, and which should be taken into account if you want to do a proper calculation. Okay, so this is the point of doing here, but I really can't comment about which is more efficient for controlling spin waves, whether the spin current or VCMA.
Okay,
so maybe you can ask Professor Anjan Burman. I think he has very nice papers on this. So if he is in the audience, probably he can also comment.
Okay, maybe.
Yeah, Oshin.
Yeah.
Anjan here. Yeah, nice talk.
Yes.
Yeah, just I had a question. Like, there can be. I mean, I don't know whether you have looked into. There can be other effects which can sort of introduce some sort of a non-reciprocity in the spin wave propagation in here. So, how do you actually take into account of those non-reciprocity before you actually can show the reciprocity in this case?
No, but I think whatever it is, we need to follow the Onsager reciprocity. Right?
No,
I mean,
I
as long
understand.
as,
like, for example, if you have a DMI, for example, so that will sort of can introduce a non-reciprocity in the spin wave propagation here, for example.
No, but I think, but if you invert all the magnetizations and magnetic field, it will still satisfy this generalized reciprocity.
Yeah, I mean, ideally, yes.
No, I mean, it should, it has to, because see, even if you look at now the Faraday effect, so we have this kind of a non-reciprocity that if the, I mean, if you simply reverse the direction of propagation, the rotation of polarization is different, right?
Right.
If you simply look at the usual Faraday effect in a magnetic material, but again, but it's still a generalized reciprocity is still there. Okay, if you reverse all the magnetizations, then okay, let me just slide this.
No, I understand your point.
So this
yes.
relation, this relation has to be satisfied. So whatever. So now this is a transmission here. So if I have transmission from 2 to 1 or 1 to 2, if I reverse all the magnetizations and magnetic fields, you should get the same transmission.
Yes, I understand this. Theoretically, absolutely fine. But let's say you have some sort of surface anisotropy or something where you actually fall into local minima due to some defects or something. And even if you reverse the field and magnetization, it does not really, sort of reverse everything.
Correct. Yeah. Yes.
So I'm asking about those kind of non-idealities.
Correct. Yeah.
I mean, this reciprocity will probably break down to some extent, right?
Yeah. So essentially, you're not applying a high enough field to reverse everything. Yeah. So that's right.
So in your case, of course, it is fine, absolutely. But I was just wondering that in general, I mean, when one measures such effects, inverse effects, then these kind of things should be also taken into account.
Yeah, absolutely. Yeah. So essentially, what you're saying is that if I have a pinned layer in somewhere in the picture, and I'm not applying field high enough to reverse that.
Right.
Okay. So yeah. So it's something like that. So
yeah, something like that.
Yeah. So definitely, then we need to take into account that we are not reversing everything. So then this kind of relationship will not hold.
Right.
Yeah.
Okay.
Thank you, Ananda. Chandra, please.
Thank you, Professor Ashwin. Wonderful talk. I really thoroughly enjoyed. I just want to ask a stupid question. Today, the first talk was telling you that in a ferromagnetic material, there can be kind of inverse pinhole effect on its own. So, would it be because of the spin-orbit coupling of the cobalt iron boron is inducing this voltage?
So in our case, you're saying, or
yeah, in this case, what my question is that should we take into account the spin-orbit coupling of the ferromagnetic material itself, like Professor Seki has presented in permalloy, you would be able to get an inverse pinhole effect without having any heavy metal capping, without having any interface. Permalloy itself can generate some kind of inverse pinhole effect. So maybe I think I'm not looking at the voltage directions properly, but I just wanted to wanted you to comment on that.
Yeah. So I think even previously, there are papers that if you take, let's say, a GMR stack, so you have a free layer and a pin layer. Okay, and there also, you can see the spin current generated by the fixed layer. So typically, when we measure this spin Hall effect, we have ferromagnet and some heavy metal like platinum. But now, if you replace this platinum by a fixed layer, for example, if you have a GMR stack, then you can see the same kind of effect. So indeed, a ferromagnet can also generate a spin current. So is that your question? Yeah. So a ferromagnet can
that is spin polarized current, right? The ferromagnet, that whatever it is generating is spin polarized current, but not the pure spin current, right?
So few years back we had done this experiment on JMR stack. So we had same as I was discussing, that a free layer and a pin layer, and we passed charge current and we measured the ST-FMR on that, and we found out that this pin layer also works as a source of spin current. And so I don't know whether this is something similar, but I need to see Seki's work.
Yeah, thank you.
Okay, maybe the very last quick question by Pranava.
No, I have no question. I was just commenting on what Chandrasekhar was asking. Actually, that effect requires the current in the plane, whereas what Ashwin's work is actually current going out in the perpendicular. So I don't think here one can have.
Yeah, thank you, Pranav. Yeah, that's what I was thinking, that there could be something I'm missing, the direction. So yeah, thank you. Now I got it.
Yeah.
And also the charge current is very small. Okay, in this case, because we have a tunnel barrier, so the total current that flows is actually very small. So even if you look at this experiment, yeah. So even in this experiment, the total charge current is very small because of this larger tunnel barrier. So the effect comes from the VCMA effect.
Yeah, I got it.
Yeah.
Thank you. Thank you, Mudli. Thank you.
Okay, thank you.
Yes, thank you.
I think if there are more questions, you can always reach Ashwin via email. It's getting a little bit delayed, and 3 days of continuous talks. But excellent talk, Ashwin. We really thoroughly enjoyed. Very nice work.
Yes. Thank you. Thank you again.
Yes. So kindly stop sharing and team SMS. Yeah, obviously, thank you. So we have a small memento to present you. Symposium on Magnetism Spintronics. Nice, sir. Takes immense pleasure in presenting this plaque to Professor Ashwin Tulapurkar from IIT Mumbai. In appreciation for being a valuable speaker to give this nice work. Thank you so much, Ashwin. On behalf of the organizing committee, I have the pleasure to present you.
Yeah.
So the scientific talks are finished. We have now the concluding session. So I formally start that. Pranav, I request you to lower your hand in the next session if somebody wants to speak. Thank you. I would probably request a few of the colleagues, senior colleagues, to give their views. But before that, I like to, although Professor Anjan Burman has given a formal vote of thanks on the inauguration ceremony, but I just like to add. Somebody is switched. Ashwin, could you kindly mute your microphone? Okay, thank you.
So I was muted only. Okay, I'll mute.
Yes, thanks. So I just want to thank actually my excellent, very dynamic team of volunteers. I'm really grateful to them. So I request all the volunteers to switch on their camera just for 10 seconds. We will take a screenshot, and on behalf of all the participants, I like to thank you. Actually, there were like 15-20 people, all volunteers in each poster room, then organizing abstracts, all those things. So online conference is also, I would say, quite cumbersome. It's not as simple as it seems. Do we have all the volunteers switched on their camera? Yeah. So please all switch on your camera quickly. We don't have much time. We have still business to do. And I request some of the volunteers to take some screenshots. Okay. All right. So take a screenshot now. Okay. I think it's done. Tamabna is done.
Yes, sir.
Okay, we can now switch off your. Okay, I think it's a good occasion. I request all the participants now to switch on their camera. We take a group photo, and then we can have some discussions, useful discussions actually. Okay, great. So Tamagno, please take as many pictures you want, and make sure you see everyone. Smile. Tamagno, have you taken all the windows, all the people?
Yes, sir.
Okay, great. So I request all of you to switch off your video and audio. Once I request, then you kindly unmute and switch on your camera to say a few words. So let me begin by thanking our NICER administration, then the core committee consisting of Professor Anjan Burman, Professor Anil Kumar, Professor Ashwin Tulapurkar, Professor Chandrasekhar Murapaka, Professor Pranav Muduli, and Professor Perumal. We have just started with a small committee, but I'm sure more people will join in, and we can organize this conference from time to time, which every 2 years at different places. That we will discuss. That's one of the agenda item. I like to thank also the local organizing committee, and my sincere thanks to all the speakers for presenting excellent talks. And I also want to thank all the participants for taking the trouble of attending all these lengthy sessions. Particularly the Indian participants have been wonderful because it is always 10 p.m. And I see Professor Maiti sitting there very late, although he has some health issues. I really appreciate Kaloda. I really thank for all of you for joining and participating and interacting, making the conference a great success. And the volunteers, of course. Now, I like to have some feedback, input, suggestions, critique, whatever. so that we can improve. This is a very new idea of bringing magnetism and spintronics together, and how we should look forward in next years. In India, the spintronics community is not very large, although the magnetism community is very strong. And how we should look at it in future, that is actually some idea. I like to first request Professor Kliman. I think he is the senior most person here. And if you could kindly unmute and switch on your camera, Wolfgang, and say a few words about the conference, your suggestions, input, that would be very nice. So all yours, Wolfgang. Wolfgang, we cannot hear you. I think we had the same issue yesterday. You please try. No, I think maybe because you are using a headset, something is wrong with this. Maybe you can remove the thing and directly use the inbuilt microphone of the laptop. It also works. Yes, we hear you now. Fantastic.
Can you hear me?
Yes, perfectly. Please go ahead.
Oh, I'm relieved.
Thank you.
Much easier to work without that. I wasn't sure. So you can hear me, you can see me, and I'm deeply honored to get the words now as a first. So I was the first to give a talk, and now something like the last. And well, I enjoyed very much these 3 days, which were filled with novel and partly unexpected results in magnetics and spintronics. It doesn't make sense to go through all points, but maybe the program which we enjoyed today. So the last talk was, for me, it was like finding a missing link in the direct and indirect or reciprocal or inverse effects in spintronics, and it looked very convincing. Maybe it is very new, but I congratulate Ashwin Tulapurkar for this wonderful talk. It is, for me, it was quite convincing. In the morning, we started with partly novel and unexpected results. Not so much in Takeshi Seki's talk. It was a clear talk on a favorite subject, and I enjoyed it spontaneously. The next talk of Susana Cardoso surprised me a little bit, because it was much more complex than in our common work, which we had 10 years ago. I talked about that in my talk. It was the supermagnetism and the connected subjects. Here, I was surprised how technology, improvement of the sensor technique, how much it takes in energy and practice. So I must say I did not understand all these things which are connected with these stacks of multi-layers in order to get an optimized spintronic sensor. But they are professionals and they will do it. Chandrasekhar's talk, I think this was a highlight in magnetochemistry. This was very clear and I enjoyed it very much. I think you did also. And also the talk, after some technical problems with the system, Arad Shelvani talked about magneto-extractive materials, which was very essential, and I found it just filling the gap. And then we had Dr. Bixi Su, so it's a Chinese name, neutron scattering from correlated topological materials. This was a very involved and very well-focused talk on advanced neutron technology in magnetism. So this was the first session. The second session contained also novel and partly surprising interfacial physics. So focused on the perpendicular magnetized system, the spin orbit torque efficiency of Anil Kumar. I think this was also in the focus of the meeting, and I appreciated that. And wait a minute. Yeah, Perumal Alagasami talked about ferromagnetic nanocomposites using this magnetical technique. This was surprising, and when I finally learned that you can apply this triboelectricity in your backpack, I was completely convinced. This was a nice feature. And finally, Professor Saibal Baju, he focused onto phenomena due to interface roughness in ultra-thin films. This surprised me totally. It involved low and large angle light scattering, X-ray scattering, and neutrons, up to Cooper pair reflection at interfaces. I couldn't digest everything, but I think it was very necessary to talk about that. And so you see, this was a very recent research which was talked about, not only today, but also the other days. And I think this meeting has brought a lot of insights, but also a lot of questions. So Spintronics is quite complex, I have to say that, and still many things to really understand. So I personally got a really good shower of this new physics, and I have to read it down and to digest it. Thank you all for that, and thank you, Subankar, for organizing such a well balanced meeting with colleagues who are really the experts in the field, not only in your country. You went around the globe to find other people, to enjoy them, and I think it was a full success. So
thank you. Thank you so much. Thank you so much, Wolfgang, for your kind words. We really appreciate, and I always learn things from you. So these are very helpful comments. Thank you. Now I request Professor Kalabaran Maiti to say a few words and his suggestions, input, whatsoever you want to suggest us.
Thanks, Shubhankar. So first of all, I think I should congratulate you and all the other organizers for organizing such a beautiful, nice field with a lot of ideas and new results, this kind of meeting. And Professor Kleeman actually very nicely summarized the science aspects. So anyway, I don't want to add much. So what I would say that, of course, I mean, I would have really loved to come to NICER. have good foods and also give you a little more trouble. But these online arrangements were not really bad. I mean, you people have done a wonderful thing. So everything went off very, very well. So thanks and congratulations to the whole team. I think the idea of this meeting, and the conception is really very nice. And of course, I mean, magnetism is one of my most favorite subject. And having initiating a meeting in that subject and Spintronics together, which has both importance in fundamental science as well as technology and so on, it's really great. And I would really like to thank you for that. And I'm sure it would be very, successful meeting or successful event for the future also. In this meeting, there are many highlights. For example, many topics have been covered very nicely, like domain dynamics, magnetism, in heterostructure, proximity effect, topological properties, quantum physics, and so on. Skyrmions, then DMI interactions, centrosymmetry. Many of them, of course, Professor Clemens touched upon. There are very nice talks on spin charge conversions, spin orbit torque, and so on. So, we can name several varieties of talks, and it was really, enjoyable kind of meeting. So, I would say that it's extremely good start, and it's a nice effort also, and I'm sure it will be a great success in the future. So congratulations to you and your team, and best wishes also, so that it goes forward, carry forward successfully in the future also.
Yeah, thank you so much.
Highly appreciate your effort. Yeah.
Thank you so much, Professor Maiti, for your kind words. I know you are too busy being the dean of TFR, but I really appreciate the last 3 days you have been constantly attending talks. We are really grateful for your support, and we will keep that in mind. Actually, today, unfortunately, we are running out of time, but I had something in mind to quickly, I can tell that I can contact to the seniors in the country to bring different people into onto the same platform where we can exchange ideas, not only conferences, to build like some scientific Facebook kind of thing where we can put our preliminary data, we can exchange ideas, we can share our problems, because experimentalists always face with this or that problem. If we can cover that, probably for that we need another discussion. I have something in mind I will share with all of you, and we would appreciate your comments and suggestions. Thank you so much.
Maybe I can just mention one more point. You remember that we both wrote a proposal on proximity effect. I was really, interesting to see Professor Shaival Goshu, Shaival, we call him, so his talk, which is almost in the same topic. It was very nice to see very nice results. And
yes, I will discuss with you on that. So now we have all the things, and probably you have also the spin polarized RPS is working now. We can make something. Yeah, sure. Thank you. Professor Ixi Su, you want to say a few words? He's also another person who listened all the talks.
Thank you. Yeah. First, I also like to really congratulate you. Okay, because first, congratulations to your institute's 11 years anniversary. Okay, I wish also you all the best, all the success for next 10 years. Okay. Second, of course, it's really a wonderful workshop. Congratulations for the organization and also your core committee member, all the volunteers, because I was in a chat room. I really chatted with one of your students. I was really impressed. I think it's been a wonderful experience for me to get interaction with the community in India, because it's great. I think this Magnetism Spintronics, let's say, since I'm working for Research Center Unity, you see, for me, it's no strange to, let's say, live or research in this boundary between Magnetism and Spintronics. Used to be when I was in Unity like 60 years ago, my office is directly in Leeds. Professor Grunberg. You knew that, yes? So you see, we have magnetism department focusing on material phenomenon. We have theory groups like Stefan Bluger focus on theory. We have, of course, a strong, powerful spintronic group focusing on the phenomenon, focusing on the device. You know, so I think it's, for me, today, this last 3 days, exactly, I just say, I exactly feel this seamless combination, you know, between magnetism, spintronic, just like we from Fortune Units had this long tradition. Yeah, yes, I would say congratulations, it's well organized. I really enjoyed. Of course, if you see there is something, I would say probably is one pity. I would love to meet you, all of you in person. I hope this might be achieved in the next year, who knows, okay? But anyway, this is definitely the best what you can do. It's a very smooth, high quality conference. Thank you. And yeah, thank you for the invitation. And I really enjoyed. Yeah.
Thank you so much, Ixi, for your kind words. You have been a fantastic friend over the years, and I really appreciate that you spent all the 3 days attending all the talks. Really great. I really appreciate.
I appreciate too. You attended the last. I remember MLZ conference a few years ago. Yeah, that's more or less like our last meeting in person.
Yes, 2019 June.
Yeah,
I gave the keynote talk, and that was the last meet. Yes. Too bad with Corona. So before I take some comments of the core members, I would welcome some comments by PhD, MSc, postdocs, if they want to come forward. Just spontaneously you come forward, raise hand. If you want to say a few things quickly, it would be nice. Yeah, Santosh, please go ahead.
So am I audible?
Yes.
Okay. Good evening, everyone, and also good afternoon and good morning to the people over out of India. I'm Santosh from 4th year integrated MSc, School of Physical Sciences, Niger. It has been a great pleasure for me to be a part of the team which is organizing such an international conference. I get to hear the speakers with whose lectures I have heard in YouTube's and other platform, but getting a chance to interact with them live, to hear them live, it was really a very big thing for me, and obviously it is not an individual effort. I would like to thank all the core team members as well as Shubhankar sir for organizing such a platform virtually and making it go. We really did some effort to organize the talks in the virtual platforms in the frame, and I really appreciate all the cooperations from the speakers as well as the participants in making it a very great success, as I think. But yeah, one regret is there. We couldn't meet in people. If it was offline mode, then it will be, again, it would have been a very great success. But I really hope in the coming years SMS will be in offline mode, and I get to interact with the speakers in people, and to have some very good time with it. And again, I would like to thank the core team members and Shubhankar sir for giving me a chance to be a part of team to getting involved in this conference and contributing to it to make it a very great success.
Thank you, Santosh. Hopefully next year onwards we can organize offline conferences. That's a dream for many now. Let's see. Thank you for your involvement in SMS. If there is somebody from outside NICER, a participant would say some. Anurag Singh, yeah, please go ahead. Anurag, you can switch on your camera if you wish.
Hi, hi, sir. Sir, I am from NICER only. Sir, from first year, integrated MSc. Sir, actually, it was like awesome lecture, but it's not like I got much of it because I just started on my journey of science. But it was amazing to hear from so many amazing professors from outside India and from top institute of India as well. That's what I like to say.
Okay, thank you, Anurag. Anurag is one of our first year MSc. He just came to campus 1-2 months back, and I'm really amazed by your enthusiasm. Okay, it is maybe difficult. It's a bit special topic.
Yes, sir.
Hopefully,
yes,
in future you can understand it. Okay, thanks, Anurag. God bless you. Anybody from outside NICER wants to say something? Any complaints, any regrets, any anything? Okay, so I will take it as no complaints, no problems. Okay, so I request Professor Anjan Burman to say a few words. He is one of the core committee member and always an advisor. Please go ahead.
Yeah, thanks, Suhankar. And first of all, congratulations to the whole team. And that comes to me also being a core member. So for organizing this conference, I just wanted to say that when I joined and came back to India 15 years back, this Spintronics, although magnetism has always been a very strong, topic of Indian research community, Spintronics was nearly non-existent, almost non-existent. So finding people working on Spintronics or spin dynamics or magnonics didn't even start very well properly in the international level also. Was very difficult. And that time we tried to have an Indo-EU project on a related topic, and I just literally had to search through Google, and I only knew Anil Kumar, PS Anil Kumar in ISA Bangalore, and I literally searched through people and found a few people to be able to write a proposal. So starting from there and then coming to this point has been a long journey, although it's only 15 years. See. So I have always been discussing, and then I met many people. Slowly Subankar came and Muduli joined and many other people. I mean, of course, Ashwin was almost, Ashwin is actually contemporary to us. Probably he joined at the same time. I didn't know about him. Then I got to know him. So slowly we found that we are probably reaching a critical mass when we can talk about spintronics or spin dynamics, not let alone having a conference. Okay, so then we had many series of conferences where small, sort of sessions of spintronics, spin dynamics started to come into picture. And then, I think now we have a whole lot of, many young people around, which also helps for, sort of thesis examination of our students. This is one of the points. Like we actually really struggle to get our, the thesis of our students examined by the community, because many people are not from this community. So really, I mean, it's a great journey altogether. Regarding, and when actually Subhankar one day called me, actually he emailed and called me and sort of talked about this conference, I was very excited and I said, yeah, let's make it a little bigger than what you may have originally planned. Let's have a core committee and have it done in a very sort of comprehensive way, when many other institutes will also pop in and have the conference in different cities and all. And then he immediately agreed, and then we formed that core committee and things started to move very nicely. And it was, of course, it's a pity that we could not meet physically this time, but I mean, we'll definitely meet next time, and we'll discuss about the next sort of venue and host. Regarding this conference, I have listened. I missed a few talks because of various administrative duties, but I listened to many talks, and it's really like almost a circle is being completed. Only one thing I have noticed is that although the Indian spintronics and nanomagnetism community has grown in last 15 years quite a bit, but unfortunately the magnonics community hasn't grown that much. So this is, of course, people are working on ferromagnetic resonance and all this, but spin wave propagation, magnon current. I mean, I must say that we are very excited about this pure spin current and stuff, because when we are going towards the non-von Neumann, like shifting from von Neumann computing to non-von Neumann computing, one of the chief aspect is, of course, the energy. Other is the bit error rate and so on. And there, sort of pure spin current, we are excited about it, but there is a energy dissipation related to the charge current, which actually creates the pure spin current. So we cannot call it dissipationless altogether. But if we actually move to magnon current, because of the lack of movement of any particle, charge particle or anything, the dissipation is much low. So we should actually think about it very carefully. And I must say that very recently, magnon drift current have been discovered by Pietro Gambardella's group in ETH. And it's a very nice paper. We had the chance to write a viewpoint on that in Physics magazine of APS, where they used the non-reciprocity using Zalesinski-Moria interaction to actually create a drift, because the electric field and charge relationship doesn't hold good for magnon and magnetic field. So magnetic field will not cause a magnon drift current directly, but you need to have break the symmetry, and they have shown it very nicely. So new things are coming up, and recently we wrote back-to-back, one magnon roadmap, 2021 roadmap on magnonics, and spin wave computing. The wave-based computing is another thing. So all these things are coming up. So I would, sort of urge the Indian community, magnetism community, to focus on magnonics also, because this is something the whole world is looking into, and probably something that we are missing to an extent. So particularly the younger people must come up with more work on magnonics. It's a little bit, sort of the know-hows and all these are a little bit different, but of course, some of us are very happy, will be very happy to help people. So this is what I wanted to say, and of course, more invited talks from remote places, like to give to all inclusiveness is something that we should also look forward to in the coming versions of this. So thank you so much.
Yeah, thank you so much, Professor Anjan Burman, for very useful suggestion. I completely agree. For instance, below light scattering, you are our champion, only one, but I think in a country like us, we should have more, and probably more of your alumni will come back to India and start to build groups. And this is something really necessary to expand the horizon of magnonics community. And hopefully, as you told, it took 15 years to have now a reasonable number of Spintronics people, maybe in another 10 years or so. But we should not take very long time, because it is very competitive and expanding at other places very fast. I completely agree with you. Anil, I request you to say a few words. Professor Anil Kumar.
Yeah, thank you, Shubhankar. Thank you for arranging this wonderful conference. It was a really good conference with a mix of everything. And I think everybody got benefited out of this conference. As Anjan pointed out, now we have an ecosystem probably shaping up in the area of Spintronics. So in that sense, maybe it's a good idea that, we have frequent meetings, and then, exchange ideas and probably collaborate. See what's happening still here is all isolated, entities. This collaboration, if a sample going from one place to another place for a different kind of a measurement. So those kind of things are still probably we have not reached that stage. It is happening in isolation here and there, but not, I mean, if you look at some of the international papers, you see large group collaborating on different aspects, and all expertise are combined together and getting a highly impactful work. So probably I think with this kind of conferences, we should also give emphasis to kind of collaborations in future. So the facilities which is not available at one place can be utilized in some other place, and then probably better ideas and good quality publications can come up. And also the students also will get a good network. I mean, networking is very important, especially among the peer groups. For different age groups, there are different peer groups. So this kind of conferences also will bring, probably students from different labs also for networking, and when they can discuss among themselves and understand very fine details which is not available in a paper, how did you get that? So those kind of tricks is something that can happen only through talking to each other. So I would strongly recommend that this kind of conference, this conference to continue at different places in the years to come. So congratulate you for initiating this action. And I thank all the student volunteers and everybody who meticulously worked out to get this conference into this shape. So thank you all. Thank you.
Yeah, thank you so much, Anil, for your kind words. You have also been like a mentor to me. So really nice. I completely agree. I think I had something in mind because you people have told. I can just quickly tell in 1 minute. I'm thinking like we are experimentalists and we go through many difficulty, like a pump in a sputtering goes bad or a PLD target breaks. And we are almost working on similar platinum, cobalt, cobalt, iron, boron, many other materials too. And measurements are also sometimes almost similar, characterization equipments, and one goes wrong. So we can have like a common platform where we can exchange our problems, and also we can exchange our happiness, excitements about new results. Sometimes we don't understand some results, we keep it aside, maybe we can discuss. And as you said, if we want to compete with the rest of the world, we have to really come together and make this consortium, and we have to come up with some ideas. I will come back to that later with all the senior people and friends. And to the collaboration, I think, I remember your short address in the which summit that organized by Prime Minister's office. Now it is getting Anil. What was that? Which was organized by Bhaskaran from IIT Bombay.
Yeah.
Which summit was it?
I also forget the name of it. This is about quantum technology.
Yeah, it was about quantum technology, and we were asked to present something. I was asked to present the future of Spintronics and Magnonics, and I addressed, and I remember your slides where you specifically mentioned that for young people, it becomes very difficult when their institute asks, what is your contribution in this paper where you are author number 4 or 5? I think this is something which has been very discouraging, and probably that mindset need to change. Otherwise, for young people like Chandrasekhar or others, I don't know, I'm already 10 years old, so probably I'm not young, but I'm not also very senior. So my situation is very bad. But for people like Chandrasekhar, who is very young and newly joined, I think for them it becomes very difficult when they comes into a big collaboration and their name goes somewhere. So people try to figure out what is exactly his contribution. So this mindset has to also change. I really admire that you mentioned that in that meeting. And I think we have to really come together, irrespective of whatever people think, and we have to do some interesting physics or interesting science. Yeah, thank you, Anil. I don't know, Pranamba, are you here? Yeah, Pranamba, you want to say something? You are another core committee member. Kindly share your view if you want to say a few words.
Hello.
Yes, please go ahead.
Yeah, I think most points are already spoken by Professor Anjan Burman and Professor Anil Kumar. It is indeed a very good initiative from your side to start such a conference which is focusing on spintronics and magnetism. And this was really missing in some sense. Of course, we have this Triple M, that is the biggest conference that happens. But from Indian point of view, we do not had a similar kind of conference whose focus is mostly magnetism and spintronics. So this was good start from you, and I congratulate you for success of this conference. And I could not attend all the session because of this end semester and a lot of other responsibilities I had to do. So I could not attend all, but I attended some at least, and I fully enjoyed all the talks, and they are really of high quality. So yeah, I hope that we can continue this now and make this a bi-yearly event and exchange idea between the Spintronics community in India, and also we invite international speakers for improving the quality of this conference and so on. So yeah, I think I will stop it here. Because
okay, thank you. Chandrasekhar, you want to say something? You are another core committee member from IIT Hyderabad.
Yeah, first of all, thanks for the opportunity to become to be a core committee member, and whatever the talks I have attended, I really enjoyed, and congratulations for the success of this SMS-1. And I hope that it will continue for the coming years. And before I just wanted to conclude that I really thank Professor Ranjan Barman, Anil Kumar, and all the seniors who is saying that they wanted to give a helping hand to the young people like us. You, I mean, in fact, you mentioned my name as well. And yeah, we really appreciate whoever joins recently. Your helping hand, and then with collaboration, we would like to grow, and then we would like to enjoy doing the science. So thanks a lot. And in that sense, already, I mean, just wanted to mention a small thing that Professor Mutli really helped me while I'm setting up the sputtering. In fact, he gave me a lot of suggestions. So I hope, thanks a lot to him. So I really appreciate. And just to tell that Professor Ranjan Barman that Dr. Arvinda Haldar, who is a colleague and a very good collaborator of mine, and he is really working hard to get this Magnonics done, and hopefully he will follow your footsteps. He is your student, and we will be able to do something great in Magnonics in very soon. And thank you, Professor Shubhankar, for giving this opportunity. Thank you.
Okay, thank you. We are actually a little bit over time. So before I wrap up, I request the core committee, if anybody wants to say. It is like, actually, I thought of making a conference with SMS, like SMS going to your mobile. So we will say like SMS-1, SMS-2, like that. So can we think about a venue, possible venue for SMS-2? Because it will not be nicer. It would be good to have another city. So any spontaneous offering who wants to host it?
See, we can, I mean, we will be very happy to host, but I was thinking if Perumal actually agrees, we can have it in Guwahati. So something that a place we all would be very interested to go visit.
Okay, he is not here, I'm afraid. So I will talk to him. If he is willing to do that, then it is good. Otherwise, we need to discuss, and we can convey this to the participants. We have all the email list. And it's good to know. I mean, we should not think after 1 year where to make it. We should just do it as soon as possible. This is my suggestion. So I agree with you. If he agrees to host it, that would be nice. Otherwise, anybody else wants to?
If not, I mean, maybe this. If you give a chance to the young people, of course, we also have some seniors like Dr. Jyotiranjan Mohanty and Dr. Surya. So at IIT Hyderabad, maybe we will try to arrange with the help of other colleagues like Dr. Arvinda and all of us, if at all we get a chance.
Okay. That will give us a chance with the good biryanis and all.
Yeah. So we
have. You have to offer
small
good
Spintronics
biryanis to all the participants. Okay. So that means. All right. So let's.
So this was almost free for Shubhankar because this is online, so no food and nothing.
Yeah, please. Go ahead.
Okay. So
you can, Shubhankar, you could order some pizza and get it delivered to our doorstep.
All right, I will do that. I think. So the idea is it will be either in IIT Guwahati if Professor Perumal agrees. Otherwise. Professor Chandrasekhar Murapaka, IIT Hyderabad, and then we can subsequently think where to go forward. And if other people wants to come forward to discuss with us, please feel free. We are absolutely open in discussing and interacting. So it's not really a closed box. So this is just the beginning. So we had to come with some core committee members, but we are absolutely open. And I will share some ideas about this open platform where we can exchange ideas, mostly problems and excitements. And that has to come. That will probably take a little bit of time. I will come back to that. So with this, I think we are done. 3 long days. And I really thank you all again so very much for your kind cooperation and also blessing us on the 11th birthday of Laboratory of Nanomagnetism and Magnetic Materials. I was very happy to see many of my former PhD, postdoc, MSc students who are really doing excellent at their respective places. And to host actually most of my collaborators, mentors, peers in this conference, I could not take everyone because I didn't really want parallel sessions in online mode. That would be horrible. But next time, I hope we can meet in person, either in Guwahati or in Hyderabad, in SMS-2 and subsequent SMSs. And yeah, with this, I wish you all a very healthy time because again, Corona is spiking at places. And in a month time or 5 weeks, we will have 2022. So in advance, a little bit too much in advance, but I want to wish all of you a great start for 2022 and a happy new year in advance. Thank you so much. And on behalf of the organizing core committee, thank you so much. So God bless you all and see you next time in person somewhere. Bye-bye.
Thank you. Bye.
Thank you.
On the lighter side, Muduli, are you sitting in front of the building or what?
No, it is just this.
No, Anil's is quite, sort of apparent that it is a background.
Yeah.
This one is almost
I brought the
impeccable.
building to my home.
I was sitting on the
Similarly,
lawn.
Professor Anil Kumar is also sitting in very greenish background of the IISc Bangalore.
Bye-bye, Shubhankar. Bye-bye. Thank you.
Bye-bye. Have a nice weekend, all of you.
Thanks.
Bye-bye.
Thank you.
Pleasure. Bye, Anil. Bye all. Bye, Anjanda.
Bye, Shubhankar. We'll
Bye,
talk to
Chandra.
you.
Bye, Bye. Bye all. See you next time. Thank you so much. Good night.
Good night.
Good night.